Today's video, we're going to take a look at answering the big question. What is calculus? And really, calculus is going to be the answer to 3 questions. The first question that we're going to attempt to answer, and we're going to focus on here in Chapter 2, is what is it getting close to? And this in calculus we're going to affectionately call the limit. The second question we're going to attempt to answer, and it's really the focus of Chapter 3, is what is the slope? Specifically, what is the slope at this given point? And there, we're going to call that in calculus the derivative. The third question we're going to attempt to answer is, what is the area? And we're not going to really dive into that question until we get to Calc 2 next term. But for now, I'll just tell you that that is the integral of the function. So to kind of set this up, we're going to take a look at, first, the tangent problem. For the tangent problem, I want to first consider how fast these lines are changing. And we really call that our rate of change. So I'm going to put 3 graphs up here. First graph is going to be y equals 2/3 x minus 1. In this graph, I'll have a y-intercept at -1, and it'll rise 2 and run 3 to another point. So it's going to look something like that. The second graph we're going to look at is y equals -3x plus 2. And so that graph has a y-intercept at 2, and it slopes down 3 over 1. And it looks like this guy. And the third graph we're going to look at is y equals -1. And that's just a flat line right at -1. And the question here that we're considering is, how fast are these lines changing? How are these lines changing? The first graph here, the 2/3 x minus 1, we see it is going uphill from left to right, but it's going uphill slowly. It's kind of gradually working its way uphill, which is different than the second graph, because not only is it going downhill, but it's also going down much quicker. It's going downhill quickly. And that's going to be different than this third graph, which really isn't going up or down. It's kind of flat-lined. So we'll say this is a flat or no change. Now, what's interesting here is these lines are really easy to see how the graph is changing because they're just a straight line. They're always changing at the same rate. A is always going up slowly, B is always going down quickly, and C is always flat without any change. But this is not always the case. Actually, most functions do not have a constant rate of change. For example, if we consider the graph y equals x squared plus 2. Now, y equals x squared plus 2 has a vertex right at 2. It's got the point at 1, 3, and negative 1, 3, and then 6 and negative 6. Or I'm sorry, 3, 6, and 3 negative 3, 6. So here is the graph of x squared plus 2. Now, if we consider at the point 0, where x is equal to 0, if I were to look at that graph, it's kind of leveled out there at the bottom. We could draw a line that's tangent to that point. And right now, it has a slope of 0. It's really not changing at that point. It's not going up or down. It's kind of leveled out at the bottom. That's a little different than if I consider the point that's just 1 to the right. Because at that point, it's actually got a much steeper tangent line that could be drawn that barely touches it. And there, the slope of that graph, it's going uphill. It's actually rising 2 and running 1. If I could grab a different color, we could look at this point at negative 1 or negative 2. Looking at the point at negative 2, we see it's very, very, very steep. In fact, the slope there is going to be negative 4. And we'll talk later about how we can actually calculate those exact slopes. But what's interesting here is this graph starts out with a very steep negative slope, and then it levels out and turns into a positive slope, which gets steeper and steeper. I've already hinted at this, but the lines that touch the graph are what we're going to call tangent lines, where they touch the graph in one point and then go off into the distance. So the question we're going to attempt to find out is, what is the slope of these tangent lines? To do that, we're going to set up another thing called the secant line. We can actually approximate the rate of change or tangent line with what we're going to call a secant line. Here's what we mean by that. So we've got some graph here. We're going to say it comes in, goes up, and levels off. And right here we're going to say is A, which means if we go up, this point here is going to be at f of A. And then a little bit over from A is B, and if we go up from B, that point right there will be at f of B. If we connect A and B with a line, that is called a secant line. A secant line is going to go through 2 points on the line. In fact, we know what those 2 points are. Let's go ahead and label those in brown. The x-coordinate of this first point is A, and the y-coordinate is f of A. And the second one with B, the x-coordinate is B, and the y-coordinate is f of B. And if we wanted to calculate the slope, which we always use m for slope, of the secant line, we know it's y2 minus y1 over x2 minus x1. So that would be f of b minus f of a over the b minus the a. This is going to be an important formula for us, the formula for the slope of the secant line. And what's interesting about this is as A and B get closer and closer together, let's draw another graph. As A and B get close, see if I can draw that same graph on here, approximately. And if we keep A at about the same spot, and so f of A is still at the same spot. But if we put B right next to it, notice it's closer now for f of B. The secant line that connects them is starting to look like a tangent line that only touches in one spot. In other words, as A and B get closer together, we get closer to the tangent line. This is the big idea that we're going to go after today is, can we get A and B close enough together so that we can estimate what is the tangent line? Let's try it, though, with some numbers in there to make things a little clearer. So let's do number 4. We're going to do an example here. We're going to estimate the slope and equation, while we're at it, of the tangent line to the function f of x equals 2x squared minus 3 at the point 2, 5. Now, the idea here is we want to estimate what it is using a different x and y point, where we're going to try and get closer and closer and closer to our actual point of 2. So we know at 2, the y-coordinate's 5. So we'll start kind of close to 2. Maybe we'll start at 2.1. Then we'll get a little closer, 2.01. Then we'll get a little closer, 2.001. And then finally a little bit closer, 2.0001. And we're going to see what y equals at each of these points. We know at 2, it's going to hit 5. But what's it going to hit as we get close to 2, as we pull b closer and closer to our a? Fortunately, this is going to be really easy to do on our calculators. So if we turn our calculators on and hit the y equals button, we can type in our function in y equals. And our function is 2x squared minus 3. Then what we're going to do is if we hit the second button, and then right above graph we see in blue it says table. And we should be able to delete these values out of here. If you cannot delete the values out of your table, first hit Secant, and then above window you see it says Table Set. And we're going to change the independent variable, the x, to ask, so that we can pick what we want that x to be equal to. Now go back to Secant Table. And now we can enter in our values we want for x. The first value we want is 2.1. The second value is 2.01. The third value is 2.001. And the third value is 2.0001. And we start to see we get these values for y. Let's record them in our y column here. That's 5.82. The next one was 5.0802. The next one was 5.008. And then finally it was 5.0008. So now what we really end up with is a third column. Let me label it in black here. X comma y is going to be our third column. These are going to be our points that we're going to compare to the original point of 2, 5. So x comma y is 2.1 comma 5.82. Then we had 2.01 comma 5.0802. Then we had 2.001 comma 5.008. And then finally 2.0001 comma 5.0008. We're going to use these points and the original point, the 2 comma 5, to calculate a whole bunch of slopes of the secant line. And again, we're going to use the calculator to help us out with that, to make some of these calculations easier. If we hit Secant Quit, it'll take us back to the home screen. Quit is right above the Mode button. And then we're just going to type in our slope formula, where the numerator and denominator need to be in parentheses. So the y2 we calculated from the first point was 5.82, minus the y1 was 5, because we always go back to the original point, divided by the x1 from the point we found, the 2.1. Whoops, need to put it in parentheses. 2.1 minus the 2. Close the parentheses, and when we hit enter, we find our slope right now is 8.2. So let's go ahead and record that. Our slope right now is 8.2. But then we're going to move a little bit closer. Now we're going to use our second point, which is the 2.01 comma 5.0802. Again, y2 minus y1, so 5.0802 minus the y from our original point of 5, divided by the 2.01 minus the 2. Again, remember, numerator and denominator in parentheses. And now we have a slope of 8.02. Let's try our third point. Our third point was 5.008 minus the 5, divided by the 2.001 minus the 2. And now we're going to get this nice, pretty 8. Our slope right now is 8. In fact, when we do it again for the third point, we're going to get the exact same thing, because we are so close. The difference is going to be minuscule. 5.0008 minus the 5, divided by the 2.0001 minus the 2. And again, we get 8 for the slope. So we can use this fact to estimate the slope of the tangent line now. We see the slope of the secant line is getting closer and closer to 8.0, so the slope of the tangent line is probably that 8.0 that we're getting closer and closer to. So if it is 8.0, then we're ready to actually calculate the equation at that point. And going back to our algebra days, a good equation to remember that the equation of the line is equal to y equals m times x minus x1 plus y1, where x1 and y1 are a point we know that's on the line, and m is the slope. This is a good equation to commit to memory because we are going to use this equation a lot in this course. So for our purposes, we've got y equals m. The slope of the tangent line we just found out was 8, times x minus x1. Going back to our original point, the x-coordinate was 2, plus the y-coordinate of 5. The equation of our tangent line to 2x squared minus 3 at 2, 5 is this guy, y equals 8 times x minus 2 plus 5. We can use this concept in physics to look at what's called the average velocity and the instantaneous velocity. Velocity is really talking about speed. So if we're talking about the average velocity or the average speed, speed doesn't really have direction, and velocity does have direction. It's only real different. The average velocity of an object can be found by the velocity average is equal to the function at the first point, at the initial point of time, minus the function at the final point in time, all over the difference in the times. And really, you'll notice that this equation, while I mark it as an important equation that we need to know for our course, it really is the same equation as the secant that we've already worked with. And then, if that's the average velocity over an amount of time, we can find the instantaneous velocity. Or how fast the object is moving at a specific point in time instead of an average over a range. It is found by making t2 closer to t1. In other words, the same idea we did before. If we try closer and closer and closer numbers, we'll get closer and closer to the actual instantaneous velocity, which is the slope of a tangent line. So let's try an example problem where we can see that actually done. Let's see, an object is dropped from the top of a 144-foot cliff. And it will land 3 seconds later we can actually find the function for its height. Its height is given by the function f of x equals negative. Actually, let's not do f of x. Let's make it more descriptive. We're doing height, so let's say height of t, or height of time, is equal to negative 16t squared plus 144. We're going to find the average velocity between 2 seconds and 2.01 seconds, and between 1.99 seconds and 2 seconds. So the average velocity just after 2 seconds and the average velocity just before 2 seconds, and see what we can learn about that. So first, for the first point, I'll do this first point in blue. The average velocity, we need to know what the height is at those 2 points. So we'll say h of 2, and I'm just going to plug this into our calculator. Negative 16 times 2 squared plus 144. When I do that on the calculator, we get 80. So the height at 2 is 80. And the height just afterwards at 2.01. Again, if I plug that into my calculator, negative 16 times 2.01 squared plus 144. That's going to equal 79.3584. 79.35. Let's just round it to 8. So the average velocity, then, is going to be the slope between these 2 points. So the average velocity is equal to y2, which is 80, minus y1, 79.358, over the difference in the x's, 2 minus 2.01. The average velocity here is negative 64.2 feet per second. So just after 2 seconds, the object is moving at 64.2 feet per second. It's negative because it's going down. Let's see what's happening just before. We'll do this in green off to the right here, so we keep these separate. So we need to know what the height is at 1.99 and what the height is at 2. Fortunately, we already calculated the height at 2. That's 80. If we put the 1.99 in our calculator, we'll end up with approximately 80.638. So to find the average velocity here, we'll subtract the y's divided by subtracting the x's. So 80.638 minus 80 divided by 1.99 minus 2. And when we do this, we find out the average velocity just before 2 seconds is negative 63.8 feet per second. And what you'll notice is both of these are really close, 0.2 away of each side of the negative 64. So we can actually find out or estimate the instantaneous velocity to be somewhere in the middle of these two guys. So between 64.2 and 63.8, it's probably at 2 seconds, at that exact moment in time, moving approximately negative 64 feet per second. That would be the tangent line or the instantaneous velocity. So with this preview so far, we've answered really the first 2 questions. We've been looking at what is the slope or the tangent, and then also what is that secant line getting close to. Let's take a look at a little preview of the third question of calculus. We won't spend much time on this because it's really a second quarter calculus question. But the question is, what is the area? Here's what that looks like in calculus. Going back to part C, addressing the area problem. We are going to consider, actually let's make this number 1. Consider the area under y equals x minus 3 squared plus 1 between the x values of 0 to 3. We're going to need a really tall graph for this, but that shouldn't be too bad. We got plenty of space here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we know x squared is the parabola shape. The minus 3 moves it to the right 3. The plus 1 moves it up 1. So the graph is going to look something like this. And it wants the area between 0 and 3. So between 0 and 3, what we're really doing is saying, what is the area that fills in underneath the graph? What we want is the area shaded in green here, is how much area is underneath the graph. So we can estimate it. And the way we're going to estimate it is we're going to say, hey, it's really easy to find the area of a rectangle. So we can use rectangles where the right corner of the rectangle actually touches the graph that we're talking about. So let me see if I can recreate the graph here. So it hits at 9, 3, 1. Is that right? It hits at 10. So here's our graph, roughly drawn. And what we're going to do is we're going to take each point and make it into a rectangle where the right corner of the rectangle touches the graph. So each rectangle is 1 wide. And the first rectangle is 1 high. The second rectangle you see is 2 high. And the third rectangle, I think it's 5 high? Yeah, it's 5 high. So we could say that the area under here is 5 plus 2 plus 1. Or the area is approximately 8 when we use rectangles on the right side, where the right corner hits the graph. But we could also do it the other way, because the problem here is we end up a little bit short. Let's use just some gray space for the short. Notice we miss this gray triangle, and another gray triangle, and another gray triangle. We're short because we went to the right. So to avoid being short, we could draw rectangles that the left corner touches the graph, and see how that compares. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 1, 2, 3, 4, 5. Putting our key points on here of 3, 1. Move over 1 and up 1. Over 1 and up 1, 2, 3. And then finally the 9. So if I wanted to draw rectangles where the right corner or the left corner touched the graph, we would start at the top point and say, OK, come out from the left corner, and there is my first rectangle. Then come out from the left corner, go over 1 unit, and there's your next. And come out from the left, and there's our next rectangle. And so we end up with 3 rectangles again. And we can find the area of those rectangles The first rectangle on the left has a height of 10. Actually, let's put, whoops. Let's put, wrong color. Let's put the heights on the right here. A height of 10. The second rectangle is a height of 1, 2, 3, 4, 5. And the third rectangle has a height of 2. So when we add those together, the area that we end up with is going to be 10 plus 5 plus 2. The area comes out to be approximately 17. But again, we've got a problem. Because now instead of having too little area, we end up with too much area. We've kind of got this area that I'm going to color in gray that sticks up above the graph. So the first time we were too low, the second time we're too high. How are we going to estimate what the actual value is? Well, we could estimate, since we're just estimating. The actual area is in the middle of these two values. So we could just average the 8 and 17. 8 plus 17 divided by 2. When we do that, we get a 12.5. So we're going to say our final estimate is that the area underneath y equals x minus 3 squared plus 1 between 0 and 3, we're going to estimate that it's about 12.5. Well, as you might expect, this process is not perfect because actually the actual area is 12 exactly. So we got an extra 0.5 out of it, but that's not a bad estimate for just kind of drawing rectangles and estimating and making a guess at it. Now, in Calc 2, we'll talk about some methods to find that exact area of 12. But for now, I just want to kind of expose you. This whole lesson today is just a preview of calculus. Just expose you to the idea of the 3 questions that we're going to be addressing in calculus. What is it getting close to? We call that a limit. We're going to focus on that in Chapter 2. What is the slope? We call that the derivative, and we'll focus on finding that in Chapter 3. And then finally, what is the area? We call that the integral, and we're going to find that in Calc 2. So I hope you enjoyed this preview of calculus. Take a look at the practice problems in the book, and I'll look forward to seeing you in class. As we dive into our study of calculus, we need to answer the first foundational question of what is a limit? So we're going to answer that question kind of broadly today, and then a little bit later we'll answer it more precisely. So we're going to kind of say the intuitive definition of a limit. So the general idea that we're going for when we say a limit, we're saying what value, what should be there even if it is not there. What should be in the function, even if it's not actually in the function at that point. And symbolically, how we'll represent that is we will say that the limit as x approaches some number of f of x equals L, or the limit. So again, mathematically, or in words, what those symbols up above there mean is that as x gets closer to a, the f of x gets closer to L. we're trying to figure out what is the function approaching, what is it getting closer to as our x gets closer to some value of a. So there's two main ways that we're going to do this. The first way that we can find a limit is what we're going to call the table method, where we basically take that definition that says as x gets closer to a, well, let's try and get closer to a. We're going to try values closer and closer to a, or to that number that x is supposed to get close to. So what I mean by that is we are going to find the limit as x approaches 2 of x squared minus 4 over x minus 2. Now, if I were to just try and find what 2 actually equals in this function, you'll notice it's going to end up being undefined. There's actually nothing at 2. But we're not interested in what's actually happening at 2. We're interested in what should be at 2, even if it's not at 2. So to set this up, we're going to make a table where we're going to take various values of x that are going to get closer and closer to 2. And we're going to see how that compares to f of x, or our function. So we'll start maybe at 1.9. That's a little shy of 2. And then we'll get closer, 1.99. And then a little closer, 1.999. And even closer, 1.9999. We're going to get really close to 2 and see what happens to f. Now, an important part of a limit is it has to work on both sides. So we can't just do values a little bit smaller than 2. We need to pick values for x and calculate f of x that are a little bit bigger than 2. So we might start with 2.1, go a little bit closer, 2.01, a little bit closer, 2.001, and a little bit closer, 2.0001. Now, fortunately, our calculator's table settings are going to make these calculations quite nice for us. So if we turn on our calculator and go into the y equals function, I can hit clear to delete anything that might be in there already. And the function we're working with is x squared minus 4 over x minus 2. Now, to preserve the order of operations, I need to put in parentheses the numerator and denominator. So x squared minus 4, close the parentheses, divided by, open a parentheses, x minus 2, and close the parentheses. And now we'll go to our table by hitting Secant Table. And there's values in here from a previous problem we don't need, so I'm going to delete those all out. Our x's here start at 1.9, enter. Then we've got 1.99. Whoops, too many 9s. Enter. Then 3 9s, 1.999. And then finally 1.9999, 4 9s. There we go. And what we see is we get 3.9, 3.99, 3.999. So let's record these. So first we start with 3.9. Then f of x becomes 3.99. Then it became 3.999. Then it became 3.9999. You can kind of see that's getting closer and closer to a very clear number. But to check it, we have to go on the other side. So let's delete out what's in the table here. And let's check these other values, the 2.1, the 2.01, the 2.001. Whoops, too many zeros again. And then the 2.0001. And we kind of see the same pattern here. It won't always be a clear pattern like this, but this one's kind of nice. So we can record our f of x became 4.1, 4.01, 4.001, and then finally 4.0001. And what we see is from the left side, these numbers are getting closer to 4, growing and growing and growing to 4. From the right side, these values are also getting closer and closer, shrinking and shrinking down to 4 as we shrink and shrink down to 2. And so what we can say then is that the limit as x approaches 2 of x squared minus 4 over x minus 2 seems to be, from this table, equal to 4. Now, this doesn't mean that x squared minus 4 over x minus 2 is equal to 4 when x is 2, because it's undefined at that point. There's nothing there. The limit is just what should be there, even if it's not. So we'd say 4 probably should be in there, but it's not. As we get really close to 2, we're getting really close to 4. Let's try another example. The table method's really nice when it works, but it doesn't always work as beautifully as we would hope. We're going to find the limit as x approaches 0 of the cosine of 1 over x. And again, just like before, we're going to take some values for x that are a little bit smaller. It's a little bit smaller than 0. Might be negative 0.1, negative 0.01, negative 0.001, negative 0.0001. And we're going to find what f of x equals. And then we'll try some values for x that are just to the right of 0. 0.1, 0.01, 0.001, and 0.0001, getting closer and closer to 0 from each side. Again, we're going to have our calculator do the dirty work for us, but we need to change the function. So we'll clear out the old function. Starting with our function is cosine of 1 over x, close the parentheses. Now, something to check, if I hit the mode button, which is right next to secant, I should see that radians is highlighted. We will always be in radians in this course, so make sure the radians is highlighted. So we've got the cosine of 1 over x. And then when we go to our table, hit secant table. I've got to delete out the old values. And for the first column, we've got negative 0.1, negative 0.01. Then we've got negative 0.001. Whoops, got an extra 0. Negative 0.001. And finally, negative 0.0001. And this guy seems quite all over the board. What you see is f of x begins by equaling negative 0.8391. Then it was positive 0.8623. Then it was positive 0.56238. Then it was negative again at 0.9522. Let's try, delete these out. Let's try the other sides. See what patterns we see on the other side. 0.1, 0.01, 0.001, and 0.0001. We get actually the exact same numbers with the exact same randomness. F of x seems to be negative 0.8391. 0.8623, 2, and then 0.56238, and then finally negative 0.9522. Now, in the first example, coming from the left, we started approaching a number, and coming from the right, we started approaching a number. But this time, we don't seem to be doing that. We are not approaching any one value, which actually, if we were to graph this function using a graphing calculator, or maybe a great website is Desmos, where you can graph it, this graph kind of goes up and down, and then it starts to become really crazy as it gets next to 0, and then it just becomes really crazy. So it's really hard to see what's happening, because it's going crazy. It's not approaching any one value. So in this case, when our table method fails, we say the limit as x equals 0. Actually, let's do this in red. We will say the limit as x equals 0, or x approaches 0, of cosine of 1 over x equals dne, which is going to be an abbreviation for does not exist. Because it's not approaching any one value, it's kind of going all over the place, we're going to say this limit does not exist. So our first strategy for finding the limit is what's called the table method. We take values that are closer and closer to the number we want and see what the function is getting closer and closer to on both the left and right side. The second method is what's called the graph method, where we can actually look at the graph and see what y value is the graph approaching. So let's draw a graph here that we can play with. And let's see, we're going to put a vertical asymptote here at 2. I'm going to put a point at -1, 3. I'm going to put a hole at 1, 2. But I'm also going to put a point at 1, -1. I'm also going to put a point at 2, 1. And then an open point at 2, -1. And I'm going to bring the graph down from that 2, -1. Starting at the asymptote, I'm going to come up from the asymptote and then kind of go through my points. All right, so we got this funky looking graph. A lot of weird things happening, but that's OK. The first question we're going to attempt to answer is to see if we can find the limit as x approaches -1 of this function. So as x approaches -1, what we see is the graph is really approaching a y value of 3. So we will say the limit as x approaches -1 on this graph is 3. What's the limit as x approaches +1 of this graph? Now, it's interesting to note at +1, this graph clearly is equal to -1, because that's where the solid dot is. There is an open dot on the graph, which means there's a hole that's not actually there. But with limits, we're interested in what actually should be there, even if it's missing. And you see the graph coming in from both the left and the right are really getting close to a height of 2. And so we'll say this graph is getting closer and closer to 2 as we get closer and closer to 1. Even though, if I were to ask what f of 1 is actually equal to -1. But it doesn't matter what the point actually is. What matters is what is the point getting closer and closer to. One more. Let's take the limit as x approaches 2 of f of x. Now at 2, this is interesting, because at 2, from the left side, let me see if I can get rid of some of this red. It's kind of getting in the way. At 2, we see from the left side, the graph is getting close to 1. But when we come in from the right side, it seems the graph is getting closer and closer to -1. Since those are not the same values, it's not approaching the same value from both sides, we have to say that this limit does not exist because we're not approaching one value. We can't say there's one value that should be there because it's really approaching two different values. Which kind of sets up the idea that if we're approaching one value on the left and one value on the right, why don't we call those two different limits? And that sets up this idea of what we're going to call a one-sided limit, where we have this notation of the limit as x approaches some number a, and we'll put a little negative sign like a superscript of f of x. And when we see that negative sign means I'm only interested in coming from the left side, coming from where all the negatives are on the left side of the graph. Versus if I want the limit as x approaches a with a little positive subscript, that positive superscript means I only want to come from the right side. So for example, if I have a graph like this, let's say comes down kind of like x squared up until we have a gap at 1, an empty hole at 1, and it's going to drop down to -2 and become a straight line from there. So now I can ask, what is the limit as x approaches 1? Even though it approaches two different values at 1, if I put a little negative superscript, that means I'm only interested in coming in from the left side. And so when I come in from the left side, we see it's approaching +1, which is different than if I asked for the limit as x approaches 1 from the right side of the function. Coming in from the right side of the function, it's going down here to a y value of -2. So now we can calculate the limits if we specify if we're coming from the left or the right side. Notice, however, we still cannot say the limit as x approaches 1 because these are not approaching the same value. From one side it's 1, from the other side it's -2. It does not exist. In fact, it only exists if the left and right are the same. Now, if they happen to both be the same, that's great. Then it exists. But if they're not the same, then it's not going to work. Let's look at the idea of one-sided limits, not with the graph method, but with the table method that we did at the beginning of this lecture. Number 2. Let's make what's called a piecewise function. If f of x is equal to, and it's got two parts, it's equal to x minus 2 if x is less than 1, and it's equal to x squared plus 1 if x is greater than or equal to 1. So just like before, it's got one part on the left and one part on the right. We use one equation for small values of x. We use another equation for bigger values of x. So we're going to use a table to find three things. The limit as x goes to 1 from the left of f of x. The limit as x goes to 1 from the right of f of x. And then we're going to use that to decide if the limit as x goes to 1 of f of x actually exists. And if it exists, What is that number? So let's start with the table on the left side. We're going to look at values of x from the left of 1, which means we want to be a little bit less than 1, so maybe 0.9, getting closer 0.99, getting closer 0.999, and then even closer 0.9999 to see what the f of x equals. So on our calculator, we'll hit y equals, and clear out the old equation. When we're on the left, we're smaller than 1. So smaller than 1 is going to be x minus 2, because x is smaller than 1. And we'll hit second table, delete out the old values, because those aren't doing us any good. The new values are 0.9, 0.99, 0.999, and 0.499999. And what we see is essentially what we're ending up with is negative 1.1, negative 1.01, negative 1.001, and ultimately pretty much negative 1 when we round it off. So what that tells me then is that the limit as x approaches 1 from the left, using numbers slightly smaller, of f of x, we're approaching or getting closer to negative 1. Now let's look at the right side. Using x values to the right, slightly higher than 1, we might start with 1.1, 1.01, 1.001, and 1.0001. And we're going to see what happens to f of x. The key here now is I have to go to y equals and delete out my old function, or clear out my old function. Because now that x is bigger than 1, we have to use the other equation, the second equation, which is x squared plus 1. And when we hit second table and clear out the old values, our new values are 1.1, 1.01, 1.001, and 1.0001. And we see a definite pattern emerging as we fill in our f of x column. That was 2.21, 2.0201, 2.002, and 2.0002. But we see those are definitely approaching a clear number. So we can announce that the limit as x approaches 1 from the right of f of x using slightly bigger numbers, we're getting closer and closer to 2. So what does it all mean about the limit as x approaches 1 of f of x overall? Well, because the left and right are approaching different numbers, one's approaching negative 1 and one's approaching positive 2, these are not the same, so the limit does not exist purely at 1. Now, there is another case that I want to look at of what can happen as you're trying to make your table. I think we're up to E now. What I'm going to call infinite limits. For example, if I take the limit as x approaches 3, we'll go from the left this time, of 1 over x minus 3. Didn't need to be in parentheses, but it will be in parentheses for our calculator anyways. So we're going to look at values for x and see how our f of x compares. I said only on the left, so we need a little bit smaller than 3. We'll start at 2.9, then we'll try 2.99, 2.999, and 2.9999 to get us really, really close. Hit y equals. Clear out the function 1 divided by, in parentheses, so we don't lose our order of operations, x minus 3. Close the parentheses. And then we'll head to our table, second table. Clear out these numbers because we're interested in 2.9, 2.99, 2.999, and 2.9999. And there's a clear pattern here. We go from negative 10 to negative 100 to negative 1,000 to negative 10,000. So when we're trying to calculate the limit as x goes to 3 from the left of 1 over x minus 3, we see it's not necessarily approaching any one number, but it's definitely going somewhere specifically. It's getting bigger and bigger, or more and more negative would be a better way to say it. So what I'm going to say is this is actually going to negative infinity, because as I get closer and closer to 3, I'm going to get a more and more negative number. In fact, a similar thing happens if we go to the other side of the function. Let's take the limit as x goes to 3 from the right of 1 over x minus 3. And look at various values for x and how f of x compares. From the right, we need to be slightly bigger than 3, so we'll start at 3.1, get a little closer, 3.01, closer 3.001, and closer 3.0001. And let's see how this compares on our calculator. Same function, so I don't have to type it in again. But for my x values, we're going from 3.1 to 3.01 to 3.001. Whoops, got an extra 0. 3.001. And then finally 3.0001. And we see the exact same pattern starting to happen here. We've got 10, 100, 1,000, and 10,000. The only difference is now the graph is not negative. Instead, it's positive. So the limit as x goes to 3 from the right of 1 over x minus 3, it's getting bigger and bigger and positive. So we will say it's going to positive infinity. So our limits can actually be infinite, positive or negative infinity, if it truly is getting bigger and bigger, or negative bigger and bigger without bound. And what this actually means about the graph, this means the graph has a vertical asymptote. At 3. Or x equals 3 would be a better way to say it. In other words, if I were to sketch a graph of this guy really quick, and I'll just make a small version of it, 1, 2, 3. At 3, there's going to be a vertical asymptote. And the graph is going to bend around that vertical asymptote. And so you see when we're approaching from the left, it's going down to negative infinity. And when we're approaching 3 from the right, it goes to positive infinity. Before we wrap up here, let's do one more problem where we just find a bunch of limits just to practice. So I'm going to draw a graph on here. We're going to go 4 each direction. And at negative 3, comma 3, we're going to put a point. And from that point, it's going to curve up to the left. We're also at negative 3, 2, going to put an open point. Then at negative 1, comma 4, we're going to put an open point. And then at 2, we're going to put a vertical asymptote. So we're going to connect the open point to open point is the maximum, and then come down to the asymptote. And then at 3, comma 2, we'll put another point and kind of bring the graph down and into that point. I want to put one more point on this graph at negative 1, comma 1. We have that open dot at negative 1. The close point means where the point actually is. Might not be where it's supposed to be, but that's where it actually is. So I've got 9 of these I want to see if we can calculate. First, we're going to find the limit as x approaches negative 1 of f of x. Now at negative 1, what is the graph getting close to? Not where the graph is actually. You'll see from the left and the right, the graph is getting closer and closer to a height of 4. So we say the limit at negative 1 is 4, because that's what should be there, even if it's not. Notice that's different than asking what is f at negative 1. Where is f actually at negative 1? And at negative 1, on the curve, there's a hole at negative 1. The actual negative 1 point is at a height of 1. How about this one? The limit as x approaches negative 3 from the left of f of x. Well, at negative 3 from the left, we see this graph is approaching a height of 3. We can compare that with the limit as x approaches negative 3 from the right of f of x. When we come from the right, or the positive side, notice it comes down a bit lower to a height of 2. So the limit there is approaching 2. Which means if I asked what the limit as x approaches negative 3 of f of x is, we can see already from the left and the right we're approaching 2 different values. They're not the same. Because they're not the same, this limit does not exist. It must be the same to exist. How about the limit as x approaches 2 from the left of f of x? As we get closer from the left side to 2, notice this graph is going down to a vertical asymptote. Because we're going down all the way, this is actually equal to negative infinity. It goes down all the way to infinity before it actually gets to 2, because it will never touch that vertical asymptote. Similarly, the limit as x approaches 2 from the right of f of x, looking at the right side, we see the graph is going up, up and up and up, without bound or stopping. It's going to be equal to positive infinity. What's the limit as x approaches 3 of f of x? Now 3 is right where this point is on the right side. And notice when we come in from the left or the right, it's going to that same height of 2. So we'll say the limit is approaching 2. And what you might also notice is the point that should be there actually is there. So we can also say that f of 3 is also equal to 2. And so when the limit and the point are equal to each other, that's significant to us. We say that means the graph is continuous. at that point because the limit and the point are the same. But we're going to spend a whole day on continuity a little bit later. Right now, what's important is that you get very comfortable finding limits both from the graph method and also from the table method. So take a look at some of the assignments in the book. And I look forward to seeing you in class so that we can discuss these limits in more detail. Today we're going to take a look at the question, how can we evaluate limits? In our last lesson, we looked at how we can use a table or a graph to evaluate a limit by getting closer and closer to a specific value. What we're going to do today is take a look at some limit laws that we can use to help us find limits quicker and more accurately. First, there are two basic limit laws. The first is that the limit as x approaches a of x. Since x is a straight line with no holes or gaps or any funny actions happening on the graph, we can say that that limit is going to equal whatever number we're checking on the graph. The second limit is as x approaches a of some constant, where c is just any number, but there's no x's in there, then that is going to always approach that constant, or c. These two are our basic limit laws, and important that we should be very comfortable calculating those limits as soon as we see them. So for example, if I ask what is the limit as x goes to -4 of x, we should know right away that's going to equal the number, or the -4. Similarly, if I want to know what the limit is as x approaches 7 of 2, 2 is just a number, or a constant. This function is always equal to 2 regardless of what x is. So even at 7, x is still, or the function is still equal to 2. In addition to the basic limit laws, there are 6 other properties of limits, or limit laws, that we should be comfortable working with. We'll list all 6 here, and then we'll look at some examples of how these limit laws can be worked out. First is the sum or difference, as they both work the same. And the idea here is if we take the limit as x approaches some number a of 2 parts that are added together, maybe f of x plus g of x, that is actually the same as if we took the limits of the 2 parts individually, the limit as x approaches a of the f of x, and added the limit as x approaches a of g of x. If we take the 2 parts individually, we'll get the same result. And it works for subtraction also. So I'm going to change this to plus or minus. The next limit law is what we call the constant multiplier. Where we're going to take the limit as x approaches a of some constant times something with x in it. The way we can work here is that constant actually is multiplied by whatever the limit as x approaches a of that function actually is. We also have the product rule, which says if I want the limit as x approaches a of f of x times g of x, 2 things multiplied together, we can actually take the limits of the 2 parts, the limit as x approaches a of the first part, times the limit as x approaches a of the second part, or the g of x. Same idea works for a quotient. because really multiplication and division are just inverse reciprocals of each other. So limit as x approaches a of f of x divided by g of x, that is equal to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. We also have what's called the power rule. The power rule says if I'm interested in finding the limit as x approaches a of some function that is raised to some type of exponent, we can find the limit first and then raise the answer to some exponent. And because exponents and radicals are really the same thing, we can extend this to number 6, what we call the radical rule, which is that the limit as x approaches a of the square root of some function is equal to the square root of the limit. So I'm going to highlight all 6 of these limit laws as important limit laws that we know and understand. But this is a case, as is often the case with calculus, is it's more important that we understand how to use the 6 rules than it is that we can actually quote the 6 rules from memory. Because if we understand the process of what we're doing, we just have to straight out solve the problems instead of going through memorizing a whole bunch of formulas, which should not be the goal in any calculus class. Basically, what we're saying here is that we can take the limits of the pieces we can, and we can add and subtract them. We've got constant multipliers. Limit pieces can be multiplied, divided, exponents, radicals. We can just take the limits of the individual pieces. Maybe it's easier to explain with some examples. If we want the limit as x approaches 2 of x squared minus 3x plus 4, we know from our limit laws that this added and subtracted can be broken into 3 pieces. We also know that the exponents and constants can be pulled outside of the limit. So what this really means we can do is we can take the limit as x approaches 2 of the x, and then square it, minus 3 times the limit as x approaches 2 of the x, and add 4. Actually, add the limit as x approaches 2 of the 4. Now we have the 2 basic limit laws that says the limit of x is the number, and that the limit of a constant is equal to the constant. And so if we plug that in, the limit as x approaches 2 of x becomes 2 squared minus 3 times the limit as x approaches 2 of x is just 2 plus 4. And I can plug this into my calculator, and we'll end up with 2. Let's try another one. The limit as x approaches negative 1 of the square root of x plus 5. Again, limits go through exponents, radicals, pluses, minuses, fractions. So what we really can say is this is the square root of the limit as x goes to negative 1 of x plus the limit as x goes to negative 1 of 5. And we know the limit of x is the number. The limit of a constant is the constant. So this is the square root of negative 1 plus 5, which is the square root of 4, or also 2. What you might notice here is instead of doing all the work of putting that limit through all the pieces, what we're really doing is, whenever possible, we're taking the number we're working with and plugging it in to the x. In summary, what we're really doing is what's called direct substitution. In other words, if I had an example like the limit as x approaches 1 of x squared minus 4 over x squared plus 2x plus 1, what that really means is we can put the 1 in for the x to see what's happening around 1. If I put the 1 in, we get 1 squared minus 4 over 1 squared plus 2 times 1 plus 1. 1 minus 4 is negative 3, and 1 plus 2 plus 1 is 4. And so the limit as x approaches 1 is negative 3/4. So in summary, the easiest way we can calculate a limit is to directly plug that number into the function. However, that doesn't always work perfectly. And so we've got a couple techniques to handle what we do if direct substitution doesn't quite work. So let's call this additional techniques. That we will use when substitution does not work. So first, we're going to find the limit as x approaches negative 3 of x squared plus 4x plus 3 over 2x squared plus 5x minus 3. Now, what I want to notice is when we plug negative 3 in, especially interested in the denominator, we get 2 times 9 minus 15 minus 3, which is 0. So what we're noticing is substitution divides by 0. We can't divide by 0. We can't have 0 in the denominator. So we need an additional technique. Our additional technique is going to be to factor and reduce. Hopefully, when we do this, we'll be able to actually take the limit through direct substitution. So we're going to take the limit as x goes to negative 3. The numerator factors nicely. X squared is x times x. 3 is 3 times 1. Both positive gives us 4x in the middle. In the denominator, 2x squared is 2x times x. 3 is 3 times 1. Is that the right order? 6 and 1. If we do plus 6 and a minus 1, it will work. And what's really nice there is now you see that x plus 3 reduces out. And so we're left with the limit as x goes to negative 3 of x plus 1 over 2x minus 1. Now direct substitution works great, because no longer does our denominator equal 0. We're no longer dividing by 0. Instead, we have negative 3 plus 1 over 2 times negative 3 minus 1, which is negative 2 over negative 7. And a negative divided by a negative is a positive. So for our final answer, this limit equals 2/7. So our first technique, if we're dividing by 0, we can factor and hopefully reduce out the part that equals 0. Here's a second problem. The limit as x goes to 8 of the square root of x plus 1 minus 3 over x minus 8. Again, we have the same note. If we substitute in the denominator, 8 minus 8 will be 0. So substitution divides by 0. We can't do that. So we need another trick. This time we can't factor because there's a radical in there. However, there's a trick that we use with radicals. If radicals are getting inconvenient, we'll get rid of the radicals by multiplying by the conjugate. This is similar to what we did in pre-calculus and algebra. When we were rationalizing the denominator, we multiplied by the conjugate. This time we're going to rationalize the numerator and see if that helps us. So we'll change the sign in the middle. Everything else is the same. The square root of x plus 1 and 3 is the same. But instead of subtracting, we're going to add in the numerator and the denominator. When we do that, the numerator becomes nice. Limit as x goes to 8 still. Because these are conjugates, a sum and a difference, the first part is squared. And when we square a square root, we just get the inside stuff, x plus 1. Then it's always a minus, and then we square the last part. 3 squared is 9. Over, let's keep the denominator factored. X minus 8 times the square root of x plus 1 plus 3. Well, that's nice because in the numerator we can simplify. And notice 1 minus 9 is x minus 8. We still have the same denominator. Don't need to multiply that out because we want to stay factored so we can divide out that x minus 8. Remember, if everything divides out, there's still a 1 up there. That doesn't disappear. And so now we're taking the limit as x goes to 8 of 1 over the square root of x plus 1 plus 3. Now we can plug our number in because the denominator no longer will equal 0. We have 1 over the square root, plugging 8 in, 8 plus 1 plus 3 equals 1 over the square root of 9 is 3, plus 3 is 6. And we now know our limit is 1/6. Another example. Let's find the limit as x approaches 3 of 1 over x plus 2 minus 1 over 5 all over x minus 3. Again, we have the same note, the same problem. Substitution means we're dividing by 0. We can't divide by 0. However, we've dealt with complex fractions, fractions and fractions before. We multiply top and bottom by the least common denominator, which in this case is a 5 and an x plus 2. So we'll multiply by 5x plus 2 and just distribute it through 5x plus 2, and the denominator also by 5x plus 2. When we do that, the x plus 2's and the 5's divide out. Be careful with the negative. It's going to have to distribute through the parentheses. Don't get in trouble with that negative. Let me get us some more whiteboard space. So now we have the limit as x goes to 3 of 5 minus x minus 2, distributing the negative all the way through, all over x minus 3 times 5 times x plus 2. Clean up by combining like terms in the numerator. The limit as x goes to 3 of 3 minus x over x minus 3 times 5 times x plus 2. We've got our subtraction backwards with the 3 minus x and the x minus 3. But that's OK, because if we remember from pre-calc, those can reduce out if there's a negative 1 left behind. The negative 1 swaps the order of the subtraction. So now we have the limit as x goes to 3 of negative 1 over 5 times x plus 2. Now we can do direct substitution, because no longer are we dividing by 0. So negative 1 over 5 times 3 plus 2, which is negative 1 over 5 times 5, or 25. So there's 3 tricks here, and these 3 tricks are going to come back again when we're talking about derivatives. So it's good to take a moment to go over what we just did. The first trick we did is we can find a limit by factoring and reducing. We also can get rid of radicals by multiplying by conjugates. And we also can get rid of complex fractions by multiplying top and bottom by the LCD. 3 tricks that are going to be very useful to us so that we can use that direct substitution in order to find a limit. While we're talking about finding limits, though, I want to go back to the discussion we had about the two-sided limits and how we can handle those. If you remember in our previous lesson, we talked about coming in from the left and coming in from the right. Well, for a two-sided limits, the left and the right must be equal. So if we're working with a piecewise function, like f of x is equal to x plus 3 if x is greater than negative 3, and it's equal to x squared if x is less than or equal to negative 3, we need to consider at negative 3 what's happening on the left and the right. So first, let's look at the limit as x approaches negative 3 from the left of f of x. From the left, we're dealing with smaller values of negative 3. Smaller values less than or equal to 3 is x squared. So we'll directly plug in the negative 3 into the x squared, or negative 3 squared, which is 9. Let's compare that with the limit as x approaches negative 3 from the right of f of x. Coming from the right, we're talking about bigger values, or x is greater than negative 3. So that's the x plus 3. Direct substitution. Negative 3 plus 3 is equal to 0. And what you'll notice is those two limits are not the same. So what does that mean about the limit as x approaches 3 of f of x? Well, we know it does not exist. Let's do one more example of a two-sided limit with a piecewise function. Let's look at f of x equals 2x if x is less than 2, and x squared if x is greater than or equal to 2. So what's the limit at 2? Well, we got to come in from each side. The limit as x approaches 2 from the left of f of x. From the left, those are the smaller values where x is less than 2. So let's plug in 2. 2 times 2 is equal to 4. Looking at the other side, the limit as x approaches 2 from the right of f of x. Coming from the right means we want bigger values, or when x is greater than or equal to 2. So we'll plug it into x squared. 2 squared is equal to 4. This time, you notice we have the same value for both the left and the right-sided limits. When we have the same value, then we can say the limit as x approaches 2 of f of x still does exist. In fact, that limit is 4, whatever is the same on both the left and the right side. So the important thing with piecewise functions is we have to be equal to the same number on both sides of the function. With our limit discussion, we talked a bit about infinite limits. So let's look at how we can work with infinite limits, calculating them with this whole idea of substitution. With infinite limits, there are two properties that will help us calculate the infinite limits. First property is that the limit as x approaches a from the left of 1 over x minus a. If we're coming in from the left on this guy, this function will always go to negative infinity. Because all the pieces are positive, it's going to go down to negative infinity. Similarly, as x approaches a from the right of 1 over x minus a, coming in from the right, we're going to go up to positive infinity. These two limits are going to be the key to finding infinite limits by hand rather than going through the table method or the graph method. Let's first look at the limit as x approaches 2 from the left of x plus 1 over x squared minus 4. We can't directly plug 2 in because it makes it undefined, so we would start to factor to see if that helps us, to see if we can remove the discontinuity. So x plus 1 over x squared minus 4 is x plus 2 times x minus 2. But the frustrating part there is that x minus 2 doesn't divide out. So we can't divide out the bad part. So what we'll do is we'll isolate the bad part in a separate fraction, 1 over the bad part. This is going to give us the limit as x approaches 2 from the left of x plus 1 over x plus 2 times 1 over x minus 2. Now we can do direct substitution on the good part. And for the bad part that's been isolated, we're coming in from the left. And we know when we come in from the left, that's going to go to a negative infinity. So let's look at each of these pieces. Plugging 2 in, we've got 2 plus 1 over 2 plus 2 times the negative infinity. Well, 2 plus 1 is 3. 2 plus 2 is 4 times the negative infinity. The answer here is going to be infinity, but what we have to decide is we've got a positive times a negative is going to equal a negative. And so we end up with this function going out to negative infinity. Let's do that one more time where we isolate the bad part. Let's come in from the other direction. Let's take the limit as x goes to 2 from the right of the x plus 1 over x squared minus 4. And again, we start out the same as x going to 2 from the right by factoring the denominator to x plus 2, x minus 2, and then isolating the bad part as a fraction, 1 over that. And so we end up with the limit as x goes to 2 from the right of x plus 1 over x plus 2 times the bad part of 1 over x minus 2. This time we're going in from the plus or positive side. That's the second property. That's now going to go to a positive infinity. So when we make our substitution step, we're going to plug positive infinity in for that second part. Plugging 2 in, we have 2 plus 1 over 2 plus 2 times positive infinity, which is 3/4 times positive infinity. A positive times a positive is positive. This graph's going to positive infinity from the right. I have one more limit trick that I want to look at. We call this guy the squeeze theorem. And it's particularly useful to find limits with trig properties. The idea with the squeeze theorem is if I've got some function and I don't know what the limit is, but I can find a function that goes above it and a function that goes below it so that they all meet in the center at the same exact point. So we've got one that's always above, one that's always below, but they all meet together in the same point. At that same point, they will all have the same limit if they all meet at the same point. My picture doesn't show them meeting at the same point really well, but the idea is the top one, the bottom one, and the middle function all converge together at that same point in the center. Then they all have the same exact limit. So let me show you what this looks like. Let's say we want to know the limit as x goes to 0 of x squared times the cosine of x. We don't have a limit rule yet that says we can just plug the number into the cosine, just into polynomials, into fractions, into multiplication, into radicals, but not into cosine. So we need to use the squeeze theorem to get at it. And how the squeeze theorem works is we're going to look particularly at the cosine and say one thing we know about the cosine, not the sine, the cosine. The cosine of x has a very bounded domain. It's always between a -1 and a +1. Same thing for the sine. So what we want to do is manipulate this inequality so that it looks like the entire function, x squared times the cosine. Well, the center is just missing a multiply by x squared. So if we do that on all three parts, we end up with negative x squared is less than or equal to x squared cosine x, which is less than or equal to x squared. We can take the limit of each of these parts, the limit as x goes to 0 of negative x squared is less than or equal to the limit as x goes to 0 of x squared cosine x, which is less than or equal to the limit as x goes to 0 of x squared. And what's nice about this is the left and the right we can do direct substitution on. If I plug in 0, we get negative 0 squared, which is just 0, is less than or equal to the limit as x goes to 0 of x squared cosine x, which is less than or equal to, here we have a polynomial. Direct substitution, we plug 0 in. 0 squared is just 0. So if the limit is less than 0 and greater than 0 or equal to, it must be equal to 0. So the limit as x goes to 0 of x squared cosine x is equal to 0, because it's been squeezed in between these other two functions that both go to 0. They all are at the same point. They all have the same limit. One is always below, and one is always above. So that wraps up our discussion of all of the limit tricks. The basic idea is direct substitution. We want to plug the number that we have for the limit into the function and simplify. We have a couple tricks we did if that doesn't work to get it to a point that it does work. But ultimately, if we can plug the number in, it's very easy to take the limit. Working with limits leads us directly into an important conversation around the topic of continuity. So we're going to answer the question, when is a function continuous? Well, in order to determine when the function is or is not continuous, we need to know what continuous means. First, kind of an informal definition. The idea of continuous means basically I can draw the graph without lifting my pencil. It's just a continuous curve without lifting the pencil for a gap or a jump or an asymptote. It's just continuous. Now, a more formal mathematical definition states that a continuous function will satisfy three conditions for all points. And we'll call those points A. The first condition is that f of A is defined. So the function can't be undefined at the given point. In addition, we need the limit as x approaches A of f of x to exist. So for example, if the function's approaching two different numbers from two different sides, the limit does not exist. But the all-important one that we probably go to check the most for continuity is that the limit as x approaches A of f of x is actually equal to whatever f of A is. In other words, we can do the direct substitution to calculate the limit because the limit is equal to the point itself. These three definitions, and specifically this last one being the most important, are what makes a function continuous. So what does it mean to be discontinuous or not a continuous function? Well, there are actually three types of discontinuity, which means not continuous. The first type of discontinuity is what we call a removable discontinuity. And here's what a removable discontinuity looks like. It's something like f of x equals x squared plus x minus 12 over x minus 3. Notice if we tried to calculate f of 3, or just directly substitute the 3 in, we would get 3 squared plus 3 minus 12, which is 0, divided by the important part, 3 minus 3 is 0. And we can't divide by 0. So f of x, or f of a, f of 3, is undefined. However, if I took my function and I factored it, we'd get, what, 4 and 3? It's plus 4 and minus 3 over x minus 3. We can then divide out the x minus 3. And we've removed the discontinuity, or the problem. Now, because we've been able to remove the discontinuity, we could calculate the limit. So this is a removable discontinuity because we were able to algebraically remove the part that was discontinuous. Now, the way this looks on a graph, and we'll go ahead and just graph this same function. Not to scale here, so we'll come up and call this 4 here. But the idea is this graph's going to go through 4, and it's going to have a hole that's been removed right at 3 that it goes around. We can't graph this without lifting our pencil, because we have to lift our pencil at the hole in the graph. So we could say that the hole in the graph is removable. It is a removable discontinuity. The first type of discontinuity. The second type of discontinuity that we're going to look at is called an infinite discontinuity. And the example we're going to use here is f of x is equal to x minus 3 over x plus 1. We would end up with a vertical asymptote at 1. And there's actually also a horizontal asymptote at 1, so this graph looks like this. No, it doesn't. It looks like this. But specifically, what we find is the infinite discontinuity. So that is our second type of discontinuity. The third type of discontinuity is what we call a jump discontinuity. And it does exactly what you'd expect the graph to do. It jumps. So if we have f of x equals the piecewise function x squared minus 1 for x less than 1, and x plus 1 for x greater than or equal to 1, what we're going to find is the limit, again, is not going to exist. Because if we take the limit as x goes to 1 from the left, or smaller values, we use the first equation. So we'll directly substitute 1 into x squared minus 1. And we get 1 squared minus 1, which is 0. And we compare that to the limit coming in from the right of 1. Well, coming in from the right, we want the bigger values. So we'll plug it into x plus 1, or 1 plus 1, which is 2. And because these are not the same, we have a jump in the graph. And the limit, as x approaches 1, again, does not exist. What does this look like as a graph? Just like you'd expect it to. It's x squared minus 1. So it's going to come, whoops, different color. The graph's going to come down. And then we've got a jump at 1. And then it turns into the line. But specifically, what we're interested in is the graph jumps. So again, the whole idea of discontinuity versus continuity is, can you draw the graph without lifting your pencil? Specifically, does the function at a equal the limit as x approaches a? Kind of a corollary that comes out of this idea of continuity is this idea of what we call the intermediate value theorem, which is often abbreviated with the first letters IVT, intermediate value theorem. And what the intermediate value theorem says is that if a function f of x is continuous, if the function always equals its limit on some interval from a to b, and there's another number z that's between f of a and f of b, then there exists another number, we'll call it c, that is in AB such that f of c will equal that z. OK, that definition's really weird. Let's draw a picture that really illustrates what this means. I've got a graph. We're going to go from A to C, A to B, sorry. So the graph goes from A to B. Let's say A is down low, B is up high, and it might do something interesting and crazy, but it's continuous, so I can draw it without lifting my pencil and go all the way from A to B. Well, A hits at f of A, and B hits up on top at f of b. The idea of the intermediate value theorem is I can pick any z that is between f of a and f of b. Any z I want. And wherever I pick that z, there is a guarantee that there will be a solution, some c, that will get me that solution. In fact, there could be more than one solution. If I pick a z kind of down towards the center, you see there's 3 solutions in there. But there's always at least one solution for any z that's in the middle of those. Basically, we're going to hit every single value all the way up from f of a to f of b, because there's no other way to connect the dots. Now, there's a couple cautions about what this theorem actually says. So before we get to an example of how to use it, I want to make sure we clearly understand what this is actually saying. First, the definition started out that if f is continuous. This does not work if f is not continuous. But it could. We just don't have the guarantee that we get from continuity. So drawing a picture of what I mean by that. Here we've got A, here we've got B. So there's a point at A and there's a point at B. So we've got f of B and f of A. The intermediate value theorem says that I can pick any z in between f of A and f of B, as long as it's continuous. But if this function just kind of goes like this, and then there's a jump discontinuity, and it goes like that, notice if I pick a z right in the middle of that jump discontinuity, I do not get a solution. I could if I picked a z up high enough that it actually hit the graph. I could get a result, but I'm not guaranteed a result because of that jump discontinuity. So it does not work if f is not continuous. The other important thing is it does not work if z is outside of f of A and f of B. But it could. Again, it could work. We just don't have that guarantee. So again, we're going to go from A to B. A's here, B's here, which means f of A is at the lower point where A is, f of B at the higher point. And if f of A is connected somehow, but my z is too low or too high, I'm not guaranteed that it's going to work, that I'm going to cross the graph. It doesn't necessarily mean no, though, because if the graph did go up and down and really wiggle, it could go down and hit z. But I don't have any guarantee that it does. So it's really important for the intermediate value theorem that z has to be between the two y values. The one other thing this tells us, this theorem only tells us there is at least one solution. There may or may not be more. And I kind of hinted at this with my original drawing. But again, we've got A and we've got B. Put A down low and B up high. And the graph is going to wiggle. But specifically, f of A aligns with A, and f of B aligns with B. And if I pick z in the middle of this graph, what you'll see is I actually get 1, 2, 3 solutions. So there's actually 3 points that work. That could be our C. We are guaranteed with the intermediate value theorem that there is at least one solution for z. There could be more. but we have no way of knowing if there is or is not more. So that's really what this intermediate value theorem is trying to say, is if f of x is continuous and our z is somewhere between those y values of f of a and f of b, then there exists at least one c such that when we plug c into the function, we get z for a solution. How do we use this? Well, here's how we use this. We use this to show that we do have solutions to functions, even if we can't solve them. We can show that 0 equals 1 over x plus sine x has at least one solution. We know this function is continuous except at 0. So we're going to stay away from 0 so that we're continuous between our a and our b. In order to show that it has one solution, what we're going to attempt to do, a solution happens at 0, it says. What we're going to attempt to do is find the point where the graph crosses 0. Notice before 0, the graph is negative. After 0, this graph is positive. 0 is going to be between negative and positive. So if I can show that there is a solution that's negative, and that this guy has a solution that's positive, everything between it, including 0, must exist. Well, one thing we know about sine is, where is sine positive? We're going to add sine of x. Well, sine is the y-coordinate on the unit circle. So if I imagine my unit circle, the y-coordinate is positive. So let's make a note of what we're doing here. We need to find a negative and positive solution. Or better than saying solution, let's say output for f of x. And then 0 between it must exist as an output. So on the unit circle, sine is the y-coordinate. The y-coordinate, I notice, is very positive up here on top. That's at pi over 2. And it's also very negative down here at the bottom at 3 pi over 2. Let's see what those give us when we plug them in. So let's find f of pi over 2, which is equal to 1 over pi over 2, plus the sine of pi over 2. 1 over pi over 2, that's the reciprocal, so we have 2 over pi, plus the sine of pi over 2 is 1. That's definitely positive. Actually, if I put it in my calculator, I get 1.64 or so. Then the other point, to try and get negative, we said the most negative point for sine is at 3 pi over 2. So let's see what that gives us. 1 over 3 pi over 2 plus the sine of 3 pi over 2 is equal to, well, the reciprocal of 3 pi over 2 is 2 over 3 pi. plus the sine of 3 pi over 2 is -1. And sure enough, that's negative 0.788. Therefore, by the way, these three triangles, these three dots in a triangle, that means therefore. It's a nice shorthand for mathematicians. Therefore, we know that all outputs between 1.64 and negative 0.788 are possible. Specifically, they're possible when x is between 3 pi over 2 and pi over 2. Therefore, 0, which is between those values, is a solution. So the intermediate value theorem tells us that there has to be a result, an output, between 1.64 and negative 0.788. 0's between there, therefore 0 is a solution. That's a quick look at continuity and the intermediate value theorem. Take a look at some of the problems in your book to practice this a bit, but I'll look forward to seeing you in class so we can talk about continuity a little bit more. Thus far in our studies of limit, we have kind of been waving our hands over the definition of a limit and talking more generally about the definition rather than the precise definition. So that's what we're going to take a look at today. The question is, what is the precise definition of a limit? So first, we're going to look at the definition. And then we'll take a look at kind of the meat of this lesson, which is how do we show that a value actually is the limit of some type of function. So first, graphically, to get an idea of what we're going to be talking about here, let's say we've got some graph. Maybe it curves up like this. And we want to know what is the limit of f of x as x approaches some number. Actually, let's call it a, not c. As x approaches a of f of x. Well, the way we actually define the derivative is we're going to say we're going to move from a out a little bit each direction. Because remember, our limit, we need both sides. That little tiny change that we move, we call delta. So we add delta and we subtract delta to get to 2 more spots. And the idea is if I go up to the point on the graph, what I can do is I can box in the actual point on the graph within that range. So the point on the graph in green here where a actually hits, or where a should be, it might not actually be there, we're going to call that L, the limit. And the idea is that the deltas will box it in within some epsilon above or epsilon below. The challenge that we're going to have is to find the connection between the delta that we move left and right on the bottom and the epsilon that we move up and down from the right. And so the idea is if we zoom in and zoom in and zoom in and get closer and closer to the actual point, we'll continue to be boxed in around some epsilon. That box is what allows us to not actually have a point there, because we just have to be around the point. Basically infinitely close to the point, but not actually at the point. What are we at? So for every epsilon, we need to be able to find a delta. And this is what gives rise to, in words, the precise definition for the limit. We say that for all epsilon, that's a Greek letter epsilon, greater than 0, that there exists a delta greater than 0, another Greek letter, such that if the absolute value of x minus a is less than delta, remember a is that x coordinate that we want to find the limit at, then the absolute value, we do absolute value because we can do plus or minus, the absolute value of f of x minus L is less than epsilon. In other words, on the right side, we're within an epsilon of the actual limit. Now, because mathematicians like to show off and make things more complicated than they really are, we actually can represent this entire definition symbolically. So this is a neat party trick, is to just be able to write down really quick the precise definition of a limit without writing a single word. So here is symbolically the precise definition of a limit. This is a thing of beauty. The limit as x approaches a of f of x equals L implies that for all epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of x minus a is less than delta, implies that the absolute value of f of x minus the limit is less than epsilon. So a great party trick is the precise definition of a limit. I enjoy putting this on the test for extra credit, but it is quite fancy looking. So what we really want to be able to do with this definition, though, is actually be able to take a limit and say, hey, if this is the limit, I can prove it's actually the limit by identifying this relationship between epsilon and delta. We call these our epsilon delta proofs, and every single proof looks identical. And so to help you set up your proofs, I'm going to show you the structure of the proof that the limit as x approaches a of f of x equals L. You're going to do 4 steps, and 3 of the 4 steps are really scripted, and the 4th one is just a little bit of algebra that's actually quite easy. The first step is you're always going to say we let epsilon be greater than 0. That has to be true. And that's always the same, every proof. Let epsilon be greater than 0. Then you'll say choose a delta that is equal to something. And actually, we're going to find this later. And I should do that in a different color because it's not actually part of the proof. But usually that something is going to have the epsilon in it because it's going to show the relationship between epsilon and delta. So just leave it blank temporarily, because the next thing you do is you assume the absolute value of x minus a is less than the delta. And then you say the absolute value of f of x minus the limit is equal to, and then you do some algebra. And after some algebra, you're going to ultimately say that's less than something, which is going to require you to do some more algebra. And that will ultimately equal epsilon. Move that arrow so it's a little nicer. Maybe make it blue. So every single proof is going to look exactly the same. The only place where you actually have to do any work is in this dot, dot, dot. And while you do that dot, dot, dot of algebra, it's going to tell you what you're ultimately going to put in back in step number 2 for that delta. And actually, steps 1, 2, and 3 we usually throw out on one line because they are so straightforward. So let's do a couple examples. I've got 4 examples of proofs, and then you can practice some on your own. First, let's do some linear examples. And just kind of as a tip, if we're dealing with a linear equation like y equals mx plus b, with linear examples, the delta is generally equal to epsilon divided by something. And you have to figure out what that something is. So following that same structure, first we're going to prove that the limit as x approaches 3 of 4x minus 7 equals 5. Notice that 3 is the a, what x is approaching. 5 is the limit, or L. And the 4x minus 7, that's the function. So here's our proof. We always say, let epsilon be greater than 0. Choose a delta that's equal to something. We'll leave that blank. And then we will assume the absolute value of x minus a is what the limit is approaching, is less than delta. That part's really scripted. The only gap is we don't know what delta equals yet. We're going to go back and fill that in a minute. Now we're going to take the absolute value of f of x minus L. Well, let's put f of x in there, actually. F of x is the function, 4x minus 7, and then subtract the limit, which is 5. And now we're going to play with this and do some algebra. What you might see immediately is we can combine like terms on the 7 and the 5. So we have the absolute value of 4x minus 12. And then what we ultimately want to do is we want to find some absolute value of x minus 3 so we can use what we assumed. And what you might see here is all we have to do is factor out the 4, and we get the absolute value of x minus 3. We know that the absolute value of x minus 3 is less than delta, so we're ready to do our less than statement. It's less than 4 times the absolute value, which is less than delta. This is where we know now what we want epsilon to be, or what we want delta to be. Because what we ultimately want to do is when we multiply by 4, all that's left is epsilon. So delta then is going to be the reciprocal of what we're multiplying by. The reciprocal of 4 is 1 over 4. So delta is equal to epsilon over 4. And we stick that into the first line. That might not be very clear, but it becomes clear why that's useful in the very next step. Because now we have 4 times delta is equal to epsilon over 4. And now the 4's divide out, leaving just the epsilon. And if we're able to simplify the f of x minus L and say it is less than epsilon, we have proven that this limit is actually equal to what we said it was equal to. When we're done with a proof, there's a couple ways we show that we're done in mathematics. The most common way is we write at the end QED. That's Latin for quod eram demonstratum. That was what we wished to show. Another thing I see a lot of times is people put a little box and color it in as if to check off that it's done. Another thing I've seen is W to the 5th, which stands for which was what we wanted. Somehow acknowledge, though, that you've gotten to the end of the proof. QED is really nice because it looks like you know Latin and it looks smart. Let's do one more linear example so that we can see kind of how another similar problem works. But every problem kind of has the same general setup. For this example, we're going to prove that the limit as x goes to -1 of x squared plus 4x plus 3 over x plus 1 is equal to 2. And like before, identifying the pieces, what x is approaching, that's my a. What's inside the limit, that's the function. And the answer, that's my limit L. The first line is pretty scripted of every delta epsilon proof. We let epsilon be greater than 0. We choose a delta that's equal to something. Leave some space. We'll come back. It's going to be the reciprocal of whatever we're multiplying delta by with an epsilon in the numerator. And then we will assume the absolute value of x minus a, which is -1, minus a -1 is the same as +1, is less than delta. Now the next line is where we do our algebra. We take the absolute value of the function, which is x squared plus 4x plus 3 over x plus 1, and subtract the limit of 2. And hopefully, after massaging it a bit, we end up saying this is less than epsilon. Well, with rational expressions, we're really comfortable with factoring to reduce. So when we factor, we get x plus 3 times x plus 1 over the x plus 1, and we still have the minus 2 at the end. But this is really nice because the x plus 1's divide out, which leaves us with the absolute value of x plus 3 minus 2. And I'm going to run out of space on my next statement. So let's go ahead and use the next line and say equals the absolute value combining like terms of x plus 1. And this is actually really nice because this already is the part that's less than delta. This time we don't have to factor anything out. Just to keep things consistent, though, I'm going to factor out a 1 and say that's 1 times the absolute value. Because we know that delta has to be the reciprocal of that number times epsilon. Well, the reciprocal of 1 is just 1. So we have epsilon over 1, or just epsilon. Delta equals epsilon. Because now I know that the x plus 1 is less than the delta. That's from my assume statement. X plus 1 is less than the delta. And we know that the delta is equal to the epsilon, which is what we defined at the beginning. And QED, we have proven that this limit equals 2. So with linear examples, our general strategy as we work through the steps is to make delta equal to the reciprocal of whatever is multiplied by delta. But we can also do quadratic examples pretty nicely. So let's do a couple of those quadratic examples. With quadratics, what we're going to have to do is we're going to need a little bit of help to make delta come out right. And so we're going to actually give delta 2 options. Delta is always going to be equal to the minimum of 1 and epsilon divided by something. We need that 1 to kind of set up what the divided by something is, and I'll show you in just a minute. But with quadratics, when you see x squared, delta is going to be the minimum of 1 and the reciprocal, again, of what's being multiplied by delta. So let's see if we can prove that the limit as x approaches 2 of x squared minus 3x is equal to -2. Again, x is approaching our a value. The function is what's inside the limit. And L, the limit, is the answer. And we start filling in our proof structure. First, we let epsilon be greater than 0. Then we choose a delta that's going to be equal to something we don't know yet. But we know with quadratics we have to do the minimum of 1 and something. We don't know what the something is yet. And then we will assume that the absolute value of x minus 2, or our a that x is approaching, is less than delta. Then we go to that absolute value statement. The absolute value of our function, x squared minus 3x, minus the limit. Minus a -2 means plus 2. And hopefully we'll work this down and ultimately say it's less than an epsilon. Well, with quadratics, we're probably very familiar with factoring. With absolute value, we just keep the absolute values around each factor. So x squared is x times x. And if we do a -2 and a -1, we're completely factored. What's nice here is that we've got the x minus 2 that we know is less than delta. So we're going to be able to say this is less than something times delta. But we need to know what to do with the x minus 1 bit. This is where it's going to take a little creativeness. How we're going to get to that creativeness is we're going to play with the algebra on x minus 2 is less than delta, and the fact that we said delta is going to be at most 1. It's the minimum of 1 and something else. Let's see. We're going to play off to the side here. I guess I'll put it underneath. The absolute value of x minus 2 is less than delta. But delta is no bigger than 1. If the absolute value is less than a number, what that really means is that the x minus 2 is between -1 and +1. We want to know what to do with the x minus 1. So we're going to try and change this middle stuff to become x minus 1. To get x minus 2 to become x minus 1, we're going to add 1. Of course, if we add 1 there, we have to add 1 to all 3 parts. And when we do, we get 0 is less than x minus 1, which is less than 2. Now we're going to change this back to an absolute value statement, that the absolute value of x minus 1 is less than something. And we can either say the absolute value is less than 0 or less than 2. We always will take the most extreme value because we want to be less than. We want to keep epsilon as small as possible. So we'll take the worst case scenario and say, worst case scenario, the 2 is more extreme. So the worst case scenario, the absolute value of x minus 1 is less than 2. That is what we're going to multiply delta by. Because x minus 1, worst case scenario is 2. X minus 2, worst case scenario is delta. So at least we know that the absolute value of x minus 2 times x minus 1 is less than 2 times delta. And now we know what to do with the epsilon. Epsilon divided by 2, the reciprocal of the 2, because it's multiplied by delta, to make the rest of the proof work. We have 2 times delta, which is epsilon over 2. 2's divide out, and we're just left with epsilon. And we're done because we've said that the function minus the limit is less than epsilon. So we can now say we're done. QED, quod eram demonstratum. I'm probably pronouncing that wrong, but you don't know Latin, so you can't prove me wrong. Let's do one more quadratic because these take a little bit more trying to manipulate that second factor in order to figure out what our delta is going to equal. So let's prove that the limit as x approaches -1 of 2x squared minus x plus 1 is equal to 4. Again, identifying the pieces, x is approaching our a. The function is what we're taking the limit of. And the answer, that is L, our limit. The first 3 statements of our proof are pretty prescribed to us. Let epsilon be greater than 0. We will choose a delta that's equal to, we don't know exactly what it equals yet, but we do know because this is a quadratic, we're going to do the minimum of 1 and something, the reciprocal of whatever delta is multiplied by. And then we assume the absolute value of x minus our a, or what x is approaching, minus -1 means plus 1, is less than delta. Now our algebra step, the function, 2x squared minus x plus 1, minus the limit of 4. A little bit of cleanup, the absolute value of 2x squared minus x minus 3. Hopefully, we can work with this and say it is ultimately less than epsilon. Well, we know we can factor it. 2x and x. To kind of help my factoring, I know I'm ultimately going to try and get an x plus 1. So hopefully that x is an x plus 1, which means the other one's probably a minus 3. And when I check that out, it does work. Plus 2 minus 3 is the minus 1. Nice. That's what we wanted. Now we have the x plus 1 that we like. We know that's less than delta, but we have to figure out what delta is multiplied by. So we need to play with the 2x minus 3. Using what we assumed, so kind of off to the side in our work, we assumed, going back to that assumption statement, we assume that x plus 1 is less than delta, which worst case scenario, it's going to be a 1, the absolute value. So we remove the absolute values by saying that's between +1 and -1. And then we want to massage this so that it looks like 2x minus 3, so we can figure out how extreme our situation is. I recommend doing the 2x part first. So we get it to equal, we get the 2x by multiplying by 2 on all 3 parts. Make sure we distribute, so we get -2 is less than 2x plus 2, which is less than 2. Buy us a little more whiteboard space. We want it to have a minus 3, 2x minus 3. Right now it's plus 2. So to get that to be minus 3, we need to subtract 5. 2 minus 5 will be the minus 3. So we subtract 5 from all 3 parts. And we get -7 is less than 2x minus 3, which is less than -3. Changing it back to an absolute value expression, 2x minus 3 is less than, and then we pick the most extreme case. So we're always ready for a worst case scenario. This time the most extreme case is on the right side, 7 being more extreme than the 3. And positive, because we're talking about absolute value. So 2x minus 3 is less than 7. That is what is being multiplied by our delta, which also tells us the reciprocal means divide by 7. So our delta is epsilon over 7. So we have 7 times delta, which is epsilon over 7. The 7's divide out, and we're just left with epsilon. So we've shown that f of x minus L is less than epsilon, which QED is what we wanted, that which was to be demonstrated. So that is your general proof for limit. We're just going to work with linear examples and quadratic examples in this class. You can take more advanced classes if you really want to prove a whole bunch of delta epsilons. But you should be very familiar with how to set up the proof. Always let epsilon be greater than 0. Choose a delta equal to something. And then assume that x minus a is less than delta. And then ultimately, we play with f of x minus L. I'll put it on top. That f of x minus L is less than epsilon. And if you do that, you've got a perfect delta epsilon proof. Practice a few of these. We will see you in class where we can talk more about these proofs in more detail. Chapter 3 is going to be all about the derivative. So to start off, we really need to know what is the derivative. Specifically, when we say the derivative, what we're talking about is the slope of a tangent line to a function. So the question we're going to answer is, how do we find the slope of a tangent line? And really, to answer this question, when we want the slope of a tangent line through a specific point, there are two methods. Both work equally well. Sometimes one is better than the other to find the slope of a tangent line. Also, by way of vocabulary, when we say the slope of a tangent line, what we're talking about is what is called in calculus the derivative. The rate of change instantaneously at that point. So the first method we're going to look at, kind of to set it up graphically, say we've got some curve going on here. And we've got some point that we want to know what is the slope, what is the rate of change of the tangent line at that point. So if I go up from A, we get a point on the line, and that is at f of A. Well, to get a slope, we need a second point that we can calculate it off of. So we'll go off to the right here, and we'll pick some other random x, which has a point on the line, and some f of x solution to that. So the coordinates of that second point in red are x comma f of x. And the coordinates of the point in green are a comma f of a. And the tangent line is the line that connects those two dots. Actually, that's a secant line. But the way we make that secant line... Actually, let's first talk about the secant line. What is the slope of the secant line? Well, to get the slope of the secant line, it's just the slope of the slope formula that we know already, y2 minus y1, and then we divide it by, subtract the x's. So for the slope of the secant line, that's going to be f of x minus f of a, subtracting the y's, divided by x minus a, subtracting the x coordinates. And the way we make that secant line into a tangent line is we take x and move it closer and closer to a. We move x to a, and then that line is going to become less secant and more tangent. Well, we know how to express that the slope of the tangent line then is the limit as x approaches a of that same function, f of x minus f of a, all over x minus a. So that is our first possible formula. It's going to be an important one for us for how to find the slope of the tangent line. There is a second way that's used quite often, and in fact, we'll probably use it more often overall in the course, that is similar to what we just did. So again, we'll make our little graph, and we've got some curve going on. And we'll have some a, which goes up to a point at f of a. But instead of going over to some x randomly, we're going to increase what we call h. So we end up with a point over here that's a plus h. And actually, let me do that in red. A plus h. And so the a plus h gets this point up here. And so what we actually end up with is f of a plus h. So if we want the slope of the secant line that connects these two together, just like before, the slope of the secant line is going to be equal to the difference in the y's divided by the difference in the x's. Let's go ahead and label that. This red point, the x-coordinate is a plus h, and the y-coordinate is f of a plus h. And then the green point is a comma f of a again. So for the slope, subtract the y's, f of a plus h minus f of a, all over the x-coordinates, a plus h minus a, which is nice because the a's actually subtract out to 0. So what we really have is f of a plus h minus f of a all over h. And the way we make this slope into or the secant line into a tangent line is we say we want that h, the amount we move over, to be basically 0. So we make the h go to 0. Or we say that the slope of the tangent line is equal to the limit as h goes to 0 of that function, f of a plus h minus f of a all over h. And that is the second way we can find the derivative at a point. And both of these functions are going to give us the same answer, but it's two ways to get at that same value. And sometimes one way will be easier than another way. So what we're going to do is we're going to work through 3 examples where we calculate the slope of the tangent line and also the equation of the tangent line while we're at it. But we're going to solve it both ways so we can kind of compare how the two formulas work together. So our first example that we're going to do is a polynomial. First, we're going to find the slope, and then we'll find the equation of the tangent line. Our polynomial is f of x equals x squared minus 3x. And we're going to find the slope of the tangent line at x equals 1. The first thing we need to know is what's the y-coordinate that we're working with. So f of 1 is equal to 1 squared minus 3 times 1, which is 1 minus 3, or negative 2. So we're really working with 1 comma negative 2 as our point. So using our first formula to solve for the slope of the tangent line, we know that the slope is equal to the limit as x approaches a of f of x minus f of a all over x minus a. Plugging in what we have then, we've got the limit as x this time is going to 1 of f of x, which is x squared minus 3x, subtract the f of a, which is what we just found. F of 1 is negative 2. So subtracting negative 2 is the same as adding 2, all over x minus the 1. What we see here is we can't do direct substitution because if we do, we divide by 0. But we worked with this problem a lot with limits in our previous unit. So we know we need to factor that numerator. It's going to be x minus 2 times x minus 1 over the x minus 1. And when we do that, the x minus 1s can divide out. And now that we've removed that discontinuity, we can plug into our function the limit value of 1. So x minus 2 becomes 1 minus 2, which means we have a slope of negative 1. Now, I did say there were two definitions. Remember, the second definition would be as if we took the limit as h goes to 0 of f of a plus h minus f of a all over h. So we have the limit as h goes to 0 of f of a plus h. Remember, a in this case is 1, so that really means 1 plus h. So x squared becomes 1 plus h squared minus 3x, which is 1 plus h. And then we subtract f of a, which we've already figured out in blue up above is negative 2. So minus negative 2 means plus 2 all over h. Multiplying out the pieces here, we've got the limit as h goes to 0. Squaring it, we get 1 plus 2h plus h squared minus 3 minus 3h plus 2 all over h. What's nice here is if we do the 1 minus 3 plus 2, 1 plus 2 is 3, minus 3 is 0. So now we've got the limit as h goes to 0 of 2h plus h squared minus 3h all over h. Every single term there has an h in it that we can factor out to remove our discontinuity. H times 2 plus h minus 3 all over h. I probably could have combined the 2 and 3. Wouldn't matter. But ultimately, those h's divide out, and now we can plug in the 0 for h. So we have 2 plus 0 minus 3, which is negative 1. We get the same slope of the tangent line. The slope at 1 is negative 1. Now that we know the slope, we can find the equation. Remember, the equation is y equals m times x minus x1 plus y1. So plugging in the pieces, y equals the slope of negative 1 times x minus, the x-coordinate is 1, and the y-coordinate is negative 2. We have the equation of our tangent line. Let's try another example where we work through both of the formulas. Let's do a fraction. Let's say f of x is equal to 3 over x plus 1, and we want the slope of the tangent line at x equals 2. Well, first we need to know what the y-coordinate is at 2. So we'll find f of a, or f of 2, remember that's the a, is equal to 3 over 2 plus 1, and 3 over 3 is just equal to 1. So we have the point x is 2, y is 1, or a is 2, and f of a is 1. We had two formulas to find the derivative or the slope of the tangent line at 2. Both of them work, give you the same answer. We're going to do both just so that we can see it worked out both ways. The first is the limit as x approaches a of f of x minus f of a all over x minus a. So for this function, we're doing the limit as x approaches 2 this time of the function 3 over x plus 1 minus f of a. We've already found out that f of a is equal to 1 all over x minus the a, which is 2. Well, what we see here is we've got a complex fraction inside a limit. But we've seen this before. We know we can get rid of that by multiplying by the x plus 1, distributing it through on top and bottom. And when we do, be careful with that negative sign. The x plus 1s are gone, and we get the limit as x goes to 2 of 3 minus 1x minus 1 all over x minus 2 times x plus 1. The limit as x goes to 2 of 2 minus x over x minus 2 times x plus 1. And we know 2 minus x and x minus 2 can divide out as long as there's a negative 1 left over, because the subtraction's in the wrong order. And now that we've removed that discontinuity, we can do direct substitution and plug 2 into the fraction. So we have negative 1 over x, which is 2 plus 1. And this gives us negative 1/3 for our slope. The slope at 2 is negative 1/3. Let's try and work that out again, this time using our second definition of the derivative at a point. And that's the one where we take the limit as h goes to 0 of f of a plus h minus f of a all over h. So the limit as h goes to 0 of, this time we're going to take a plus h. A is 2, because we're at 2. So 2 plus h. Of 3 over x, which is 2 plus h plus 1, minus the f of the a. We know that's 1 all over x, or all over h. The simplifying step is going to feel almost exactly the same. We need to get rid of that denominator, so we're going to multiply by 2 plus h plus 1 all the way across the numerator and the denominator. We're going to leave the denominator factored, however, because that's going to reduce out the h in just a minute. So first fraction, we're just left with 3 minus, distribute the negative 1 through, minus 2 minus h minus 1 all over h. Don't forget the limit as h goes to 0 all over h times 2 plus h plus 1. And we could have combined the 2 and the 1 if we wanted to. It's not going to make much difference. What's nice now, though, is if we do 3 minus 2 minus 1, that's completely gone. So why don't we do that simplifying? We have the limit as h goes to 0 of negative h over h times 2 plus 1 is 3 plus h. And we notice those h's are gone. We've removed the discontinuity. And so we're able to just plug 0 in. We have negative 1 over 3 plus 0, which is negative 1/3. Same answer both times, so I'm feeling pretty confident going into my equation of the tangent line here. The equation is y equals my slope, negative 1/3, times x minus the x-coordinate, which is 2, plus the y-coordinate, which is 1. The equation of the tangent line to 3 over x plus 1 at x equals 2 is y equals negative 1/3 times x minus 2 plus 1. One more example that I want to work through using both equations. This one is going to be finding the derivative with a radical. We're going to find the derivative, or the slope of the tangent line, of f of x equals the square root of x plus 1 at x equals 3. X equals 8, sorry, at x equals 8. So to do that, we first need to know the y-coordinate. So f of 8 is equal to the square root of 8 plus 1. 8 plus 1 is 9. Square root is 3. So we're talking about the point 8, comma 3. We have two ways to find the derivative. We're going to do both here so you can see how they both work out. The first is the limit as x approaches a of f of x minus f of a all over x minus a. So for our problem, the limit as x is going to an x-coordinate of 8 of f of x, which is the square root of x plus 1, minus f of a. And we just found out that f of 8, is 3, all over x minus a, and that a value was 8. Now, we've worked with limits with removable discontinuities and radicals before. Our strategy in the past was we get rid of the radical by multiplying by the conjugate. And so we'll do just that. We'll multiply by the square root of x plus 1, change it to a plus 3, over the square root of x plus 1 plus 3. And that's going to remove the radical in the numerator and hopefully set up something we can reduce. So we now have the limit as x goes to 8. In the numerator, conjugates will just square both of them and put minus between them. When we square a square root, we're just left with the stuff, x plus 1. Always a minus between them, and 3 squared is 9. Over, we've got the x minus 8 times the square root of x plus 1 plus 3. Cleaning up a bit, to combine like terms in the numerator, we've got the limit as x approaches 8 of x minus 8 over x minus 8 times the square root of x plus 1 plus 3. And that's nice because the x minus 8s divide out. Always remember, when we divide out everything, there's still a 1 in the numerator. And what's really nice is we've removed that discontinuity, so we're ready to plug that 8 into x. We've got 1 over the square root of 8 plus 1 plus 3. 8 plus 1 is 9. The square root of 9 is 3. Plus 3 is 6. We seem to be getting a slope of 1/6 at x equals 8. Now, just to practice the other definition as well, we've got the limit as h approaches 0 of f of a plus h minus f of a all over h. I like writing it every time until you get this ingrained in your head. It's an important formula to know for the rest of this unit and beyond. So we've got the limit as h goes to 0 of f of a. This time a is 8. So we're going to plug 8 plus h into the x, the square root of 8 plus h. And there's a plus 1. Minus f of a. We've already calculated that to be 3 all over h. Same strategy from here. We're going to get rid of the radical by multiplying by the conjugate, which is the square root of, let's go ahead and combine the like terms. 8 plus 1 is 9 plus h. We're going to make it a plus 3. Square root of 9 plus h plus 3. And when we do that, let's go on to the next line. We've got the limit as h goes to 0 of square the square root. We get 9 plus h. Negative 3 plus 3 is negative 9 over h times the square root of 9 plus h plus 3. Which is really nice because 9 minus 9 is 0. And that leaves us with the limit as h goes to 0 of h over h times the square root of 9 plus h plus 3. Reduce out the h's, remembering that leaves us with 1. But what's important there is we have removed our discontinuity. So we're ready to plug 0 in for h. We've got 1 over the square root of 9 plus 0 plus 3, which is 1 over 9 plus 0 is 9. The square root of 9 is 3. Plus 3 is 6. And we get the exact same slope. So we are ready to write the equation of our tangent line at 8 is y equals m, the slope of 1/6, times x minus the x-coordinate of 8 plus the y-coordinate of 3. Y equals 1/6 times x minus 8 plus 3. And so that's how we can find the equation of the tangent line at a point. We can use one of these two formulas. I believe the homework assignment tells you which formula to use for a given problem, so you get practice using both formulas with similar types of problems. But once you find the slope of the tangent line from one of those points, we just plug it into our equation formula. Take a look at some problems, and we will see you in class. In our previous lesson, we talked about how we could find the derivative at a specific point. But today we're going to extend that discussion and answer the question of how can we calculate the derivative at every point. So to set this up, we are going to expand our definition of the derivative to, instead of just calculating the slope of the tangent line at a specific point, we're going to start to look at the derivative as a function. And specifically, that function is going to be written as f with a little mark that we call prime, f prime of x. That means it's the derivative of f at x. F prime of x is equal to the limit as h goes to 0. And we're going to take that second definition of a derivative and kind of generalize it to f of x plus h minus f of x all over h. And this is going to be our equation to calculate the derivative as a function for all points x. So if we can just calculate this thing, we just have to plug in the x value to get the actual derivative at any point we're interested in. So let's see if we can actually use this formula to find the derivative of, let's start with f of x equals x squared minus 4x plus 1. So to calculate the derivative, f prime of x, we're going to replace each of the x's with the x plus h. So x plus h, it becomes x plus h squared. Whoops, forgot the limit part. Don't forget the limit part. That's important. Limit as h goes to 0 of x plus h squared minus 4 times x, which is now x plus h plus 1. And then the derivative function says subtract the entire function f of x. It's very important when you do this, you put the function in parentheses, because otherwise we're going to run into a sign error. We're not just subtracting the first term. No, we want to make sure we subtract the entire thing. That negative is going to ultimately, in our next step, distribute through that parentheses onto the entire polynomial there. We'll get there in a minute, but don't forget to put the function in parentheses. And it's all over h. So cleaning this up then, we're going to end up with the limit as h goes to 0 of, and when we square, we get x squared plus 2xh plus h squared Distribute the negative 4 through, we get negative 4x minus 4h plus a 1. Then distributing the negative through, we get negative x squared, positive 4x, and a negative 1. Distributing that negative all the way through, all over h. But what's nice now is this is as ugly as it gets, because you'll start to see lots of things are going to disappear. We've got x squared and a negative x squared. Those go to 0. We've got a negative 4x and a positive 4x. Those go to 0. We've got a positive 1 and a negative 1. Those go to 0. And so when we clean up, we just have left the limit as h goes to 0 of 2xh plus h squared minus 4h all over h. We want to remove the discontinuity at h, and it's nice because we can factor out in h. So we have the limit as h goes to 0 of h times 2x plus h minus 4 all over h. And now we divide out the h's. We've removed the discontinuity, so we can replace h with what it's approaching, 0, 2x plus 0 minus 4, or just 2x minus 4 is the equation for the derivative of the tangent line of x squared minus 4x plus 1. Now, if we wanted to know the derivative at any value, we just plug in that number. If we want to know what the derivative is when x equals 0, plug 0 in, we get negative 4. If we want to know what the derivative is at 10, we plug 10 in. We get 20 minus 4, which is 16. And it's really quick to calculate the derivative now that we have a function to describe it. Let's try one more example. Let's take f of x is equal to the square root of 2x plus 1 and see if we can calculate her derivative. So to calculate the derivative, f prime of x, it's equal to the limit as h approaches 0 of f of x plus h. We're going to replace the x with x plus h. That gives us the square root of 2 times x plus h plus 1. Minus the function itself, which is the square root of 2x plus 1, all over the h. Well, we've seen square roots before. We know to get rid of them, we multiply by the conjugate. So we have the square root of, and I'm going to go ahead and distribute just to save us the work, 2x plus 2h plus 1. We use plus, the opposite sign, the square root of 2x plus 1. And do the same thing in the denominator, 2x plus 2h plus 1 plus the square root of 2x plus 1. When we do that, we have the limit as h goes to 0. We square the square roots. They're gone. We've got a minus in between them. So we have 2x plus 2h plus 1 plus minus between them. Don't forget the minus between them. Minus, and I'm going to go ahead and distribute that negative onto both parts. Make sure it goes onto both parts. Negative 2x minus 1 all over h times, and we'll leave this factored because we want to be able to reduce the square root of 2x plus 2h plus 1 plus the square root of 2x plus 1. And then things become nice for us. 2x minus 2x is 0. 1 minus 1 is 0. And so we just have the limit as h goes to 0 of 2h over h times the square root of 2x plus 2h plus 1 plus the square root of 2x plus 1. And ultimately, those h's divide out, and we have removed our discontinuity. Now we're ready to plug in what we know. H is 0. So we have 2 over the square root of 2x plus 2 times 0 plus 1 plus the square root of 2x plus 1 What's nice is that 2 times 0 is actually equal to 0. So we have matching radicals in the denominator. 2x plus 1 times 2x plus 1. So we've got 2 of those. So we have 2 over 2 square roots of 2x plus 1. And actually, we can reduce out the 2's, which is going to leave behind a 1. So for our final function, 1 over the square root of 2x plus 1. So now that we know kind of how to calculate derivatives, and there'll be a lot to practice on the assignment and in class, I want to talk a little bit about how the derivative is connected to the graph of the function. We're going to see if we can sketch a graph of a derivative. Because remember, the derivative describes the slope or the rate of change of the tangent line. In fact, let's write that down. The derivative is the slope of the tangent line. So if the graph is increasing, if the graph is going uphill, then it's got a positive slope because the slope is going uphill. In other words, f prime of x has to be greater than 0. That means the graph must be going uphill somehow. You see it's going uphill from left to right. It's got a positive slope. If the slope, or if the graph, is decreasing, the graph is going downhill, the tangent line will also go downhill, so the slope of the tangent line is negative. In other words, the derivative f prime of x is negative. It's less than 0. The graph is going downhill, so the graph of the tangent line is also negative, showing the downhill slope. I guess we could also say the neutral statement, that if the graph hits a flat point, if the graph is flat, then we could say the slope is 0. In other words, we would say f prime of x is equal to 0. And that could happen a couple of ways. It could be going up and level out. So there's your slope 0 right on top. It could be going down and leveling out. So your slope is 0 down there on the bottom. It's completely flat. Or it could make a trough where it comes up, levels out, and keeps going up or keeps going down. But you notice right in the middle there, the tangent line does level out as it changes direction. So what this looks like then on a graph is, for an example, is if I have a function here, we'll call this f of x. And let's see, we're going to put a point on the graph at, let's give it some height too. We'll put a point on this graph at -3, -2. And another point at -1, 2. Then a point at 2, -2. And then we'll connect it by coming in from the top, hitting the first point and going up, hitting the second point and going down. And we're going to make a trough where we level out and keep going down at the third point. Let me see if I can make that a little better here. Down, maximum, level off. There we go. Maybe. We'll call that good enough. In order to draw a graph of the derivative of this function, a graph of f prime of x, what we'll do is we'll kind of make some observations about this graph. The first observation that's going to be helpful to us is identifying where the tangent line is completely flat. Because at all of those points where the tangent line is flat, we know the slope is equal to 0. Which means we've got a 0 on our graph at each of those points. So the slope is 0 here at -3. At -3, there's a 0. At -1, the slope is 0. And at +2, the slope is 0. That's where we've got our x-intercepts of 0, because the graph is describing the slope. The next thing I notice is the graph starts going downhill. The slope is negative. So we need to start negative on our graph until we hit that point. After that, the graph starts going uphill. It's increasing. The slope is positive until the next 0. So we need to make sure our graph is positive until we hit the next 0. Notice the green line is now all above the x-axis, positive to the next 0. Then we're decreasing to the next 0, so we're going to be negative. Need to be negative to the next 0. But afterwards, it's still decreasing, which means after the next 0, we still need to be decreasing. We still need to be negative. So the graph starts negative, turns positive, turns negative, and then stays negative. And so we've sketched approximately, not exactly, but pretty close to what the derivative of this first function looks like, because we know that if the graph is increasing, the derivative is positive. If the graph is decreasing, the derivative is negative. And if the graph is flat, the derivative is 0. I have one more extension I want to put onto this lesson, and it's really just more of the same of what we saw at the beginning, along with a little bit of notation. And it's this idea of what we call higher ordered derivatives. And the idea here is if we take a function and we can find its derivative, which is also a function, we should be able to take its derivative to get another function, and then take its derivative to get another function, and just keep taking derivatives of derivatives. Derivatives of derivatives. And to set this up, I want to talk a little bit about notation and one of the challenges of calculus that came out of it. Calculus was developed simultaneously by both Newton, who gets all the credit, and Leibniz. I'm probably pronouncing his name wrong. But both of them used a different notation for how to express the derivative. And so as a result, we have two different notations for how to express the derivative. Newton used f of x, and his compadre used y. And so when we're talking about the first derivative, the derivative that we just take, Newton would just put a prime on it. So we'd see f prime of x to represent the first derivative. Alternatively, with just the y, we could call that dy dx, which is the derivative of y with respect to x, what the variable is that we're working with. The second derivative, then, the derivative of the derivative, with f of x notation, we just do a double prime to show the derivative has been taken twice. However, with the dy dx notation, we say we take the derivatives twice of y with respect to x twice. And so we get d2y over dx2. And then we kind of extend that to the third, fourth, fifth, and beyond derivatives, where you'll see 3 primes to represent the third derivative. And then it's d3y for the third derivative of y with respect to x 3 times. So that's kind of the notation you might see. But really, it just means take the same formula for the same idea. In other words, the derivative of the derivative, or f prime prime of x, is equal to the limit as h goes to 0 of f prime of x plus h minus f prime of x all over h. In fact, I'm not even going to mark this as a key formula because it's the exact same derivative formula. This time, we're just working with the derivative to calculate the second derivative. Let's do an example where we can see that worked out. We're going to find the second derivative of 3x squared minus 4x plus 1. Well, in order to find the second derivative, we first have to know what the first derivative is. So let's find the first derivative. F prime of x is equal to the limit as h goes to 0 of f of x plus h. We're going to replace the x's with x plus h. 3 times x plus h squared minus 4 times x plus h plus 1 minus the f of x, which we're going to put in parentheses so we don't forget to distribute the negative through, minus 3x squared minus 4x plus 1 all over h, which is equal to the limit as h goes to 0 of, with this first part, we have to square the x plus h and then distribute a 3 through. So I'm just going to square it off to the side here. X squared plus 2xh plus h squared. And then I'll distribute the 3 into that. So we have 3x squared plus 6xh plus 3h squared. Distribute the negative to get negative 4x minus 4h plus 1. Distribute the negative through to get negative 3x squared plus 4x minus 1 all over h. Hopefully we can clean this up a bit. 3x squared minus 3x squared is 0. Negative 4x plus 4x is 0. 1 minus 1 is 0. And so we have the limit as h goes to 0 of 6xh plus 3h squared minus 4h all over h. And we remove that discontinuity by factoring out the h. Times 6x plus 3h minus 4 all over the h. The h's divide out, and now we can just plug in the 0. So we have 6x plus 3 times 0 minus 4, which is equal to just 6x minus 4. But that is just the first derivative. This problem wanted us to find the second derivative. So using our new function, we take the derivative again. F prime prime of x is equal to the limit as h goes to 0 of f of x plus h. We're going to replace the x with x plus h. So we have 6 times x plus h minus 4. Subtract the function, or subtract the 6x minus 4, and put it all over h. Distributing through, we get the limit as h goes to 0 of 6x plus 6h minus 4 minus 6x plus 4, distributing that negative through, all over h. Fortunately, we can subtract some things out. 6 minus 6x is 0. Negative 4 plus 4 is 0. And so we have the limit as h goes to 0 of 6h over h, which is really nice because the h's divide out. And we're just left with a single simple number 6 as our second derivative of 3x squared minus 4x plus 1. If I wanted to find the third derivative, we would just run through the formula again. But ultimately, with this lesson today, the important key thing is that you know the function for the derivative is the limit as h goes to 0 of f of x plus h minus f of x all over h. Try a few and practice this. We'll take a look at it more in class, and we will see you then. Now that we've gotten comfortable with the definition of the derivative, the common frustration is how tedious that formula is. So the question that starts to come up is, what are some derivative shortcuts? So that we don't have to go through that formula every time. And you can imagine as a function becomes very complicated, the derivative function could become very tedious to work through. Well, there's lots of derivative shortcuts we're going to look at over the next several lessons. We're going to look today at 4 basic shortcuts. And then after that, we'll take a look at 2 important shortcuts that are a little bit more involved. The most basic is the constant shortcut. And the idea of the constant shortcut is if we take the derivative, d dx is the alternative notation for a derivative, the derivative of some constant or some number, we're going to always get 0 for our answer. Because if a constant is a straight line, the derivative of a straight flat line is 0. So for example, if I wanted to calculate the derivative of 5, a constant, well, that's just going to be 0 because 5 is not changing. It has a slope of 0. The second basic shortcut is the power rule, and this is probably the one we will use the most. And the idea is if we're taking the derivative of x raised to some exponent. When we have x raised to some exponent, we'll pull that exponent out in front, and then we will reduce the exponent by 1. And this is probably the most used derivative shortcut. With polynomials, we pull the exponent out front and then decrease the exponent by 1. So for example, if I wanted the derivative of x to the 7th power, all I have to do is I move that 7th power out front, and then I reduce the exponent by 1, and we get 7x to the 6th. A third rule, I'm going to call it the sum rule. It's often called the difference rule as well because it works with plus or minus. And the idea is if I take the derivative of some function plus or minus another function, where I know the derivative of the individual pieces, all I have to do is take the derivative of the individual pieces. And it's f prime plus g prime of x. So, for example, combining the power rule and the sum rule together, it should be plus or minus. If I wanted the derivative of x to the 5th minus x squared plus x plus 2, we just take the derivatives of the individual pieces. The power rule says we move the exponent out front and subtract 1. So we get 5x to the 4th minus x squared, bring the 2 out front, subtract 1 from the exponent, we just have x, plus, with x, that's really x to the 1st, so we pull the 1 out front and drop it by 1. So x to the 0 is just 1. And then the derivative of 2, a constant, is just 0. So all that we're left with is the 5x to the fourth minus 2x plus 1. The final basic shortcut is the constant multiplier. Which says if I'm taking the derivative of some constant times a function, we keep that constant in front and multiply it by the derivative of that inside function. And that is the fourth basic shortcut. So, for example, if I wanted the derivative now of 3x to the fifth minus 2x to the fourth plus 5x squared minus 7x plus 1. Let's get us a little more whiteboard space so we can put it right underneath it. The 3 can just be multiplied by whatever the derivative is of x to the fifth. Well, we know we pull that exponent out front, so 3 times 5 is 15. X to the 1 less, fourth power, minus, bringing the exponent out front, 2 times 4 is 8, x cubed, shrinking the exponent by 1, plus 2 times 5 is 10, x, shrinking the exponent by 1, minus 7 times 1 is 7. Shrink the exponent by 1, and the x disappears, and the derivative of the constant is 0. So now we have our new derivative of that polynomial. These 4 basic rules of differentiation will save us a lot of work and time on that derivative formula. Now, in fact, we should be able to quite quickly find, let's do this in black, quite quickly find the equation of the tangent line to f of x equals 4x cubed minus 2x squared plus 5x minus 1 at x equals -1. Well, first we need to know what the y-coordinate is that we're going to end up with. Actually, no, first let's actually find the derivative at 1. So first we're going to take the derivative, f prime of x is equal to 4 times 3 is 12, x squared, subtract 1 from the exponent, minus 2 times 2 is 4, x, plus 5, and the x disappears. We want it at specifically x equals -1, so we'll do f prime of -1, which is 12 times -1 squared, minus 4 times -1 plus 5. And if we work that out, it becomes 12 plus 4 plus 5 is 21. So the slope we now know is 21. We do need to know the y-coordinate of this point. When x is 1, what does y equal? So we do need to plug the -1 into the original function as well. F of -1 is equal to 4 times -1 cubed minus 2 times -1 squared plus 5 times -1 minus 1. So our y-coordinate is equal to -4 plus 2 minus 5 minus 1, which gives us -12. So for the equation of our line, y equals the slope we found out was 21 times x minus x1, minus a -1 is +1, minus 12, and our line tangent to our function is 21 times x plus 1 minus 12. So those are our basic properties to help with differentiation. The next two are a little more involved, and they take a bit of practice to get used to using. We'll see a lot of errors with this one particularly, which is the product rule. The product rule says that the derivative of two pieces that are multiplied by each other, f of x times g of x. The common error I see is people just take the derivative of both and multiply, and they say f prime times g prime. That is incorrect, and it does not work. What we actually do is the derivative of the first part times the second part plus the derivative of the second part times the first part. So there's two parts to it, and we take the derivative of the first part in the first part and the derivative of the second part in the second part. So for example, if I wanted to take the derivative of 3x squared minus 5x plus 1 times 2x squared plus 4x minus 7, we've got two individual parts. So the formula says we take the derivative of the first part. The first part, the 3x squared, let's color code these. We'll do the first part in blue and the second part in green, just so we can see how this works out. So in blue, the derivative of the first part is 6x minus 5. Then that is multiplied by the second part, 2x squared plus 4x minus 7. Plus, then we take the derivative of the second part. The derivative of the second part is 4x plus 4 times the second part, 3x squared minus 5x plus 1. And this, then, as ugly as it looks, is the correct answer for the derivative of that product. So the derivative of the first times the second plus the derivative of the second times the first. Let's look at one more. Let's do the derivative of 5 over x squared plus 3 over x times 2x cubed minus 7. Whoa, we don't really have a derivative trick for x's being in the denominator. Actually, we do. We just need to tweak this problem a little bit and rewrite it as the derivative of, and think about what type of exponent sticks things in the denominator. Well, a negative exponent does that. This is really 5x to the negative 2 plus 3x to the negative 1 times the 2x cubed minus 7. So again, now we're multiplying two polynomials, a first part times a second part. And the formula says it's equal to the derivative of the first. 5 times negative 2 is negative 10x. And if we subtract 1 from negative 2, the new exponent is negative 3. 3 times negative 1 is negative 3x. Subtract 1 from the exponent, and we get negative 2. The derivative of the first times the second, 2x cubed minus 7. Plus the derivative of the second. 2 times 3 is 6x squared. And the negative 7 is a constant, so there's nothing there. Times the first. 5x to the negative 1. I'm sorry, 5x to the negative 2 plus 3x to the negative 1. And this, then, is the derivative of that product. That is the product rule. Similar to the product rule is what we're going to call the quotient rule. And I should probably label this as C. The quotient rule. It's got two tweaks to make it different, but it's very similar. if I'm taking the derivative of two things that are divided, f of x divided by g of x. Be careful, this is not f prime divided by g prime. We can't just divide the derivatives. Instead, we will take the derivative of the first times the second. And because this is division, we'll actually subtract the derivative of the second times the first. And the big difference here is we have to divide by the denominator squared, which is kind of interesting. We end up with this squared denominator in the denominator. So for example, if I'm being asked to find the derivative of 4x squared minus 5x plus 1 over x squared minus 7, we've got a top piece and we've got a bottom piece. Keeping track of that, then, we take the derivative of the first piece. 4 times 2 is 8x minus 5 times the denominator, just like it is, x squared minus 7. Then we subtract the derivative of the denominator. X squared becomes 2x times the numerator, which is 4x squared minus 5x plus 1. And then in the denominator, we take the old denominator, x squared minus 7, and we square it to get our final big, ugly, but correct derivative. This formula takes a little bit of practice to get really comfortable with, but it certainly is much nicer than doing it with the derivative formula. Let's do another one. Let's take the derivative of the square root of x over 2x cubed minus 7 over x. One thing you might notice right away, let me buy us some whiteboard space, is that we need to rewrite that so it's that friendly polynomial so we can use our exponent trick. So we're going to actually find the derivative. Square root is really just a 1/2 power over 2x cubed minus 7x to the negative 1, which is what moved that x into the denominator. Now we have a clear numerator and denominator to use in our formula. We take the derivative of the first one, pull the exponent out front, x, subtract 1 from 1/2. 1/2 minus 1 is negative 1/2. Times the denominator, which is 2x cubed minus 7x to the negative 1. Subtract, and then we take the derivative of the denominator. 2 times 3 is 6, x squared. Negative 7 times negative 1 is positive 7, x to the now negative 2, times the first function, which is x to the 1/2. And this is all over that denominator, 2x cubed minus 7x to the negative 1 squared. And we now have the derivative of our quotient. Now that we have a couple derivative rules, we can actually take a look at some applications of the derivative and solve some more interesting problems. And one of the most common applications of the derivative is the relationship between the position of an object, the velocity of that object, and that object's acceleration. All three of these things are connected by derivatives, because the derivative is the rate of change. And so the velocity describes how the position is changing. The acceleration describes how the velocity is changing. So these three variables, or functions really, we can make for each of them, The position describes where the object is at time t. And we will use the function s of t to represent the object's position at a given moment of time. But it's moving. And so to describe the speed or rate at which it's moving, we have the velocity, which the velocity can be thought of as speed, but speed doesn't really have a direction. Velocity does have a direction, positive generally meaning to the right, negative generally meaning to the left. So speed with direction, or the rate of change at which the position is changing. So the change in position. So we will use v of t to represent the velocity at a specific point in time. But because it's the change in position, we say that it's the derivative of the position. Finally, we have the acceleration, or how fast the velocity is changing, the change in velocity. And we use a of t to represent the acceleration. And because that's describing the change in velocity, that's the derivative of the velocity, or the second derivative of the position. So knowing that we have this relationship between position, velocity, and acceleration, all connected by the derivative, we can solve problems in relationship to these three questions. So for example, if the position of an object in feet after t seconds is given by s of t is equal to t cubed divided by 5 minus 3 over t squared, what is its velocity and acceleration after 2 seconds? First thing I'm going to do with this function is I'm going to change it to be a nicer polynomial, because I don't like having or a nicer rational expression. I don't like having the fraction in a fraction. So I'm going to write that as t to the negative 2. So s of t is equal to t cubed over 5 minus 3 t to the negative 2 power. And then we can take the derivative of this function to find the velocity function. So the velocity at time t, this is a quotient. So we take the derivative of the top, which is 3t squared, times the denominator, which is 5 minus 3t to the negative 2, minus the derivative of the denominator, which is negative 3 times negative 2 is positive 6t to the negative 3, times the numerator, t cubed, all over the denominator, 5 minus 3t to the negative 2 squared. I'm going to clean that up a little bit just so that we can take a second derivative of it, because we're also being asked about the acceleration. So when we distribute through, we get 3 times 5 is 15t squared minus 9. And when we add the exponents, we get 0 t's. And then minus 6, and we have 0 t's. Since we have negative 9 minus 6, I'm going to write that as negative 15. Over, and I'm going to go ahead and square this out. We've got 25 minus 30t to the negative 2 plus 9t to the negative 4. So we should be able to calculate the velocity after 2 seconds by plugging 2 into this formula. 15 times 2 squared minus 15 over 25 minus 30 times, not t, but 2 to the negative 2 plus 9t, which is 2 to the negative 4 power. And we can plug this into our handy-dandy calculator. Second quit to get me to the home screen. We need a parentheses around the numerator. 15 times 2 squared minus 15, close the parentheses, divided by parentheses for the denominator, 25 minus 30 times 2 raised to the negative 2 power plus 9 times 2 raised to the negative 4 power, and then close the parentheses on the denominator. And my velocity at 2 seconds seems to be about 2.49 feet per second. Almost 2.5 feet every second this guy's going to travel. That's the velocity. But the problem's also asking for the acceleration. So let's scroll down to give us some more whiteboard space. The acceleration, then, at t is going to be the derivative of the velocity. So we've got this derivative of a velocity function. So we'll take the derivative of the numerator, which is 30t, times the denominator, which is 25, minus 30t to the negative 2 plus 9t to the negative 4, minus the derivative of the denominator. Negative 30 times negative 2 is positive 60t to the negative 3, minus 36t to the negative 5, times the numerator, which is 15t squared minus 15. And then that is all over the denominator squared, 25 minus 30t to the negative 2 plus 9t to the negative 4, all squared. Now the problem was asking us what's the acceleration at 2 seconds. So in order to get that, we're going to need to go back to our calculators. I'm not going to write it out. I'm just going to put 2 in for everything all the way across here. So we've got a numerator, parentheses, 30 times 2, open a parentheses, 25 minus 30 times 2 raised to the negative 2 power plus 9 times 2 raised to the negative 4 power, close the parentheses, minus, open a parentheses, 60 times 2 raised to the negative 3 power, minus 36 times 2 raised to the negative 5 power, close the parentheses, open a parentheses, 15 times 2 squared minus 15, close the parentheses, and close the parentheses on the numerator, divided by denominator, open a parentheses, 25 minus 30t, which we know is 2, raised to the negative 2 power, plus 9 times 2 raised to the negative 4 power, close the parentheses on the denominator, and square the denominator, and hit enter to find out our acceleration is 2.44 feet per second squared. So it might have been ugly to type in the calculator, but it just took time. It wasn't difficult plugging 2 in for all those t's. So that's velocity, acceleration, and position, derivatives of each other. But the big thing that I want you to practice with these differentiation rules, specifically focus on the product rule and the quotient rule. The sooner you master those, the more advantage you will have moving forward in our calculus class. So take a look at those, practice, 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 and we will see you in class to practice some more. Now that we're able to quickly calculate derivatives, we're able to look at some applications of how we can use the derivative to model some real-world situations. So our question is, what are some applications of the derivative? And the first one we've already kind of hinted at over the past couple lessons, but we're going to formalize our discussion around position, which we use s of t as a function to represent position over time. Velocity, where we use v of t to represent the velocity over time. And acceleration, where we use a of t to represent the acceleration at some point in time. Now, we've already discussed the fact that the velocity is the derivative of position. Or more specifically, v of t is equal to the s prime of t. And we've also discussed that the acceleration is the derivative of the velocity. Or a of t is equal to v prime of t, or the second derivative of the position, s prime prime of t. But what we haven't discussed is how velocity and acceleration work together or against each other. For example, I want to look at if the acceleration is in the same direction as the velocity. In other words, we're getting more and more push in the direction that we're going. If you think about the football player who's trying to get the first down on third and inches, the players on his own team are pushing him as he accelerates in the same direction as the push. He's going to end up going further and faster. So the object is going to, let me put the word the in front. The object will speed up because we're being pushed in the direction we're running, so we will run faster. And the opposite is also true if they are in opposite directions. Sticking with the football player analogy, you've got a football player running downfield, and the defender grabs him and pulls him backwards. It doesn't necessarily mean he's going to go backwards, but he's not going to go forward at the same speed because those forces are in opposite directions. So because the push and the speed are in opposite directions, it or the person slows down. So the acceleration pushes or pulls to either speed up or slow down. The question is, are they going in the same direction? So let's look at an example. The position of an object actually, we're going to have two examples. So let's say number 3 is examples, and example A is going to be the position of an object in t seconds is given by s of t equals t cubed minus 3t squared minus 45t plus 7. The question we want to know is, when is it speeding up? And when is it slowing down? When are the acceleration and velocity pushing in the same direction? And when are they pulling against each other in opposite directions? Let's get us some space to work on that. And we'll attempt to answer that by first finding the function for the velocity, which is the derivative of the s of t. And the derivative there is going to be 3t squared minus 6t minus 45. The acceleration, then, is going to be the derivative of the velocity, which is going to be 6t minus 6. So we need to know when these are changing directions. When does the velocity change directions from left to right? When does the acceleration change from speed up to slow down or push to pull? And so really what we need to know is, when do they each cross the threshold of 0? Because that's when they change directions from positive to negative, from push to pull, from faster to slower. So for each of these, we're going to solve for when they equal 0. So with the velocity, 0 equals 3t squared minus 6t minus 45. And we can solve that by first factoring out the GCF of 3, t squared minus 2t minus 15. And then continuing to factor, that's t minus 5, t plus 3. And so setting each factor equal to 0, t is equal to 5 or negative 3. Now, generally, we don't talk about negative time, so we're going to start at 0 for all of our time references. So really, we don't care about the 3. But at 5, things are probably changing at 5 because the velocity is changing direction at 5. Same thing with the acceleration. We want to know when that changes. So we'll make that equal to 0, 6t minus 6. Add 6 to both sides, and 6t equals 6. Divide by 6, and t equals 1. So something else of note is happening at 1. So what we want to know is, if I make a little timeline here, something happens at 1, and something happens at 5. We're going to look at how the velocity and the acceleration are behaving in these time ranges. Are they specifically, what we're interested in is, are they positive or are they negative? Because that's going to tell us if they're pushing each other or if they're pulling against each other. Fortunately, this is really easy to do on our calculators. What we're going to do is we're going to type in the function for the velocity in y1. And then we'll type in the function for the acceleration in y2. So y1, the velocity, is 3t squared. We don't really have a t, so we're going to use x. Minus 6t, or x, minus 45. And in y2, it's 6t, or 6x, minus 6. Then we're going to go to the table settings. Second table. And we can delete out whatever we were working on before. And what we'll do for our x is we're going to pick an x that falls within each range on this number line. So first we need something between 0 and 1, because our graph really starts at 0. And we want to know what's happening in the middle of each of these areas. So between 0 and 1, a good number is 0.5. Hit enter. And looking at that, I see that they're both negative. Remember, the middle column, the y1 is the velocity. The next one, the y2, is the acceleration. But they're both negative. And that's what's important to me right now, is they are negative between 0 and 1. Now let's pick something between 1 and 5. Maybe 3. 3 falls between 1 and 5. Notice there, the first one, the velocity is negative, but the acceleration is positive. So the velocity is negative, but the acceleration is positive. Finally, we need something past 5, maybe 8. We can pick any number past 5. And when I do that, I see that they are both positive. So the velocity is positive, and the acceleration is positive. Now we're ready to kind of interpret what we've got here. When the velocity and the acceleration are both going in the same direction, notice between 0 and 1, they're both negative. That means the velocity, it's going backwards, and the acceleration is pushing further backwards. Same direction, we're going backwards at a faster and faster rate. We're actually speeding up between 0 and 1. Then between 1 and 5, we see they're going in opposite directions. The velocity is negative, so we're going backwards, but the acceleration is pulling it forward. So it's starting to slow down and slow down and slow down because they're pulling in opposite directions. Until finally the acceleration wins and gets the velocity going in the other direction. And now they're both going in the positive direction, with the acceleration pushing in the positive direction. So we're going faster and faster. So again, when they're the same, we're speeding up. When they're different, we're slowing down. So giving it as a range, this item is speeding up between 0 and 1 second. Union 5 all the way to infinity, it will always speed up, while it's going to slow down between 1 and 5. Let's do another example where we can take a look at how the position of an object is changing, whether it's being pushed or pulled in the same direction or in the opposite direction. So let's say the position of an object in seconds, using t for seconds, is given by s of t equals x cubed minus 9x squared plus 24x minus 3. And so our question, our theme, is when is it speeding up and slowing down? And we can decide that by looking at the velocity function and the acceleration function and determine when they're pushing or pulling in the same direction or opposite directions. So the velocity, that's just the derivative of the position, which is 3x squared minus 18x plus 24. The acceleration, it's the derivative of the velocity, so that's 6x minus 18. And we're specifically interested when both of these are changing between positive and negative, because that's where things are going to change. And they change at 0. So 0 equals 3x squared minus 18x plus 24. On the velocity, we'll factor out a 3, x squared minus 6x plus 4. Nope, plus 8. Sorry, 24 divided by 3 is 8. 0 equals 3 times x minus 4 times x minus 2. And so this time we have two solutions, x equals 4 and x equals 2. With the acceleration, we get our other key point by making it equal to 0, 6x minus 18. If we add 18 to both sides and divide by 6, we get x is equal to 3. So something is probably happening at 2, 3, and 4. So we'll make our little number line here. 0, 2, 3, and 4. And we're going to be interested in what happens to the velocity and what happens to the acceleration. Again, we'll use our calculator to help us do this a little quicker. Hit y equals. And we're going to clear out the functions that are in here. Make sure you clear them out so you don't accidentally get the previous problem in here. The velocity was 3x squared minus 18x, x. There we go. Plus 24. And the acceleration is 6x minus 18. Hit second table. Delete out the old points. And we need something between 0 and 2. 1 is between 0 and 2. And we've got a positive, then a negative. The velocity is positive. The acceleration is negative. They're going in opposite directions to begin with. Between 2 and 3, let's try 2.5. Now they're both negative. Looks like the acceleration ended up winning here. So the velocity is negative, and the acceleration is negative. Pick something between 3 and 4, maybe 3.5. Now notice the velocity is negative, but the acceleration has changed to positive. So the velocity is still negative, but the acceleration is now pulling it in the positive direction. And finally, bigger than 4. We can pick any number bigger than 4. I picked 5. We see they're both positive. So now the velocity is positive, and the acceleration is positive. And it's going to stay that way all the way up to infinity. So we see initially the velocity is positive, the acceleration is negative. They're in opposite directions. It's going to slow down there. Between 2 and 3, they're in the same direction. It's going to speed up. Between 3 and 4, they're in opposite directions, slowing down. And then 4 on up, it's going to speed up. So writing that as a range, we're speeding up between 2 and 3, union from 4 to infinity. And we're slowing down from 0 to 2, union from 3 to 4. This particle is actually slowing down to ultimately change directions. So that's one application of the derivative: position, velocity, acceleration, speeding up, and slowing down. A second application that we're going to take a look at is in business, with the idea of revenue, cost, profit, and what are called marginal changes. When we say a marginal change in business, that is the change for one more. And usually this is on the large scale. So once I make 1,000 widgets, if I make one more widget, 1,001 widgets, is it more profitable or less profitable, more cost, less cost? Making one more, how's that going to affect my bottom line? And that can help us make the decision if it's worth expanding or shrinking the business at this given time. because we're talking about change, a marginal change, which is a very small change, we can estimate the marginal change with the derivative. Let's break down some of these business terms. We've got cost, which we normally represent with c of x. And we've got marginal cost. For marginal cost, we do mc of x for marginal cost, which is actually estimated, not actually, but estimated by the derivative of the cost function. We've also got revenue. Revenue, we usually use r of x for revenue. And often we have to find that because what we actually have is some price function that needs to be multiplied by the number of things that we sell. So if the price is $5 and we sell 7, 5 times 7, we've made $21 in revenue. This price function, the price per item, is often a function, because the price is going to be dependent on various variables. So we've got the revenue, and we've also got marginal revenue. And as you might expect, we use MR for marginal revenue of x, which can be estimated using the derivative of the revenue. And finally, what we're always interested in business is the profit. The profit is P of x, which is simply calculated by taking the revenue, or the amount of money we took in, and subtracting the cost that it took to bring in that money. And we also have a marginal profit, or how much more money do we make for selling one more. So marginal profit of x, as you might expect, is equal to the derivative of the profit at x. So those are kind of the parts of the profit function. Let's take a look at some examples and see if we can wrap our head around what is this marginal profit, marginal cost, and marginal revenue. First, the cost to develop a product is c of x is equal to 500 plus 12x. Startup cost of 500, and then each one cost $12. We want to know what is the marginal cost of the 100 first item. Now, a nice way to estimate the marginal cost of x is to simply take the derivative of the cost function. Well, this is really nice because the derivative of 500 plus 12x is just 12. So we'll estimate that the 12th item will cost $12 extra. I'm sorry, the 100th item will cost $12 extra because every single one we add to it costs $12 extra. That's probably a less exciting example. So let's try a price function. The price function for the product, same product, is P equals 126 minus 0.15, I'm sorry, 0.16 x. We want to know what is the marginal revenue for the 101st item. So first we need to know what is the revenue equation or expression, function. Remember, revenue is always x times the price function. The number of things we sell times the price for each one of those. So that's 126 minus 0.16x. And if I distribute to make the derivative easier, 126x minus 0.16x squared. So then the marginal revenue of x is pretty darn close to the derivative of the revenue. So that's 126 minus 0.32x. And we want to know the marginal revenue of the 101st item. So we can plug 101 into this function to estimate it. 126 minus 0.32 times 101. And quickly typing that in my calculator, we'll get $93.68. Which means after I've sold 100 items, the 101st item is going to make me another $93.68. Or so. How accurate is that estimate? Because remember, I did say it is an estimate. Let's find out. Note the actual. Because the derivative is just an estimate. It's going to be off by a bit because the tangent line touches at 100, but not necessarily at 101. It's off by a little bit. So we could calculate the revenue at 100, how much revenue we've already made at 100. So the revenue equation was 126 times 100 minus 0.16 times 100 squared. And plug that into my calculator. We actually make $11,000. The revenue at 101 is 126 times 101 minus 0.16 times 101 squared. We make $11,093.84. And so if we want the marginal revenue, that's how much more we made for the 101st item. We subtract these. 11,093.84 minus 11,000. We actually get $93.84 is the actual marginal revenue. The 101st item actually brings us in $93.84. But much quicker with the derivative, we estimated $93.68, which is pretty darn close and probably good enough for this business to make a decision based on. We're not going to care about less than about 15 cents, 16 cents. Of a difference when we're trying to make decisions on our product, whether to expand or contract. So that's why it's always better to use the derivative, because it's quicker, it's easier, it's clearer to understand. The actuals just take too long to calculate and really don't make much of a difference. So we've done cost and we've done revenue. Let's add one more, though. What's the marginal profit? For the 101st item. Well, remember, P of x, the profit, is equal to the revenue function minus the cost function. And the revenue function, we've got it up here above on part B. It's 126x minus 0.16x squared minus the cost function, which was given to us up here in part A, 500 plus 12x. So distributing that minus, because we have to subtract the whole thing, minus 500 minus 12x. And then actually combining like terms, we get negative 0.16x squared plus 114x minus 16x, oops, minus 500. Keep things in the right order. And so if we want the marginal profit, we take the derivative. The marginal profit of x is equal to the derivative of the profit function, which is negative 0.32x plus 114. And we want the marginal profit of the 101st item. So plugging 101 in there, negative 0.32 times 101 plus 114. If we were to make one more item, we would make an additional $81.68. Our marginal profit. I want to do one more application of the derivative based on where we're at right now. And that is in population change. Truth is, anytime you see the word change, we're really dealing with a derivative in action. Anything that changes is the derivative. So with population change, if we use P of t to represent the population at time t, then the derivative, P prime of t, is the rate of change of the population. So for example, if I have a bacteria population that is growing according to the function P of t is equal to x cubed minus 18x squared plus 96x plus 20, where t is in hours, when is the population growing and shrinking? We want to know when it's growing and shrinking. We're talking about the derivative. We're talking about the change. So the change in the population, P prime of t, the derivative of that function is 3x squared minus 36x plus 96. And where the change happens between growth and shrinking, growth, the derivative is positive because it's going up. Shrinking, the derivative is negative. It's going down. So it changes when the derivative is equal to 0. So 0 equals 3x squared minus 36x plus 96. And we know we can solve this by factoring. Factor out the GCF of 3 times x squared minus 12x plus 32. 0 equals 3 times x minus 8 and x minus 4. I probably should have t's, not x's, because it's P of t. I'll change to P of x, then it works. P of x. So x is equal to 8 and 4 hours. So at 8 and 4, things are changing. So if we got a timeline here, at 4 things change, and at 8 things change. What is happening with P prime of x? What is happening to the derivative? Are we increasing or decreasing? Is the derivative positive or negative? So again, we'll go to our calculator, hit y equals, clear out these other formulas. And our population is changing according to 3x squared minus 36x plus 96. And if we hit second table, we can try out a few values for time and see if the derivative is positive or negative. If it's positive, it's increasing. If it's negative, it's decreasing. Between 0 and 4, we'll try 2. We see it's positive. Between 4 and 8, we'll try 5. Negative. Bigger than 8, 9. It's positive. So it goes positive, negative, positive. Positive, negative, positive. So what that means is the population is growing wherever the derivative is positive. Between 0 and 4 hours, union. And then from 8 to infinite hours, it's never going to stop growing. And it's shrinking in between 4 and 8 hours because the derivative is negative. So we're talking about population, business, and physics with velocity and acceleration, a couple key applications of the derivative. We'll talk about more as the course develops, but that's enough to get you going for now. We will see you in class to dive into these a little bit deeper. Up until now, we've avoided really talking about trigonometric functions and the derivatives. So today we're going to attempt to answer the question of what are the derivatives of the trig functions, sine, cosine, tangent, and also the less used ones of cosecant, secant, and cotangent. And to begin setting this up, we're going to look at the graph of f of x equals sine x. And you'll remember from your days of trigonometry, it has a maximum of 1 and a minimum at -1. And then at pi over 2, pi, 3 pi over 2, and 2 pi, things get exciting. Going the other direction, same thing, negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. And if you remember, the sine of x starts at 0. It reaches a maximum at pi over 2, back to 0, minimum at 3 pi over 2, and back to 0, doing kind of the same exact thing in the opposite direction when we are on the other side. So the sine of x is this familiar graph. If that's the sine of x, then what I want to graph next to it is see if we can graph the derivative of the sine of x. Using kind of the same scale we had before with pi over 2, pi, 3 pi over 2, 2 pi, negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. And what I want to notice as we graph the derivative, f prime of x, as we graph the derivative, I want to notice first off where the derivative is 0. Notice the derivative is 0 at negative 3 pi over 2. It's 0 at negative pi over 2. It's 0 at positive pi over 2. And it's 0 at 3 pi over 2. And also I want to notice it starts out increasing. Starts out increasing from the negative 2 pi up to the 0. So that means it's going to start positive down to our negative 3 pi over 2. Then it's decreasing, meaning our derivative is negative up until it reaches pi over 2. Then we're going uphill and we're positive again up until the graph equals pi over 2, then decreasing all the way until we equal 3 pi over 2, then increasing or positive all the way up to 2 pi. And so we end up with this derivative graph. And what's interesting is this derivative graph should look familiar to us. Notice at 0, it starts at 1, and it's got the same shape as our familiar cosine of x function. So in other words, what we've discovered here is that the derivative of sine appears, at least from the graph, to be the cosine of x. Well, let's take the derivative of this graph. Just a little too tall. I want to have room for a label. And doing the same thing now. Whoops. Let's try that again. Let's see if we get something else familiar when we take the second derivative, f prime prime of x, or the derivative of cosine, to see what we end up with here. Let's label here. We've got negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. Go in the other direction. We have pi over 2, pi, 3 pi over 2, and 2 pi. And again, noticing where the derivative is 0 at negative 2 pi. It's 0 at negative pi. It's 0 at 0. And it's 0 at pi. And again, it's going to be 0 at 2 pi. But this time, the graph starts out decreasing, which means it has to start off negative. So it's going to start off negative up until it reaches the negative pi. Then, between the zeros, it's increasing. So the derivative has to be positive until it reaches the 0. Decreasing, indicating the derivative is negative. And then increasing, indicating the derivative is positive up until the 0. Now, what we might hope is that there's this relationship that the derivative of sine is cosine and the derivative of cosine is sine, but that's not quite the case because sine starts out increasing. This one starts out decreasing. It's actually flipped over the x-axis from the sine graph. In other words, this red graph here is actually the graph of negative sine of x. And so really what we found is that the derivative of the sine of x is equal to the cosine of x, and that the derivative of the cosine of x turned out to be the negative sine of x, at least graphically. So can we use that information then to learn what the derivative is of the tangent of x? Well, what's nice about the tangent is we know that tangent is actually the sine of x divided by the cosine of x. We have that property from trig, which means really all we have to do is use the quotient rule. The derivative of sine, we said, was cosine x times the denominator, cosine x, minus the derivative of the denominator. The derivative of cosine is negative sine. Negative, negative makes it positive. Times the numerator, which is the sine of x, all over the denominator squared. So what we have really is cosine squared of x plus sine squared of x all over cosine squared of x. But that numerator should look really familiar to us. We should recognize from our trig days that sine squared plus cosine squared is 1. So we have 1 over cosine squared of x. But cosine is just the reciprocal of secant. And so we end up with secant squared of x. The derivative of tangent is secant squared. Well, similar to what we just did with the tangent of x and using the quotient rule, we can work our way through all the other trig derivatives. So similarly, we complete all the trig derivatives. In fact, the remaining 3 are left to a homework assignment. But here they are in their properties. the derivative of the sine of x is equal to the cosine of x. The derivative of the cosine of x is the negative sine of x. The derivative of the tangent of x is the secant squared of x. Those are the ones we just played with. But the other three, which are left to an exercise in the homework, the derivative of the secant of x turns out to be the secant of x times the tangent of x. The derivative of the reciprocal of cosine, the derivative of the reciprocal of sine, which is cosecant of x, is negative cosecant x cotangent x. And the derivative of the cotangent of x is equal to negative cosecant squared of x. These 6 trig identities, at least sine and cosine you should have memorized. But ultimately, we're going to have to be able to use all 6 of these trig derivatives. Six important formulas for us to learn. And that's what we're going to focus on today. Actually, that's all there is that's new. We can just combine all of this with things like our product rule, our quotient rule, our polynomial rules, and calculate a whole bunch of derivatives. So let's see if we can use these in a couple examples. First, we're going to look at f of x equals 3x to the 4th sine of x plus 7 over x. Now, one thing you might notice is that 7 over x we can rewrite. So let's rewrite it as 3x to the 4th sine x plus 7x to the negative 1. So we can use our polynomial formulas. And then we'll start calculating the derivative of x, of f of x. First thing I notice is we really have a product rule to start us off. We've got 3x to the 4th times the sine of x. So to do the product rule, we take the derivative of the first, which is 12x cubed, times the second, sine of x, plus the derivative of the second. The derivative of sine is cosine x, times the first, and I'll just put it in front to make it obvious that it's not inside the cosine. And then after the product rule, we still have to take care of the plus 7x to the negative 1. 7 times negative 1 is negative 7, x to the negative 2. And we've got our derivative. Let's try another one that might be a little more involved. Let's say f of x is equal to the cosine of x minus x to the 5th times the cotangent of x plus the secant of x. Now it should be clear here we're working with a product, 2 pieces multiplied together. So we have to do the product rule for f prime of x for the derivative. So we'll take the derivative of the first term, or the first factor. The derivative of cosine x is negative sine x minus x to the 5th becomes 5, x to the 4th, times the second, cotangent x plus secant of x, plus the derivative of the second. The derivative of cotangent is negative cosecant squared of x, plus the derivative of secant is secant x tangent x. And then we have to multiply by the first part, the cosine x minus x to the 5th. And we've got our derivative. One more for this video. F of x is equal to tangent of x minus 3x to the fourth over cosecant of x minus 7. Now we're dividing two functions. With division, we know we need to use the quotient rule, just like we always have before. The quotient rule says we take the derivative of the top. The derivative of tangent, we now know, is secant squared of x minus 3 times 4 is 12, x cubed. The derivative of the top times the bottom, cosecant x minus 7, minus the derivative of the bottom. Well, the derivative of cosecant is negative cosecant. So a negative negative makes it positive. Cosecant x cotangent x times the denominator. Or I'm sorry, times the numerator, times the first part. Tangent x minus 3x to the fourth. And that's all over the denominator squared. Cosecant x minus 7 squared. So today's video is really short because there's not a lot of new stuff to add. All we have now is we've added the 6 trig derivatives. And then we kind of tie them into all the other derivative rules that we've seen before, the quotient rule, the product rule, the polynomial rules, and just continue to practice taking these important derivatives. With calculus and derivatives, practice, practice, practice is the key until you can do these derivatives in your sleep. So go ahead and try some of these off the homework assignment. This video is shorter to give you more time to get into the practice, and we'll dive into these more in class. I'll look forward to seeing you then. Quite often when we're trying to find the derivative of a function, we find out we actually have a composite function, or a function inside a function. And so that's the question we're going to address today, is how do we take a derivative of a composite function? A function inside of a function. And really, the short answer to that is we use something that is called the chain rule, which officially is written that the derivative of a function with another function inside it is equal to the derivative of the outside function, where the inside stays the same. Actually, I should use square brackets there, times the derivative of the inside function. So in words, it's probably easier to remember the chain rule is we take the derivative of the outside times the derivative of the inside. And that's what we're going to take a look at today. I've got 7 examples where we basically do this process over and over again. We take the derivative of the outside times the derivative of the inside. But this chain rule is one that you should be very comfortable with completing, working through in order to take derivatives. So let's take a look at some examples. Where we take the derivative of the outside times the derivative of the inside. Let's say we've got a function f of x equals 1 over 4x minus 7 cubed. Now, one thing I noticed with this, to make it easier to take the derivative, we could use the quotient rule, but that's just way too much work for what we need to do because we've just got a 1 in the numerator. This is really 4x minus 7 with a negative 3 exponent because the negative exponent makes it a reciprocal 1 over that. So what we see we've actually got here is the 4x minus 3 as a block is all raised to the negative 3 power. If this was just x to the negative 3, we know the derivative of that is negative 3x to the negative 4. So that's kind of what we're going to do here, but we're going to use the 4x minus 7 in place of that x. So we pull the exponent out front, and f prime of x is equal to negative 3 times the base, the 4x minus 7, all to the negative 4 power. Now the only thing we have to do is multiply by the derivative of the inside. And the derivative of 4x minus 7 is just 4. We'll clean that up a bit. Let's see, the negative 3 times 4 is negative 12. So we've got negative 12 times 4x minus 7 to the negative 4 power as our final derivative. But the idea here is we identified that we've got that 4x minus 7 inside another function, which is the x to the negative 3. So we took the derivative of the outside times the derivative of the inside. So let's look at another one. Let's say we had f of x equals the square root of 3x squared minus 7x plus 1. Now again, we recognize square root is really an exponent. We've really got 3x squared minus 7x plus 1 to the 1/2 power. And so what we need to recognize here is we have a function inside of a function. What we really have is the 3x squared minus 7x plus 1, that function sitting inside a 1/2 power. In other words, this is kind of the same idea as if we had x to the 1/2 power. We know how to take the derivative of x to the 1/2 power. That's 1/2 x to the negative 1/2. Bringing the exponent out front and then reducing the exponent by 1. The only difference is instead of having an x, we're going to have the 3x squared minus 7x plus 1. So our derivative is, we pull the exponent out front. It's 1/2 times the stuff, 3x squared minus 7x plus 1. And then we reduce the exponent by 1, giving us negative 1/2. The only thing we have to do in addition is multiply by the derivative of what's inside. The derivative of 3x squared minus 7x plus 1 is 6x minus 7. And there we have our final answer. The only thing we might want to do is clean up a bit because we've got that negative exponent and a fraction going on. I'll leave the 6x minus 7 in the numerator. The 2 is in a denominator. And the 3x squared minus 7x plus 1 with the negative exponent moves down. That just cleans it up. It's not really a needed step, but it does make it a little prettier. But now we have our derivative. Let's try to increase in complexity a little bit as we continue working through these problems. Let's go to a trig problem. What if we have f of x equals the cosine of 5x squared? With this one, what you notice is we have got the 5x squared sitting inside of a cosine. So we'll take the derivative of the outside times the derivative of the inside. So the derivative of cosine is, let's mark this as f prime of x equals The derivative of cosine is negative sine of the stuff, 5x squared. And then we multiply by the derivative of the inside, which is 10x. Clean this up a little bit, and we'll move the 10x to the front. So we just see negative 10x sine of 5x squared. And we've got our derivative. The derivative of the outside times the derivative of the inside. What about this one? F of x equals secant squared of x. What's the outside and what's the inside function? Another way to think about secant squared of x is, that's really secant of x squared. So actually, our inside function is the secant of x. The outside function is that we're squaring it. So if we're squaring it, we know we bring, for f prime of x, we bring the exponent out front, and then reduce the exponent by 1. And we multiply by the derivative of the inside. The derivative of secant is secant tangent. Just to clean this up a bit, secant times secant is secant squared. So we have 2 secant squared x tangent x. And we've got our derivative. Let's try another one. How about if we had f of x is equal to cosecant of 3x squared minus 5x? Again, we've got a function inside of a function. Identifying what's inside is the 3x squared minus 5x. So we'll take the derivative of the outside times the derivative of the inside. And the derivative of cosecant is negative cosecant cotangent. So we have f prime of x equals negative cosecant of the stuff, 3x squared minus 5x, cotangent of the stuff, 3x squared minus 5x, times the derivative of the inside. Well, the derivative of the inside, using our power rule, is 6x minus 5. There's not much to clean up on this one. The only thing we might be able to do is move the 6x minus 5 to the front, so it's really clear that that part is not part of the cotangent or cosecant. So we have negative 6x minus 5. Don't lose the parentheses. Cosecant of 3x squared minus 5. Cotangent of 3x squared minus 5. And we've found our derivative. To make these a little more exciting, we can combine different rules together to find derivatives. Number 6 is an example of this, where we have f of x equals 4x plus 5 cubed times 2x squared minus 6x plus 1 to the 7th power. This problem is going to combine the chain rule along with the product rule. So we see we're working with a product, but the product is of functions within functions. On the left side, we see 4x plus 5 is inside the cubed function. On the right side, we see 2x squared minus 6x plus 1 is inside the 7th power function. So let's use our product rule along with our chain rule in order to find the derivative. The product rule says we take the derivative of the first part times the second part. So the derivative of the first part, we bring the exponent out front, 3 times 4x plus 5. Reduce the exponent by 1, so it's squared. And then we multiply by the derivative of the inside, which is just 4. Then, that's the derivative of the first part. We still need to multiply by the second part, 2x squared minus 6x plus 1 to the 7th power. Plus. Now the product rule says we take the derivative of the second part times the first part. The second part is a chain rule again. We bring the 7 out front times 2x squared minus 6x plus 1. Now to the 6th power, because we've reduced the exponent by 1, times the derivative of the inside. The inside has a derivative of 4x minus 6. And that part is the derivative of the second part. We still have to multiply by the first part, which is 4x plus 5 cubed. From here, there's just a little bit of cleanup. I'm going to multiply 3 times 4 to get 12 times 4x plus 5 squared times 2x squared minus 6x plus 1 to the 7th power. The second part doesn't really have any cleanup to do, so we'll just keep that all the same. 7 times 2x squared minus 6x plus 1 to the 6th power times 4x minus 6 times 4x plus 5 cubed. And that big, ugly thing is the derivative of our function. Notice to get that derivative, we had to combine both the chain rule and the product rule. We knew the product rule was the derivative of the first times the second, plus the derivative of the second times the first. But in order to take those derivatives in each of those parts, we had to use the chain rule, where we took the derivative of the outside times the derivative of the inside. We not only can combine the chain rule with other rules, we can combine the chain rule with the chain rule. If we've got functions inside of functions inside of functions, we can just keep applying the chain rule, taking the derivative of the outside times the derivative of the inside times the derivative of what's inside that times the derivative of what's inside that until we run out of things to take the derivative of. So for our final example, if f of x is equal to the tangent cubed of 5x squared minus 7, what you'll see we have here, and maybe we should rewrite, remember tangent cubed means we really have the tangent of 5x squared minus 7 to the 3rd power. So we've got a tangent inside of cubed. But then we've also got a 5x squared minus 7 inside of the tangent. And those colors are overlapping, making it very difficult to see. But you get the idea. So we're going to first take the derivative of the outside function, which is cubed. So for the derivative of a cubed, we pull the 3 outside. and reduce the exponent by 1. Now it's tangent squared of 5x squared minus 7. Then we take the derivative of the inside. Well, the derivative of tangent is the secant squared of the inside stuff, 5x squared minus 7. But we're still not done, because we can take the derivative of the inside stuff, which is going to be the 5x squared minus 7. The derivative of that is just 10x. Cleaning up a little bit, 3 times 10 is 30, so f prime of x is equal to 30x tangent squared of 5x squared minus 7 times secant squared of 5x squared minus 7. And now we've got our derivative, which required us to use the chain rule on the chain rule, which all we do is just start peeling off layers, like peeling the layers off an onion. Derivative of the outside times the derivative of what's in that, times the derivative of what's in that, times the derivative of what's in that, until we finally reach the end. So that's the chain rule. The chain rule is we just keep taking derivatives and multiplying until we reach the far inside of our function. This video is a little bit shorter because it's going to give you time to practice this on your own before you come to class. And then we'll dive into it a little deeper in class and answer any questions. I'll look forward to seeing you then so that we can work on the chain rule. As we continue to work with derivatives, we want to continue to expand the types of functions we can take the derivative of. And there's another one that we've missed, and that is the inverse trig functions. So the question we're going to answer is, what are the derivatives of the inverse trig functions? And before we can actually answer the question about what are the derivatives of the inverse trig functions, we really have to understand how derivatives of inverses work. And there's a nice little theorem that says that if f inverse of x is the inverse of f of x, then the derivative of f inverse at x is simply the reciprocal of the derivative at that inverse point. Maybe a better way to say that that's not so mathematical is if a comma b is a point on f of x, then the slope of the tangent line is f prime of a. We stick that x-coordinate into the derivative. We already know that, though. That's just our basic definition of the slope of a tangent line that we've been working with thus far. So if AB is a point on f of x, then b comma a, switching the x and y coordinates, is on f inverse of x. And the slope of the tangent line is, and it turns out to be, just the reciprocal of the slope of the standard function. So the slope of the inverse is the reciprocal of the slope of the function. We'll say 1 over f prime of a. And that's probably an important slope to know. 1 over the derivative at that point. So let's take a look at how we can do some of these reciprocals of slopes or derivatives to calculate some tangent lines on inverse functions. So for example, we're going to find the equation of a tangent line of the inverse of f of x equals x cubed minus 7x plus 5 at 5. So we're going to break this down into 3 parts. First, it's really important as we're talking about this, we keep track of our 5. Is that the x-coordinate or the y-coordinate of the function or of the inverse? Because the function and the inverse have the same x and y coordinates. They're just switched and backwards. And it's really easy to get those confused. So let's take a moment to really clearly say that 5 is the x-coordinate of the inverse. We're finding the equation of the tangent line of the inverse at 5. So 5 is the x-coordinate of the inverse, which means it is the y or the f of x for the regular function. Maybe I should say y for the f of x. So it's the x of the inverse, and it's the y for the function, which means we need to still find the other coordinate, the x of the f of x. So if f of x is x cubed minus 7x plus 5, and 5 is that y coordinate, this is like saying it equals 5. And we can solve this really quickly for x. We'll subtract 5 from both sides to make it equal to 0. X cubed minus 7x equals 0. Factoring out the x from both sides, or factoring out the x of both terms, sorry, we get x minus x squared minus 7 equals 0. And let's scroll down a little more here, give me some more space. And we'll set each factor equal to 0, so x equals 0, and x squared minus 7 equals 0. So x is equal to plus or minus the square root of 7. So we've got 3 possible values for our x-coordinate to make the y-coordinate 5. 0, square root of 7, or negative square root of 7. OK? In fact, let's clearly state that on f of x, the point we're talking about is 0, 5, square root of 7, 5, and negative square root of 7, 5. We've got 3 points, which means on the inverse, we're talking about the opposites, 5, 0, 5, square root of 7, and 5, negative square root of 7. Keeping track of what's x, what's y on which function. Probably the most challenging part of this section is keeping track of what is what. All right, so next thing we're ready to do is, now that we know what our x and y coordinates are that we're working with, we still need to find the slope of the tangent line of f of x, because we know that the slope of the tangent line of the inverse is just the reciprocal of this slope. So just because it's off my screen, I'm going to write the function again, x cubed minus 7x plus 5, so that we can take the derivative at 3x squared minus 7. So we need to find the slope at each of the 3 points, at each of the 3 x coordinates that we just found. So we're going to find f prime of 0, f prime of the square root of 7, and f prime of negative square root of 7. We're going to have 3 because we're dealing with 3 points. I think the homework assignment specifies a specific range, so you're only doing one of the points. But the process is the same, so let's take the extra practice. First, plugging 0 into the derivative, we have 3 times 0 squared minus 7. That's just going to equal negative 7. Plugging square root of 7 in, we've got 3 times the square root of 7 squared minus 7. That's 3 times 7, or 21 minus 7. That's equal to 14. Really similar with the negative square root of 7, because squaring a negative is the same as squaring the positive. So we've got 3 times 7, or 21 minus 7, is 14. So now we can make the equations of the tangent line on f prime, oops, not f prime, f inverse of x. Remember, with f inverse, we have to switch coordinates because x is y and y is x on the inverse. We also have to do the reciprocal slopes. So for our first point, let's see if I can get the points on the screen here. On the inverse, the first point was 5, 0. And at that point, we found the slope was equal to negative 1/7, the reciprocal of the negative 7. So we have y equals negative 1/7 times x minus 5 plus the 0. That's the equation of the tangent line at 5, 0. What if we wanted to do it at 5 square root of 7? Actually, let's do this in a different color just to keep the different colors separate. The second point was 5 square root of 7. There, the slope is the reciprocal of 14, or 1 over 14. So we have y equals 1/14 times x minus 5 plus the square root of 7. We had a third point. Our third point was at 5, negative square root of 7. That slope is going to be the reciprocal of 14, which is 1 over 14. So for that equation, we've got y equals 1/14 times x minus 5 minus the square root of 7. And now we've got our 3 tangent lines that are tangent at an x-coordinate of 5, depending on the y-coordinate, because this inverse isn't actually a function. So we probably should have restricted the domain. But it provided us the chance to practice 3 times with this process of finding the slope of the tangent line to the function, knowing the inverse is the reciprocal slope. Let's try one more example that uses this idea before we get to trig. How about this example? The point 4, 1 is on the inverse of f of x equals x to the 5th minus 3x squared plus 4 squared. Find the equation of the tangent line. Well, we know the tangent line is going to have the reciprocal slope of the function's tangent line slope. So let's find the function's tangent line slope. F prime of x equals, this is a chain rule here. We'll take the derivative of the outside, which is 2 times x to the 5th minus 3x squared plus 4, times the derivative of the inside, which is 5x to the 4th minus 6x. Now remember, 1 is on the inverse. So the point we want that's on the standard function before the inverse is actually reversed. It's actually 1 comma 4. So we want to make our x equal to 1 because we're dealing with the standard function, not its inverse. So f prime of 1 is equal to 2 times 1 to the 5th minus 3 times 1 squared plus 4 times 5 times 1 to the 4th minus 6 times 1. And maybe use a calculator to do that real quick. 1's nice because it's not going to do anything exciting when we multiply it or when we do exponents with it. So we've got 2 times 1 to the 5th, which is just 1, minus 3 times 1 squared, which is just 3, plus 4. Close the parentheses. Then we have 5 times 1 to the 4th, which is just 5, minus 6 times 1, which is just 6. And so we get this nice slope of negative 4. So if that's the slope of the function at 1, the slope at the inverse, at the alternative coordinates, the slope of the inverse that we're going for is negative 1/4. And the point we're working with is 4 comma 1. So we just go straight to our equation. Y equals negative 1/4 times x minus 4 plus 1. That's going to go through the point 4, 1. It's on the inverse of, it's tangent to the inverse of our function. But the original question that we're dealing with had to do with the inverse of the trig functions. So we haven't touched any trig functions yet. Let's see if we can use what we've just learned about inverses to find the derivatives of the inverse trig functions. To set this up, I want to consider f of x equals sine x. If we want the inverse of sine x, we remember from our trig days, we call that just the sine inverse of x. And it's really important to note that that negative 1 is not an exponent. It's not an exponent. That doesn't mean sine to the negative 1 power. That means the inverse sine of x. It might be called the arcsine of x. Well, using what we know, then what we know about inverses is we can find the derivative of the inverse using the derivative of the standard function. So the derivative of the standard function, f prime of x, the derivative of sine is cosine of x. And we know that the derivative of an inverse is equal to 1 over the derivative of the function's inverse. So in our case, that's going to be 1 over f prime, the derivative is cosine, of the inverse function, which is sine inverse of x. And if we think back to our trig days, we remember to find sine inverse of x, we say, hey, well, we've got a triangle, the cosine of the sine inverse. We've got a triangle. We like to make the radius equal to 1. And we want the sine inverse of x. So sine inverse of x. So we're talking about x. So the opposite over the hypotenuse is the sine. Opposite over the hypotenuse is x. So x over 1 is x. And then using the Pythagorean theorem, The other side has to be 1 minus x squared, the square root of all of that. So that's our triangle for the sine inverse of x. We want to take the cosine of that. And cosine is adjacent over hypotenuse. The adjacent over the hypotenuse, in this case, is the square root over 1, which is just the square root. And so we end up with 1 over the square root of 1 minus x squared. 1 over the square root of 1 minus x squared, then, is the derivative of the inverse sine. Using this exact same process, we can actually find the derivative of all the inverse sine function or inverse trig functions. So similarly, we get the derivatives of the inverse trig functions. Six inverse trig functions. The derivative of sine inverse of x, we just found out that that was 1 over the square root of 1 minus x squared. Similarly, the derivative of cosine inverse of x turns out to be negative 1 over the square root of 1 minus x squared. And the derivative of tangent inverse of x, using the same process, will be 1 over 1 plus x squared. And then we can find the derivative of the reciprocals. The reciprocal of sine is cosecant. Its derivative is negative 1 over the absolute value of x times the square root of x squared minus 1. The derivative of secant inverse of x is 1 over the absolute value of x times the square root of x squared minus 1. And the derivative of cotangent inverse of x is negative 1 over 1 plus x squared. So you've got 6 more important derivatives to add to your list of derivatives. The nice part about these is if you know your trig well enough, you should be able to derive them all using our inverse formula that we just found. Or you can memorize them, which comes quite naturally out of just trying a few of these over and over again in practice. So let's do just that. Let's do 2 examples where we're finding the derivatives of the inverse trig functions. Let's say f of x equals the cosine inverse of x squared. We're dealing with the chain rule here. We've got x squared inside the cosine inverse. So let's see how that comes out. The derivative of cosine inverse is negative 1 over the square root of 1 minus x squared. But x squared is in there, so we've got x squared squared. X squared squared is x to the 4th, knowing that we multiply those exponents. Times the derivative of the inside. The derivative of x squared is 2x. And since that's really 2x over 1, we can simplify to get negative 2x over the square root of 1 minus x to the 4th. Let's try another one. Let's say f of x is equal to the square root of x times the secant inverse of x. By this point in our study of calculus, when we see that square root of x, we should immediately know to change that to x to the 1/2 power so that we can use our exponent properties. So we have x to the 1/2 secant inverse of x. And let's start taking the derivative using the product rule, because we're dealing with a product. So the derivative of the first is 1/2 times x to the negative 1/2 times the second, which is secant inverse of x, plus the derivative of the second part. The derivative of secant inverse is 1 over the absolute value of x times the square root of x squared minus 1 times the first, which is x to the 1/2. Let's clean that up a little bit. Let's go ahead and use our negative exponents. The 1/2 means we've got a 2 in the denominator. X to the 1/2 sticks the square root of x in the denominator. Now be careful with secant inverse. That is not secant to the negative 1 power. That is not a negative exponent. That's an inverse trig function. So we'll put the secant inverse of x in the numerator, plus x to the 1/2, that's really the square root of x in the numerator, absolute value of x times the square root of x squared minus 1. And now we've got the derivative of that function. So we did a little bit of work today with inverse functions. But the big idea that I want you to be able to pull out of this lesson is how to take the derivative of the inverse functions using these 6 derivative properties. We'll also do a little bit of work with inverses in general, but the bulk is going to be here on the trig derivatives. Practice a few of these. We will see you in class to dive into them a little bit deeper. Now that we're able to use the chain rule in order to calculate more complex derivatives, we are actually ready to answer a deeper question about finding derivatives. And that's for finding derivatives around functions, or not functions, but relations between x and y that are more complex than a function. This would include things like circles, ellipses, hyperbolas, or more complex graphs and non-functions that do not pass the vertical line test. So the question is going to be, how do we take the derivative if it is not a function of x? In other words, it's going to fail the vertical line test. It's not a function. And everything we've done thus far has been all predicated on the idea of a function. And so what we're going to have to do is, if it's not a function, we're going to have to use what's called implicit differentiation. And the idea with implicit differentiation is we're going to have a function where y is a function of x. We don't know what it is, or it's too complex for us to work with. And so we'll just take the derivative of y times the derivative of what's inside it. And the derivative of y, we know, is just dy dx. So in summary, we can use the chain rule with this idea that the derivative of y with respect to x is dy dx. But of course, dy dx is what we're trying to find. What is the derivative of y with respect to x? And so what we will then do is we will then solve for dy dx. And generally, dy dx will be a linear function. So we'll be able to get all the dy dx's on one side, factor out dy dx, and divide by whatever it's multiplied by. But to get an idea of what this looks like, let's start with the simple example. Just a basic circle with a radius of 6 has the equation x squared plus y squared equals 36. And just kind of to draw a picture off to the side, we won't normally do this, but just to get an idea of what we're talking about here is we've got a circle with a radius of 6. And the idea is that we could, in theory, come up with a tangent line to this circle that touches at one point. And we could put that tangent line anywhere on the circle. And so what we want to do is come up with what is the equation of the slope of that tangent line. What is dy dx? But we can't do it by our traditional means because this thing is not a function. It does not pass the vertical line test because it's going to a vertical line will cross the graph twice. So because it doesn't pass the vertical line test, because it's not a function, we will take the derivative implicitly, which means we're going to use this idea of the chain rule whenever we come across a y. So first, the derivative of x squared is 2x plus the derivative of y squared. Now, keeping in mind the chain rule, we're going to treat the y like it's the inside stuff. And so the derivative of y squared is 2y, but we have to multiply by the derivative of the inside. And the derivative of y is dy dx. Equals, we'll do the same thing on the other side. The derivative of 36 is 0. And now I've got something that I can solve for the dy dx. To solve for the dy dx, we'll subtract 2x from both sides. And we have 2y dy dx equals negative 2x. Get the y by itself, or the dy dx by itself, by dividing by 2y, and we get negative 2x over 2y. Or by reducing out the 2's, we have dy dx is equal to negative x over y. So the slope of the tangent line of this circle is negative x over y. We would then know from our point what x and y are, and we'd be able to find the slope at any given point. Now, that was a simple example. These examples can quickly increase in complexity as we combine quotient rules and product rules and chain rules and all the other rules we've seen. So let's try several of these examples. We'll do 2 more examples where we're just solving for dy dx, and then we'll also look at how we can find the equation of these tangent lines. So first, we're going to look at x cubed y squared minus the sine of x equals the tangent of y. To take the derivative implicitly, because solving for y would be a headache, we'll take the derivative of the first part here. We notice we've got a product, the x squared times the y squared. So we will use the product rule. The derivative of x cubed is 3x squared times the second part, which is y squared, plus the derivative of the second part, which is 2y dy dx. And I'll just put that in parentheses so we can see what we're solving for, times the first part, which is x cubed. Now that we've used the product rule, we keep going down our function. The derivative of negative sine is negative cosine of x equals the derivative of tangent is secant squared of y, but times the derivative of the inside. Whenever we take the derivative with the y, we have to multiply by dy dx. Now we just have to solve for the dy dx. To do that, we're going to get all the dy dx's on one side. So I'm going to move that 2y dy dx. That's a terrible y. The 2y dy dx times x cubed, we're going to move that to the left side. So we now have 3x squared. It should be green. 3x squared y squared minus the cosine of x equals the secant squared of y times dy dx minus 2yx cubed times the dy dx. And then, because the dy dx is on both terms, we're able to factor that out. Dy dx times the secant squared of y minus 2yx cubed is still equal to, the other side's unchanged, 3x squared y squared minus cosine x. And so to get the dy dx alone, we just divide by everything it's multiplied by. And so now we can say that dy dx, the derivative or slope of the tangent line of this relationship, is 3x squared y squared minus cosine x divided by what was multiplied by the dy dx, the secant squared y minus 2yx cubed. And that's how we can use this idea of implicit differentiation. We just keep taking the derivative of both sides, and then whenever we come across a y, we're going to multiply by the derivative of y using the chain rule, which is dy dx. Let's look at another. Let's say we have xy plus x over y equals y times the square root of 2x plus 1. One thing that's going to help us make this derivative a little easier is the x over y. We can rewrite that y with a negative exponent. So we can just use the product rule instead of the quotient rule, which is much simpler. Also, the square root. The easiest way to take a derivative with the square root is to change that to a fractional exponent of 1/2. And then we can just use our exponent rules. So let's rewrite this problem as xy plus xy to the negative 1 equals y times 2x plus 1 to the 1/2 power. Now, we're going to have to use several product rules here, so you want to make sure you keep track of each part, because we've got a product at the beginning. Actually, let me do this in green so it stands out a little more. A product at the beginning, a product in the middle, and a product at the end, which is going to require us to use the chain rule. So the first product, x times y, derivative of the first, the derivative of x is 1 times y, plus the derivative of the second, the derivative of y is dy dx, times the first, which is x, plus the derivative of x is 1 times the second, y to the negative 1, plus the derivative of the second, the derivative of y to the negative 1. We bring the negative out front, so instead of plus, we actually have minus y to the negative 2 times dy dx, because we were taking a derivative with y, times the first, which is x, equals, we have another product. The derivative of the first part, the derivative of y is dy dx, times the second part, which is 2x plus 1 to the 1/2, plus the derivative of the second part, which is 1/2 times 2x plus 1 to the negative 1/2. But now we have to use our chain rule, because the derivative of the 2x plus 1, the inside stuff, is 2. Now we can multiply by the derivative, by the first part. Looking at this ugly thing that we have, a couple things to simplify. We've got a times 2 and a divide by 2. Those are going to reduce out, which is nice, so we don't have to deal with the fraction. Other than that, what we're going to want to do is get all of these dy dx terms. There's one right here, dy dx times x. We've got a negative y to the negative 2, dy dx times x. And we've also got a dy dx multiplied by the 2x plus 1 to the 1/2. let's move all the dy dx's to the right and everything else to the left. So on the left, we've still got the y plus y to the negative 1. And then we'll subtract out that term at the end, the 2x plus 1 to the negative 1/2 times y. And I'm just going to put that y in front. Equals, we've got a dy dx multiplied by the 2x plus 1 to the 1/2. We have to also subtract off the dy dx, which is multiplied by the x. And we're also going to add, to get rid of the minus, a y to the negative 2x times dy dx. Now that we've got the dy dx's on the right, the everything else on the left, we can factor out the dy dx, which leaves us with 2x plus 1 to the 1/2 minus x plus y to the negative 2x. The other side's unchanged. Y plus y to the negative 1 minus y times 2x plus 1 to the negative 1/2. That's a terrible 2. There we go. And then finally, we get the dy dx alone by dividing both sides by what it's multiplied by, giving us y plus y to the negative 1 minus y times 2x plus 1 to the negative 1/2 all over the 2x plus 1 to the 1/2 minus x plus y to the negative 2 times x. And now we have implicitly found our derivative. Keeping along with this same idea, I want to add to it a little twist, something we're very familiar with. And that is finding the equation of the tangent line. So that equation of the tangent line, same idea. Let's start with x cubed y plus 5x squared y equals negative 28. And we're going to find the equation of the tangent line at the point 2, comma, negative 1. First, we need to find the slope of the tangent line, and then it's going to be really easy to find the actual equation. To find the slope, we take the derivative. We've got a couple products. We're getting really good at the product rule here. So we've got 3x squared times y plus the derivative of y is dy dx times the x cubed plus, for the second product, the derivative of the first part is 10x times the y, plus the derivative of the second, which is a dy dx, times the first part, which is 5x squared, equals the derivative of negative 28 is just 0. Now solving for the dy dx's, they're all on one side, which is nice. So we just need to get rid of the other stuff. So we've got a dy dx times x cubed plus a dy dx times 5x squared is equal to negative 3x squared y minus 10xy, moving those things without dy dx to the other side, so that we can factor out the dy dx, leaving behind x cubed plus 5x squared equals the negative 3x squared y minus 10xy. Now we can divide by what dy dx is multiplied by. So we know that dy dx is equal to negative 3x squared y minus 10xy over the x cubed plus 5x squared. We want that derivative at the point 2 comma negative 1. So we'll plug 2 in for all of these x's. We'll plug negative 1 in for the y's. So we have negative 3 times x, which is 2 squared, times y, which is negative 1, minus 10 times x, which is 2, times y, which is negative 1, all over x cubed. X is 2 cubed, plus 5x squared, which is 2 squared. And this is not too bad to plug in to our handy-dandy calculators. Let's just do the numerator and the denominator so it's a fraction and it looks kind of slope-esque. We've got negative 3 times 2 squared times negative 1 minus 10 times 2 times negative 1. So the numerator is 32 over our denominator, which is 2 cubed plus 5 times 2 squared, which is 28. Both of those are divisible by 4. 32 divided by 4 is 8, and 28 divided by 4 is 7. So 8/7 is equal to our slope at the point 2 comma negative 1. So the equation of the tangent line, y equals m, my slope 8/7, times x minus x1, which is 2, plus the y1, which is negative 1, the equation of our tangent line of this ugly function is 8/7 x minus 2 minus 1. Let's do one more example. It's got a trig function in it. Number 2. Cosine of xy equals y. And we're going to find the equation of the tangent line at pi over 3 comma 1. We'll do this implicitly because it's almost impossible to solve for y. At least it would be quite tedious. So the derivative of cosine is negative sine of xy. Using the chain rule, we multiply by the derivative of what's inside. We want to make sure we multiply by the entire derivative. And because we have to use the product rule, there's going to be a plus. So I'm going to put this in parentheses to remind me to distribute the negative sign through the parentheses. The derivative of x is just 1 times the y, which is y, plus the derivative of y is our dy dx times the x. And that's equal to the derivative of y, which we know is dy dx. We want to solve for the dy dx. We first have to get it out of the parentheses, so we're going to distribute that negative sine xy through. That gives us negative y sine of xy minus x sine of xy times dy dx equals dy dx. We want to get the dy dx's all on the same side, so we'll add that x sine xy to both sides, giving us negative y sine of xy equals dy dx plus x sine of xy dy dx. Once they're all on one side, we can factor out dy dx, leaving behind a 1. Don't forget the 1. It doesn't just disappear. Plus x sine of xy, still equal to negative y sine of xy. Finally, to get the dy dx alone, we divide both sides by what it's multiplied to get our final derivative, negative y sine of xy, divided by 1 plus x sine of xy equals dy dx. We want the slope, though, or we want the equation, at pi over 3 comma 1. So let's plug that into our function. We got negative y, which is negative 1, times the sine of x times y. 1 times pi over 3 is just pi over 3. All over 1 plus x, which is pi over 3, times the sine of xy, which is pi over 3. And if we remember our unit circle, pi over 3, the y-coordinate there is the square root of 3 over 2. So we have negative root 3 over 2 over 1 plus pi over 3 times, again, the sine of pi over 3 is root 3 over 2. And I don't like having those fractions and fractions, so let's clear out those fractions and fractions. We've got a common denominator of 6. I'm going to multiply by 6 and distribute that 6 through. 6 over 2 will reduce to 3. So we have negative 3 root 3 over 6 plus 3 times 2 is 6, which will reduce to the 6. So that's pi root 3. And it looks weird and ugly, but sure enough, it is our derivative. So we have y equals our slope, which is negative 3 root 3 over 6 plus pi root 3 times x minus the x-coordinate, which is pi over 3, plus our y-coordinate, which is 1. And this is the equation of the line that is tangent to cosine xy equals y. So that's implicit differentiation. The idea behind implicit differentiation is that we just take the derivative of both sides of the equation, using the chain rule, knowing that the derivative of y is dy dx, because y is a function of x. It's not just a variable. It is a function of x. So we use our chain rule and multiply by the derivative of y. Then we just have to solve the resulting equation for dy dx. Looking forward to seeing you in class when we can work on this a little bit more. Give yourself some time to practice before then, and we'll see you in class. There is one more set of functions that we haven't taken a look at how to find the derivative of. So we're going to attempt to answer that question today, is how do we find the derivative of exponential and logarithmic functions? And we'll break that up into two halves. Once we'll talk about the exponentials, and then we'll come back and talk about the logarithmic functions. So first, exponential functions. Some important formulas that will help us take derivative. The nicest derivative formula of all, and it's also the most interesting, is that the derivative of e to the x, the slope of the tangent line to e to the x at e to the x, is actually exactly e to the x. which is kind of weird when you think about it. But if our base is not e to the x, it turns out the derivative of any base to the x is that base to the x times the natural log of the base, which just so happens that the natural log of e is just 1. So we end up with two formulas that could be condensed into one. But since we use e to the x so often, we'll give it its own little formula. But these two formulas are going to be what guide us here as we go into the first part of this video. So let's take a look at some examples of taking derivatives with exponentials. Let's say f of x equals e to the cosine of x squared. What we really have here is just a really big chain rule problem. It's a 3-level chain rule, but we can do that. F prime of x is equal to the derivative of the outside, and the derivative of e to the x is e to the stuff, e to the cosine of x squared, times the derivative of the inside stuff. And so the derivative of cosine is negative sine of the stuff, times the derivative of the inside stuff. And the derivative of x squared is just 2x. Cleaning this up a little bit, putting the negative and 2x out front, we'll put the sine of x squared next, and then the e to the cosine of x squared after that, just so that it looks a little nicer. But that way, we found our derivative, which contained in e to the x. We could even expand this into any of our rules or patterns that we've seen thus far. So what if we did a quotient rule? F of x is equal to e to the 3x minus 7 all over x squared plus 5x. Well, we should be very comfortable with the quotient rule by now. So we take the derivative of the top, which is e to the 3x minus 7, because the derivative of e to something is e to that something. But we have to multiply by the derivative of the inside, which is just 3. And then we have to multiply by the denominator, x squared plus 5x. Then we subtract the derivative of the denominator, which is 2x plus 5, times the numerator, which is e to the 3x minus 7. And that's all over the denominator squared, x squared plus 5x squared. Not a lot to clean up in there. So after using our quotient rule and the exponent rule, we'll call that our derivative. Let's do one more, one that doesn't use a base of e to the x, but uses some different base. So let's try f of x equals 4 to the x times 5 to the x minus x. We could distribute the 4 to the x through, and then we don't have to use the product rule. Well, we still would, but let's just keep it the way it is. F prime of x is equal to, and we'll use the product rule here. The derivative of the first part, the derivative of 4 to the x, is 4 to the x. But if the base is not e, we need to multiply by the natural log of the base. Then times the second part, 5 to the x minus 1. Plus the derivative of the second part. Well, the derivative of an exponential is the exponential times the natural log of the base minus the derivative of x is 1 times the first part, which is just 4 to the x. And there's not really much that cleans up in this example either. And so we end up with our solution. So basically, all we're doing is we're expanding our repertoire of derivatives to include these two exponential formulas. The derivative of anything is the derivative of the exponential is the exponential times the natural log of the base. If it's e to the x, it's really nice because the derivative of e to the x is just e to the x. We can use the fact that the exponential derivative is so simple to derive and create the derivative of the logarithmic. If I can spell it right. Logarithmic functions. And the way we get the derivative of the logarithmic functions is we use implicit differentiation. Because we know that if y equals the natural log of x, we can rewrite this as e to the y equals x, because the base is e, the exponent is y. And then if we take the derivative of both sides of this guy using implicit differentiation, the derivative of e to the y is e to the y dy dx equals the derivative of x is 1. Dividing both sides by e to the y, we get the derivative dy dx is equal to 1 over e to the y. But the good news is that we know what y equals. Y is equal to the natural log of x. So we have 1 over e to the natural log of x. But e and the natural log with the same base are inverses, so that leaves us with just the x. And so we find out that dy dx is equal to 1 over x. Kind of neat how the formula comes out. So we've got our formulas for the logarithms. The derivative of the natural log of x, we just found out, is simply 1 over x. If the base isn't a base e, though, we can do the derivative of any log base b of x. Doing just a simple change of base formula, we end up with 1 over x natural log of b. And these two formulas allow us to take the derivatives with logarithms. 2 more formulas to add to our derivative repertoire. And so we should be able to solve a whole bunch of examples using all the other derivative rules we've seen, but now throwing in some logarithms. If f of x equals the natural log of the tangent of x squared minus 5x, what we really have is derivatives inside of derivatives inside of derivatives. So that f prime of x equals, using the chain rule, natural log, the derivative of that is 1 over the stuff. 1 over the tangent of x squared minus 5x times the derivative of the inside. Well, the derivative of tangent is secant squared of the stuff, x squared minus 5x, times the derivative of the inside, which is the x squared minus 5x. The derivative there is 2x minus 5. And all there is to do is clean that up nicely. All that stuff multiplied ends up in the numerator. And so we get this nice derivative, secant squared of x squared minus 5x times the 2x minus 5 all over the tangent of x squared minus 5x. Let's try one with a log that's got a different base. Let's say f of x is equal to the log base 7 of 2x minus 5 times the cosine of 5x. Here we have the product rule again. So we'll take the derivative of the first. The derivative of log base 7 is 1 over the stuff. The 2x minus 5. And because it's not a base e, we have to multiply by the natural log of the base, or the natural log of 7, times the second part. Actually, before we get to the second part, we still need to multiply by the derivative of the inside, which is just 2, times the second part, which is cosine of 5x, plus the derivative of the second part. The derivative of cosine is negative sine. So let's change that to negative sine of 5x, times the derivative of the inside, which is 5. And we still have to, using the product rule, multiply by the first part, which is log base 7 of 2x minus 5. Just want to clean it up a little bit. Not much to clean up, but we'll definitely make it easier on the eyes. We'll combine the fraction together. So we have 2 cosine of 5x over 2x minus 5, natural log of 7, minus, we'll put the 5 out front, sine of 5x, log base 7 of 2x minus 5. And we have our derivative. One nice thing that comes out of working with logarithms and derivatives is that logs have some nice properties that help us simplify out to something that is very simple to take the derivative of. For example, if we were given f of x equals the natural log of x to the 4th cosine of x divided by the square root of x plus 3. That looks very ugly to take the derivative of. However, we can break this up into 3 separate logarithms, one for each factor. The logarithm from the denominator is going to be negative, and then we can also pull exponents out in front of logarithms. So what we really have here, rewriting the function, is the natural log of x to the 4th, but the 4 moves out front, plus the natural log of the cosine of x, minus the natural log of the x plus 3, and then the 1/2 power can move out front. Now we've got something that's much easier to work with, much easier to take the derivative of. F prime of x is equal to, we've got a constant of 4, times the derivative of the natural log of x, which is just 1 over x, plus the natural log means the derivative is 1 over that, so 1 over cosine of x, times the derivative of the inside, which is negative sine of x. We'll just stick that in the numerator, minus 1/2. That's a constant, so that's going to be out front. And the derivative of the natural log is 1 over the stuff, x plus 3, times the derivative of the inside, which is just 1. And we can clean this up a little bit even, so that it's equal to 4 over x. We'll just say minus instead of plus a negative. And sine over cosine we should recognize. Sine over cosine is the tangent, minus 1 over Yeah, we could distribute if we want. 2x plus 6. Don't have to distribute, but why not? And we get this nice derivative. So that's one nice thing that comes out of derivatives with logarithms is quite often logarithms help us break the problem down where it started complex. What we end up with is quite simple to take the logarithm of. Another nice trick that comes out of this is what we call logarithmic differentiation. Which we use when the variable, we'll say x, but the variable is in both the exponent and base. And the most classic example of that is if y equals x to the x power. Here, we can't really take the derivative because we could use the exponent rule, but that doesn't work because we don't know what x is. We don't know how to do the base. We're kind of stuck until we get this nice trick called logarithmic differentiation, where we take the natural log of both sides. And when we do, we get the natural log of y equals the natural log of x to the x power, which allows us to use the log property. The log property says the natural log of x to the n is equal to n times the natural log of x. We can move that exponent out front. So now we have the natural log of y equals x times the natural log of x. Now we can take the derivative, but because this has the natural log of y on both sides, we have to do implicit differentiation. The derivative of the natural log of y is 1 over y dy dx. The derivative of x, natural log of x, that's a product rule. We'll always end up with a product rule here. The derivative of x is 1 times the natural log of x, plus the derivative of natural log of x is 1 over x times the first, which is just x. But x over x is just equal to 1, which is really nice. Then what we need to do is solve for the dy dx. We know implicit differentiation. And it always turns out to do that, we multiply by y. With implicit differentiation, this step's always the same because you'll always have 1 over y. I'm sorry, not with implicit differentiation. With logarithmic differentiation, this step is always the same because you'll always have 1 over y on the right. So we'll multiply both sides by y, giving us dy dx is equal to the natural log of x plus 1 times y. So all that's left to do then is to substitute y from the original function. Y is equal to x to the x. So dy dx is equal to, and I'll just put the y in front, x to the x times the natural log of x plus 1. And now we've got our derivative. We can use this process, though, to solve things that are much more complex than x to the x. We'll use this process of taking the log of both sides and then the derivative implicitly to solve things more complex that might look something like this. Y equals 3x squared minus 5x, all to the sine of x power. We have x both in the base and in the exponent. When it occurs in both places, we take the natural log of both sides. The natural log of 3x squared minus 5x to the sine of x. Whoops, lost my n. Not to the 6, to the sine of x. Let's clean that up. Now we have our log property that says that exponent can come out front. So we know the natural log of y is equal to the sine of x times the natural log of 3x squared minus 5x. Then we can take the derivative implicitly. On the left, the derivative of the natural log of y is 1 over y times our dy dx is equal to, we have a product rule here. The derivative of sine is cosine x times the natural log of 3x squared minus 5x plus the derivative of the second part. The derivative of natural log is 1 over the stuff, 3x squared minus 5x, times the derivative of the inside. That'll go in the numerator, 6x minus 5, times the first part, the sine of x. Now we can solve for the dy dx by multiplying both sides by y. And that tells us that dy dx is equal to the cosine x natural log of 3x squared minus 5x plus 6x minus 5 times the sine of x all over 3x squared minus 5x times y. But we know what y equals. Y is equal to the original problem. So dy dx is equal to the cosine of x times the natural log of 3x squared minus 5x plus 6x minus 5 sine of x divided by 3x squared minus 5x times our original problem, which was 3x squared minus 5x, all to the sine of x power. And logarithms take that which once was impossible, now very possible and straightforward. So we've kind of done three things today. We talked about the derivatives of the exponential, specifically e to the x is e to the x. We talked about the derivatives of the logarithms. The derivative of the natural log is 1 over x, or 1 over the stuff. And then we talked about doing logarithmic differentiation, to take problems that would otherwise be impossible to take derivatives of, change their form so that we can use logarithmic differentiation to find our derivative. A couple things to practice with. Take a look at those, and we will see you in class to work on them further. This video is going to take a look at a preview of working in 2 dimensions and 3 dimensions and taking derivatives. Thus far, we've only taken derivatives in the x direction, where we've got a coordinate plane in 2 dimensions. But we can extend that to a 3-dimensional coordinate plane and still work with derivatives. The trick is we have to decide what direction we're going in. So the question is going to be, how do we calculate derivatives in 3D? Now, a 3D function, generally a 2D function is f of x. We've done a lot of work with that because we just take the derivative with response to f of x, with respect to x. But a 3-dimensional function will have variables x and y in them to result in a z variable that's a solution. So these are still a function. We've just got multiple variables inside the function. And the way we take those derivatives is we take what is called a partial derivative. Or a derivative or rate of change in a specific direction. In other words, are we going left and right? Are we going forwards and backwards? How far are we changing in each of these two directions? And so to specify that we're just taking a derivative partially in one direction, we've got a special notation to indicate this. You will see what we call the partial derivative of f with respect to x. And I'll even write that. That's the partial derivative in the x direction. And you might think about that as the left-right direction, loosely. And it's kind of this funky df dx that we saw before, but now because it's got this curved looking d, that notation should tell us we're talking about a partial derivative in the x direction. And similarly, you'll see a partial derivative with respect to y. That's the partial derivative in the y direction, or how fast we're changing in the y direction, which you might think of loosely as the up-down direction. And by up-down, I mean if I'm looking down at a piece of paper away from me and towards me, up-down, or left-right would be the other two directions. So how are we changing left and right? How are we changing horizontally as we've got a partial change of the function? And the way we actually calculate a partial derivative is we treat all other variables as constants. So, for example, let's say we've got f of xy is equal to 3x squared y to the fourth. And if I wanted to calculate the partial of f with respect to x in the x direction, we're going to take the derivative with respect to x, and we're going to pretend the y is a constant. So the derivative of 3x squared is 6x, and the y to the fourth is a constant. So it's going to kind of hang out like constants do when they're multiplied by our x. I could also take the derivative of this same function with respect to the y. In that case, we take the derivative of the y, which is y cubed. And then we bring the 4 out front. 4 times 3 is 12. And we keep the x squared as if it was a constant, as if it was part of the 3. Really important here to note, though, that the notation and process is different than implicit differentiation. Implicit differentiation used that whole dy dx. With dy dx, y was a function of x in 2 dimensions. Y was f of x. Now we've got a 3-dimensional function that has x's and y's in the function, but these are functions. These pass the vertical line test, or in 3 dimensions, the vertical plane test. With implicit differentiation, we took the derivative of y as if it was a function of x and then multiplied by its derivative dy dx. That is different than partial derivatives, where we're just going in the x direction in 3 dimensions, and the y is treated like a constant. Or we're going in the y direction, and the x is treated as a constant. Be careful not to mix these two processes, because they are very different. So let's try a few examples, though, where we have to take a bunch of partials. What's nice about these partial derivatives is it's a great place for us to synthesize all the derivative rules that we have seen up to this point and see how we do. So let's first take a function in x and y. Let's call it 5x squared minus 7xy. Minus 9y to the 5th plus 2x minus 7y plus 3. And first we'll find the partial of f with respect to x. So we're going to pretend like all the y's are constants as we take the derivative with respect to x. So our first term, we know that's 10x, minus the derivative of x is 1, so we're just left with the constants, 7 and y. The 9y to the 5th, those are all constants, and the derivative of just a constant is 0, so that term's gone. 2x, the derivative of that is just 2. Again, the 7y, all constant. The 3, constant. Therefore, those derivatives are also 0. And so our partial derivative of f with respect to x is 10x minus 7y plus 2. We can also take the partial derivative of f with respect to the y. With respect to the y, the 5x squared is now a constant, so that's 0. Negative 7xy, the derivative of the y is 1, so we're just left with the constant 7x. The derivative of negative 9y to the 5th is negative 45y to the 4th, bringing that 5 out front and dropping the exponent by 1. 2x, it's all constant. The derivative of negative 7y is negative 7. And 3 is also a constant, so that derivative is 0. And now we've got our partial derivatives with respect to x and the partial derivative with respect to y. Let's try another one. We'll increase in complexity here, making these more interesting. The function of f with respect to x and y. The function of f with x and y as variables is the secant of x to the 4th y plus 7x minus 4y. And now the partial of f with respect to x. Here we've got a chain rule set up. We've got a secant of stuff. The derivative of secant is secant tangent of the stuff. So the secant of x to the 4th y plus 7x minus 4y tangent of the stuff, which is x to the 4th y plus 7x minus 4y, times the derivative of the stuff inside it with respect to x. So the x to the 4th becomes 4x cubed with the constant of y still there, plus the derivative of 7x is just 7. Negative 4y, those are all constants because we treat the y as a constant. So it's 0. And now we've got our partial derivative of f with respect to x. Let's try the partial derivative of f with respect to y. Very similar. Chain rule again. The derivative of secant is still the secant tangent of the stuff. So we have the secant of x to the 4th y plus 7x minus 4y tangent of x to the 4th y plus 7x minus 4y times the derivative of the inside stuff with respect to y. So now with the x to the fourth y, the derivative of y is just 1, so we're left with the constant x to the fourth. 7x doesn't have any y's on it, so that goes to 0. And the derivative of negative 4y is negative 4. And now we've got the derivative, the partial derivative, with respect to y. Let's make this a little more interesting. Let's say f is a function of x and y, which is equal to e to the xy cosine of 2x sine of 3y. And if we want the partial of f with respect to x. Here we've got a product. With respect to x, the sine of 3y is a constant. So really the only product is e to the xy times the cosine of 2x. And then we will have that constant out in front. So I'm just going to go ahead and write that constant in front. The sine of 3y times the derivative of e to the xy is e to the xy times the derivative of the inside with respect to x is just y times the second part, which is the cosine of 2x, plus the derivative of the second part. The derivative of cosine is negative sine. So let's make that negative sine of 2x times the derivative of the inside, which is 2. And let's go ahead and put that 2 actually in front of the sign, just to keep it clean. Times the other part, e to the xy. And we've got our partial derivative with respect to x. Let's also do the partial derivative of f with respect to y. Very similarly, but this time, notice the factor of cosine of 2x does not have any y's on it. That is a constant that's being multiplied by stuff with y's. So that constant we'll put out front, cosine of 2x, times the derivative of the product. So our product is multiplying e to the xy times the sine of 3y. So we'll take the derivative of the first times the second, plus the derivative of the second times the first, all the partial with respect to y. So the derivative of e to the xy is e to the xy times the derivative of the inside. The derivative of xy with respect to y is just x, times the second part, which is the sine of 3y, plus the derivative of the second part. The derivative of sine is the cosine of 3y, times the derivative of the inside, which is a 3, times the first part, e to the xy. And we have our derivative. Let's try one last example. F is a function of x and y. It's equal to the tangent of x to the fourth, y to the third, times the natural log of 5 over xy. Now, something to make life easier, you should be very good at picking up now. When we see a fraction like 5 over xy, we can think about that as 5x to the negative 1, y to the negative 1. Because that's going to be easier to take the derivative of. So as we take the derivative, that's the natural log of 5x to the negative 1, y to the negative 1. And first, we're going to do the partial derivative of f with respect to x. And again, we have a product rule. And each product part is going to be a chain rule. So there's going to be a couple pieces to this one. First, the derivative of the first times the second. The derivative of tangent is secant squared of the stuff. And then we multiply by the derivative of the inside with respect to x. So the derivative of x to the fourth is 4x cubed. And the y cubed is a constant. Times the natural log of 5x to the negative 1, y to the negative 1. Plus the derivative of the second. The derivative of natural log is 1 over the stuff, 5x to the negative 1, y to the negative 1, times the derivative of the inside with respect to x, which is going to be negative 5x to the negative 2, bringing the negative 1 out front, subtracting 1, and the y to the negative 1 is a constant, times the tangent of x to the fourth y cubed times the first part. A little bit to clean up. Let's move the 4x cubed y cubed to the front. Also, the 5 over 5 reduces out. The y to the negative 1s reduce out, which is really nice. And so we're just left with an x to the, when I move the negative 2 down, it's going to be just a negative or a positive 1 left over. So cleaning that up, we get 4x cubed y cubed secant squared of x to the fourth y cubed natural log of, let's go ahead and make this a fraction, 5 over xy plus, we've got the tangent of x cubed, or I'm sorry, x to the fourth y cubed. And all that's left from that ugly fraction we crossed everything out is just an x in the denominator. And now we've got our partial derivative with respect to x. Let's do the partial derivative with respect to y. It's going to be very similar because x and y appear in very similar locations. But just to walk through it together, product rule again. So first, the derivative of tangent is secant squared of the stuff, x to the fourth y cubed, times the derivative of the inside, this time with respect to y. In the y direction is 3y squared. And the x to the fourth is a constant, times the second part, which is the natural log of, I'll just leave it as 5 over xy, plus the derivative of the second part, which is natural log, is 1 over the stuff, 1 over 5x to the negative 1, y to the negative 1, times the derivative of the inside, which is going to be y to the negative 2 with a negative 5 and an x to the negative 1, because an x is a constant, times the first part, which is tangent of x to the fourth y cubed. The cleanup is very similar. We'll move the 3x to the fourth y squared to the front. The 5s are going to divide out, which is nice. Oops, I just saw an error that I missed earlier. We had a minus, and my minus disappeared. That should have been a minus on number 4. I apologize for that. Don't lose your signs. But the x to the negative 1s do divide out. And when we bring the y down, we'll just be left with a single y in the denominator. So for our cleaned up version, we have 3x to the fourth y squared, secant squared of x to the fourth y cubed, natural log of 5 over xy, minus, because of the minus sign, not forgetting it this time, we'll put the tangent of x to the fourth y cubed in the numerator, And in the denominator, all that's left is a single y. And we have our partial derivative with respect to y. The homework assignment with partial derivatives is really short, but they are going to force you to review all of these derivative properties we've worked with here in Chapter 3, which is what makes it such a great assignment. So take a look at it, give it a good practice, and then we will see you in class to discuss these partial derivatives in a little more detail. Chapter 4 is going to take a look at how we can use the derivative in various contexts and applications. The first one is what are called related rates. And so our question we're going to answer is, how are rates of change that's a derivative, a rate of change, how are they related to each other? And this is what brings up this idea of related rates. And basically, a related rate means two things are changing, but they're changing in relationship to one another. One increases at a certain rate, and it makes the other one increase or decrease at a certain rate. The best example of this is if you think about filling up a balloon. Let's say if we have a spherical balloon that is filled with air at a rate of 3 cubic inches per second. We want to know how fast is the radius changing. When the radius is 4 inches. As we solve these related rate problems, the radius of the balloon is related to the amount of air in it. As we solve these problems, we're going to go through kind of a 4-step process. The first step is going to be to draw a picture with the related formulas. So we're talking here about a sphere. So we'll draw our little spherical balloon here. And the radius of r. And we're talking specifically about the volume, or how much stuff is in this circle. And we can look up, or we might know the formula for the volume of a sphere is 4/3 pi times the radius cubed. Once we know that relationship, we're ready for the second step, which is to take the derivative with respect to time. So if I were to take the derivative of this guy, we're going to have to use implicit differentiation because time t is not a variable here. So v, the derivative of v is just 1 dv dt, is equal to, and 4/3 and pi are constants. And we know we can use our exponent rule on the 3, bringing the 3 out front and reducing it by 1, so r squared. And then times the derivative of r, which is dr dt. This one's kind of nice because the 3's are going to divide out. So we really say dv dt is equal to 4 pi r squared dr dt. And now that we have our derivative with respect to time, let's plug in what we know. And I can't quite fit it all on the screen, so hopefully you have it on your notes. We're going to plug in what we know. And what we know is that the volume is increasing at a rate of 3 cubic inches per second. That is the change in volume with respect to time. We also know that the radius is currently 4 inches. It's not changing with respect to time. It's at this moment exactly 4 inches. So when we come down to plug in dv dt, the volume is changing at a rate of 3 cubic inches, equals 4 pi r, the radius we said was 4 inches, squared dr dt. And then all we have to do is solve for the remaining rate, or dr dt, the change in the rate with respect to time. So simplifying, 4 squared is 16, times 4 is 64 pi dr dt. And then we can get the dr dt, or the change in the radius with respect to time. How fast is that radius changing? By dividing 3 by the 64 pi. And then we have 3 over 64 pi inches per second is the rate that radius is changing when it's exactly 4 inches long and the volume is increasing at 3 cubic inches per second. Let's try another related rate problem. Let's say we have a 7-foot ladder that is sliding down the wall. And we know that the top is sliding down at a rate of 1.5 feet per second. We want to know how fast is the bottom moving along the ground. When the bottom is 6 feet from the wall. Let's draw a picture to get a better idea of this. We've got a building, the ground, and there is this ladder that's leaning against them. The problem is that ladder is sliding down the wall at a rate of 1.5 feet per second. We know the ladder itself is 7 feet long. And the moment we're interested in is the fact that we are 6 feet from the wall. And if we call this other side A, we don't know what A is, but we're going to be able to find that pretty quick. The big thing, though, that we know that the formula for any right triangle is that a squared plus b squared equals c squared. And we can take the derivative of this with respect to time. We have 2a times the change in a with respect to time, or dA dt, plus 2b dB dt equals 2c dC dt. Then let's go ahead and plug in what we know and see what we come up with. We can actually figure out how long a is using the same Pythagorean theorem. 7 squared is equal to 6 squared plus a squared, or a squared plus 6 squared equals 7 squared. A squared is 36. A squared plus 36 equals 49. So a squared is equal to 13. A is the square root of 13. So at this moment, up the wall, we're the square root of 13 high. So plugging that into the formula, we have 2 times a, which is the square root of 13, times the change in a with respect to time. We know that a is going down, so we're going to say it's negative to represent the downward motion. And it's moving down at a rate, the change with respect to time is negative 1.5. Plus 2b, b is the bottom of 6, times the change in b with respect to time. And we don't know how fast this ladder is moving out. That's what we're looking for, the dB dt. Equals 2c. c is 7 feet. But how fast is c, the ladder's length, changing? Well, if we think about a ladder sliding down a wall, that ladder's not changing length at all. It's always going to be 7 feet long, whether it's completely against the wall, completely against the ground, or anywhere in between. There's no change in the ladder's length, so we'll use 0 for that length. When we clean this up, then, we end up with negative 3 square root of 13 plus 12 dB dt equals 0. And this is going to solve quite nicely for us. Add the 3 root 13 to both sides. We get 12 dB dt equals 3 square roots of 13. Divide both sides by 12. And the change in b of the base with respect to time is equal to 3 root 13 over 12. And what's nice is the 3 over 12 reduce. So for our final rate, this ladder is moving square root of 13 over 4 feet per second when the ladder is 6 feet from the wall. Let's try another example. Let's say a camera is 2,000 feet from a rocket that fires vertically. And when this rocket is 500 feet in the air, its velocity, that means speed, but with direction, is 400 feet per second. The cameraman needs to know what is the needed rate of change of the angle of the camera. Let's draw a picture to kind of get an idea of what's going on. We've got a little camera here. That's my camera, which is 2,000 feet away from the launch point for a rocket. That's my little rocket. It's going to go up in the air. And the camera's going to change angles so that it can watch that rocket no matter how high it gets. We need to come up with an equation that relates these variables. Well, since we're dealing with an angle and the sides opposite and adjacent, we should know that the tangent of that angle is equal to the height over the 2,000 feet, the opposite over the adjacent. Then we can take the derivative of that. Actually, let's save ourselves a little bit of work. Before we take the derivative, let's multiply both sides by 2,000 so we don't have to worry about the fraction. It's just a constant, so it's not going to make much difference. Now let's take the derivative of that. And the derivative is going to be 2,000 secant squared of theta with respect to time. So we have to say dt d theta, using that implicit differentiation, equals the derivative of the height is dh dt. So now we can plug in what we know. First, we need to figure out what secant squared of theta is. Secant of theta, you remember, is 1 over the cosine of theta, or the reciprocal of cosine. If cosine is adjacent over hypotenuse, the secant is the hypotenuse over the adjacent, the reciprocal. We already know the adjacent side is 2,000. We just need to find the hypotenuse side. We're interested in the moment where the height is 500 feet. Fortunately, the quadratic formula can tell us that 2,000 squared plus 500 squared is going to be equal to c squared. If I were to do that on my calculator, we would get 425 with 4 zeros after it equals c squared. And so if I take the square root, c is approximately equal to 2061.55. So 2061.55. So plugging in what we have, we've got 2,000 times the secant, which is the hypotenuse, 2061.55, over the adjacent, which is 2,000, squared. Oops, I just realized I got a small error up here. It should be d theta dt. We're taking the respect to time. The change in the angle with respect to time is what we're solving for. The change in the height, we know the height is increasing at 400 feet per second. The change in the height is 400 feet per second. Then we start multiplying this out. We will do the 2,000 times 2061.55 over 2,000 squared. When I do all of that, I get 2125 approximately d theta dt equals the 400. So the change in the angle with respect to time after I divide is 400 over 2125. Which, if I divide that, I get 0.1882 radians per second. So when this rocket is 500 feet in the air, the camera needs to be changing its angle at 0.1882 radians per second. Let's do one last example of these related rates. Finding an equation that relates the rates, taking a derivative with respect to time, plugging in what we know, and solving. Let's say I have a funnel, and water is draining from it. Water is draining from a cone-shaped funnel at a rate of 0.25 cubic feet per second. The height of the funnel is 3 feet. And the radius at the top is 2 feet. But we're not interested in the funnel. We want to know about the water. At what rate is the height of the water changing? When the height is 1 foot. Well, let's draw a picture of our funnel. Here's our funnel. Water's leaking out. It's not full, though, so here's the water level. The funnel itself, we know, is 3 feet high. The radius on the funnel is 2 feet. That's a constant, so we'll label those constants. We know water is coming out at 0.025 feet per second. So we'll call that negative 0.25 feet per second. Cubic feet per second. It's a volume. And we're interested specifically in the water. We don't really know the radius and the height because that's going to change. Those aren't constant. But what we do know is an equation about the volume of that water. You might have to look it up, or we might know that the volume of a cone is 1/3 pi r squared times the height. The problem we have is we end up with 3 variables. And so if we were to take the derivative, we'd have 3 rates of change: the change in the height, the change in the radius, and the change in the volume. We want to reduce that down to 2. So it's a little more manageable. Fortunately, if we were to draw a line down the middle, you see we end up with triangles that make up kind of the right side. A big triangle with a height of 3 and a length of 2, and a small triangle with a height of h and a radius of r. Those triangles, because they both have a right angle and share an angle, are similar triangles, so their sides must be proportional. In other words, if we set up the radius divided by the height on the little triangle, it would be the same on the big triangle, a radius of 2 divided by the height of 3. And we can solve this for r really quickly by multiplying by h. r is equal to 2h over 3. And so let's plug that in to our radius. That's going to reduce out the radius variable because we really don't care about the radius. We care about the height. And we care about the volume of the water decreasing. We've got height and we've got volume. We do not have anything about the radius. So let's stick with that pattern. So our volume is 1/3 pi times the radius, which is 2h over 3 squared, times h. And actually, let's go ahead and simplify that. We got 1/3 pi times 2 squared is 4. H squared over 3 squared is 9, times the height. And so our final formula that connects the variables of the height and the volume, oops, not 1/3. Let's multiply. 1 times 4 is 4. 3 times 9 is 27. So we've got 4 pi over 27 times the height cubed. Now that we have our formula connecting our variables, we'll take the derivative. The derivative of v is 1 dv dt, the change in the volume with respect to time. 4 pi over 27 is a constant, but the derivative of h cubed is h squared with the 3 out front times dh dt. Let's go ahead and simplify. 3 over 27 is 9. So dv dt is equal to 4 pi over 9 h squared dh dt. Let's come over here to the side and plug in what we know. dv dt, that's the change in the volume with respect to time. We said the volume was decreasing at 0.25 cubic feet per second. Decreasing, so it's negative 0.25 is equal to 4 pi over 9. The height at the moment we care about, is 1 feet. So we're going to put 1 in for our height at the moment we care about, squared. dh dt, that's what we're looking for, the change in the height with respect to time. So we have negative 0.25 is equal to 1 squared is 1 times 4 is 4 pi over 9 dh dt. And so to get dh dt alone, we multiply by 9 over 4 pi times the negative 0.25. And the change in height with respect to time is equal to approximately, putting that in the calculator, negative 0.17914 feet per second. In other words, at that moment, the height is decreasing by almost 0.18 feet per second. And that's how we're going to handle these related rates. We're going to take a look at drawing a picture, finding a formula that relates the variables of interest, the variables that are changing specifically. Then we'll take the derivative with respect to time implicitly. And then we'll plug in what we know and solve for what we don't know. Give a couple of those some practice on the assignment, and we will see you in class to discuss this further. Sometimes it is easier to use a derivative to approximate the value of an equation or a function than it is to actually calculate the exact value. And that's what we're going to take a look at today. The question's going to be, how do we approximate a function at a point? And to set this up, we're going to start by asking the why it works, or what's going on in the background. The why behind what we call linear approximation. To set this up, we're going to recall the equation of a tangent line. To the function f of x at the point A is y equals the y-coordinate, which is just f of a, plus the slope of the tangent line at A, which is f prime of A, times x minus the point, which is A. And what we also know is that close to the point, close to A, it is close to f of a. In other words, here's what I mean. Let's say I've got this curve here. And there's this point on the curve that we're going to call A. And we calculate this tangent line at A. And if I look at a value that is close to A, it's also going to be close to the point of the line. It's also going to be a very similar height. It's going to be close to f of a. It's off by a little bit, but that line can give us a really good estimation of what's happening close to the point A as it curves away from A. And the fact of the matter is, lines are easier than curves to calculate points. And so we're going to prefer to use that blue line that gets us close to A to calculate what's actually happening close to A. Maybe this will look better with a more concrete example. Let's take a look at example. Let's say we were trying to calculate the square root of 25.1 by hand. That would be very, very difficult because it doesn't have a perfect square root. We know it's close to 5 because the square root of 25 is 5. And that's the fact that we're going to use in order to estimate it. We know that the square root of 25.1 is close to the square root of 25. So we can consider. Let's say the function f of x is equal to the square root of x, or as we like to have it in calculus, x to the 1/2. Then f prime of x, the derivative, is 1/2 times x to the negative 1/2, or 1 over 2 square root of x. We need to know what f of 25, the easy point, and f prime of 25 is in order to estimate the not so easy point of the square root of 25.1. Well, f of 25 is the square root of 25, which we know is 5. And f prime of 25 is 1 over 2 times the square root of 25, or 1 over 2 times 5, 1/10. So if we want the linear approximation of the square root of x at 25, that's just the equation of our tangent line. The y-coordinate of 5 plus the slope, which is the derivative, 1/10, times x minus the x-coordinate, which is 25. We can use this linear equation to estimate the square root of numbers very close to 25. So we can estimate the square root of 25.1 by using x is equal to 25.1 in this equation. So the linearization at 25.1 is equal to 5 plus 1/10 times 25.1 minus 25. And if we plug that into our calculator, we will get that the answer is approximately 5.01. And so we're estimating that the square root of 25.1 is about 5.01. So I know what you're thinking. How good is that estimate? Well, let's actually find it on the calculator. We did it by hand. We're going to compare with the square root of 25.1 on our calculator. So on my calculator, I will do the square root of 25.1, and we get 5.00999. That's pretty darn close. 5.00999. It is quite close to our estimated value that we found by hand. And doing it by hand with the square root would have been a real big pain because curves are difficult to calculate. But lines are much easier to work with. And so that's this idea of linear approximation, is we're going to estimate by finding the equation of the tangent line to see what's happening really close. So let's try some examples. Let's see if we can get good at this. First example, we're going to estimate 1 over 3.1 squared. Well, the function that we seem to be working with is we're doing 1 over x squared, or x to the negative 2. And then we can make the x equal to 3. So f prime, the derivative of that is negative 2x to the negative 3, or negative 2 over x cubed. (3.1) is close to 3. So we're going to find f of 3 and f prime of 3, and then we'll see what's happening close to that. So f of 3 is equal to 1 over 3 squared, which we know is 1/9. F prime of 3 is negative 2 over 3 cubed, which is negative 2 over 27. So let's set up our linear approximation. Is equal to the y-coordinate of 1/9 plus the slope, which is negative 2 over 27, times x minus the x-coordinate. The x-coordinate is 3. We can use this to estimate 1 over x squared near the point 3. We're particularly interested in 3.1. So 1/9 minus 2 over 27 times 3.1 minus 3. And if I plug 3.1 into my calculator, we get 0.1037. So let's check it. On the calculator, what is 1 over 3.1 squared? 1 divided by 3.1 squared. Let's see how close we got. It's 0.1041. And as you can see, that is quite close. We're only off by about 0.0004. Not too bad of an estimate. Doing it by hand was much nicer than doing 3.1 squared, getting something with 2 decimal points, and then doing that long division. Much nicer. This even works with trigonometry. Let's do a trig example. Let's estimate the tangent of 44 degrees. Well, let's change that to radians first. We see that's close to 45. So we're really working with the tangent of 45 degrees. And if you remember your unit circle, 45 degrees is pi over 4. So we're looking at the tangent of pi over 4 to estimate our point. So f of x is the tangent of a value, tangent of any point. We're going to find that point. F prime, we know, is the secant squared of x. We're specifically interested in pi over 2. So f of pi over 2 is equal to the tangent. I'm sorry, not pi over 2, pi over 4. the tangent of pi over 4, we should remember, is equal to 1. And f prime of pi over 4 is the secant squared of pi over 4. If it helps to remember, secant is 1 over cosine. Cosine is the x-coordinate, root 2 over 2. The reciprocal of that is going to be, actually, I'll write down what I'm talking about here at the top. So it's 1 over the cosine of pi over 4, which is 1 over root 2 over 2, which is the reciprocal of that, 2 over the square root of 2. And if I rationalize, we get 2 root 2 over 2, which is equal to just the square root of 2. So square root of 2 is the secant, but that's squared. So it's actually equal. Square root of 2 squared is just 2. Remembering your trig from secant. How does that work? Secant of pi over 4 is equal to 2. All right, let's make our linearization equation then. L of x is equal to the y-coordinate of 1 plus the slope of 2 times x minus the x-coordinate, which is pi over 4. But we want the linearization of 44 degrees, which we have to change that 44 degrees into radians. 44 degrees. Remember, we multiply that by pi over 180. So we have 44 pi over 180 radians. There's no reason to reduce because we're going to use our calculator. So we're doing the linearization of 44 pi over 180. Is equal to 1 plus 2 times 44 pi over 180 minus pi over 4. Plugging that mess into our calculator, we get 0.9651. So that's our estimate. Let's check it with the actual value of the tangent of 44 degrees. And since our calculator is probably in radian mode, let's do the 44 pi over 180. Verify that my mode is in radians. Yes. So we've got the tangent of 44 pi divided by 180. And it equals 0.9657. 0.9657. And look how close the actual value was. It was only off by 0.0006. Only a 20th of a percent. So we have this idea that we can get close to any curve using a tangent line. And so if I move a little bit to the right, or if I move a little bit to the left, I can see what's happening kind of near that point. But it kind of begs this question. How much are we off by? How much are we changing by? This kind of leads into this concept of what we call differentials. How much are we off by? As x changes, how much does y change in relationship to x? Is there a relationship there? A differential is really just the amount a function changes. As a result of a small change, I'm going to move this up. As a result of a small change in x. Not the amount, the amount. The amount a function changes as a result of a small change in x. So we know that dy dx is equal to the derivative of the function. dy, though, is representing a change in y, a small change in y. And dx is representing a small change in x. It's the change in y with respect to x. What's happening? How are things changing really close to that point? So if we want to know how much the y's are changing, if we multiply both sides by dx, then we get that dy is equal to f prime of x dx. And this formula is the formula for a differential. It tells us for every small change in y, it's equal to the derivative of the function times the small change in x. So if I was asked to find the differential equation of y equals 4x squared minus secant x, first we can take the derivative, which is dy dx, equals 8x minus secant x tangent x. And then multiply both sides by the dx so that we can see what a small change in y does. It's equal to whatever 8x minus secant x tangent x dx equals. So now if I know the amount of that small change in x, I could plug that into this equation and estimate how y is changing for a given small change in x. In fact, let's do an example equation where we do just that. Let's find the differential and evaluate when x is equal to 0 and the small change in x, dx, is equal to 0.2. And let's do the function y equals 5x minus 3 over 2x plus 1. What we're asking for is at the point 0 on this function, if the x changes a little bit, if the x changes by 0.2, how much would we expect the y to change by? What's the little bit y changes by? Well, for this one, it's going to be quite a dramatic change because of its structure. First, we have to find the derivative, dy dx. And we know the derivative of a fraction is the derivative of the top times the bottom minus the derivative of the bottom times the top. And so that gives us 5 times 2x plus 1 minus 2 times 5x minus 3 all over the bottom squared, the 2x plus 1 squared. Let's clean that up a little bit. 5 times 2, let's distribute, is 10x plus 5 minus, distributing the negative 2 through, 10x plus 6 over 2x plus 1 squared. And that's nice because the 10x's subtract out to 0. So we're left with 11 over 2x plus 1 squared. To get the differential, we just multiply both sides by the dx. And we find out that the differential in y, the change in y, the difference in y, is equal to 11 over 2x plus 1 squared dx. Now we're asked to evaluate it. Evaluate what the change in y is when x is 0 and the change in x is 0.2. Well, we'll estimate that as 11 over 2 times x, which is 0, plus 1 squared, times the differential, times the 0.2, which comes out to be 11 times 0.2 over 1, which is 2.2. So at the point 0, when x changes 0.2, we're going to expect the y to change by about 2.2. And that's how we can find that differential and see kind of that estimated change at the point. So the big thing for today, though, is linearization to estimate a point. And we also took a little bit of a look at differentials. Take a look at those, practice a few, and we will see you in class. One of the most important things the derivative can tell us is where the minimum and maximum points are on a function. So that's what the question we're going to look at today is: how do we identify the minimum or the maximum points of a function? And to set this up, there's a little bit of vocabulary that we need to be familiar with as we work with this concept. And to help us kind of visualize the vocabulary, I'm going to put a function here. Let's say it's going to start at 0. It's going to come down, come up really high, go down really low, come up a little bit, and then go towards an asymptote at 0. OK? The first vocabulary word we need to know is what is the absolute minimum. And quite simply, the absolute minimum is the lowest point. So let's actually give this graph that we just made some coordinates here. Let's call this, we'll just make it 1, 2 up and 1, 2 down. So you can see that the absolute minimum, the absolute lowest point, is at y equals -2. It's down low at y equals -2. The other word we need to know is, as you might expect, the absolute maximum, as you might expect, is the highest point on the graph. And so the highest point on this graph is up at this top peak. We're going to call that the absolute maximum. And you see that's at a height of 2. Y equals 2 is the absolute maximum of this graph. We can kind of generalize this idea of absoluteness with what we call the absolute extrema. And that is basically just talking about both the absolute max and min together. So when I say what are the absolute extrema, I'm asking what's the absolute maximum and what's the absolute minimum. But we don't just have absolute maximums and minimums. We also have what we call local minimums, which we'll say is the lowest point in the area. So there's nobody lower around here, so we're going to call it the absolute minimum. And you'll see we've got a little dip off to the right. We can call the, we can call that the local minimum, because it's kind of a valley. It's not the lowest valley, but it is the lowest valley in the area. So that's going to be at y equals -1. And similarly, we can have a local maximum, which, as you would expect, is the highest point in the area. And the local maximum, you'll see off to the right with this little peak, is the local max. It's the highest mountain in the area. It's just not the highest mountain overall. And that one has a height of 1, so we would say that is y equals 1. And similarly, we can lump those together and call them the local extrema, which is all the local min-maxes grouped together. What's interesting about all of these points, though, is if we notice the derivative or the tangent line at each of these points is always going to be a flat line. The derivative at each of these points is equal to 0. They have a slope of 0, slope of 0, slope of 0, and slope of 0. Anytime the slope is 0, that's going to identify one of these local min or local max, and possibly an absolute min or max. We have a special name for those points. Those are called critical points. Critical points are a point where the derivative is either 0 or undefined. And what's really important there is it might be a local extremum. It's not guaranteed to be a local min or a local max, or even an absolute min or an absolute max, but it certainly is a very good candidate for that to occur. So using this idea, this leads into, getting away from the vocabulary now, this leads into what we call the extreme value theorem, or affectionately called the EVT, extreme value theorem. And basically, the extreme value theorem states that if a function f is continuous on an interval between a and b, then there is an absolute maximum on AB and an absolute minimum on AB. In other words, if we take a closed interval, somewhere on that interval is going to be a maximum, and somewhere on that interval is going to be a minimum. And what's really important to note is the min and max points are either A, the first point of the interval, B, the end of the interval, or what we're going to call C. They're either at A, B, or C, where C is when the derivative at that point equals 0, or where C is a critical point. What this is really saying is find the critical points and test these points and the edges. And either the critical points or the edges are going to be your minimums and or your maximums. Let's take a look at what we mean by that. Let's say that f of x is equal to 2x cubed minus 3x squared minus 12x plus 5. And we're going to look on the interval from 0 to 4 to find the absolute minimum and the absolute maximum in that range. Well, first we have to find the critical points. And that's when the derivative is equal to 0. Because it might level off and come back down. So where is that derivative equal to 0? Well, the derivative is 6x squared minus 6x minus 12. And we'll set that equal to 0. Solving, we factor out a 6. X squared minus x minus 2. Continuing to factor, we have x minus 2 times x plus 1. And so we've got two potential critical points, 2 and negative 1. These are the critical points. That's where the derivative is 0. That's where it levels off. However, we need to be careful. All we really care about is numbers between 0 and 4. So negative 1 doesn't really help us because it's outside of the range. So now we know our critical points. We just have to test what is f of the critical point, what is f of the edge, and f of the other edge. One of those is the minimum, and one of those is the maximum, and one we don't really care about. So let's get our calculator. Let's hit y equals. Clear out any function that might be in there. And let's just type our function in here, 2x cubed minus 3x squared minus 12x plus 5. And we'll hit second table so that we can enter in our own values. And let's delete out the values we don't care about. So we're interested in when x is 2, when x is 0, and when x is 4. And you see our y's are negative 15, 5, and 37. Negative 15, 5, and 37. And we can see on there that negative 15 is the minimum number. The 37 is the maximum number. We don't care about the 0. But we have a maximum of 37 at x equals 4. And we have a minimum of negative 15 at x equals 2. We've identified our minimum and maximum using the extreme value theorem, or EVT, for this function on this range. Let's try one more that might be a little more open. Let's see what happens when we say f of x equals cosine squared of x. And we're going to do it on negative infinity to infinity. It's not really a closed interval, but the extreme value theorem should still apply here. We can't check the extremes of negative infinity and positive infinity, but we certainly can check the critical points to see if there's any minimums or maximums. So first, f prime of x, the derivative. It's a chain rule, so we have 2 times the cosine of x times the derivative of cosine, which is sine. And we want to know when that derivative is equal to 0. Well, it's already factored. We just have the cosine of x equals 0 and the sine of x equals 0. First, thinking about the cosine of x on our unit circle, cosine of x is equal to 0. Cosine's the x-coordinate. It's equal to 0 at the top and at the bottom, which means x here is equal to pi over 2. And then we move a pi over to 3 pi over 2. So it's pi over 2 plus n pi's. Every pi around And n can be any element of the integers. We'll say n is some integer 1, 2, 3, 4, or it could be -1, -2, -3, -4. For sine of x is going to be the x-coordinates. I'm sorry, the y-coordinates. And the y-coordinates are 0 here at 0 and pi. So sine of x tells us that x is equal to pi plus n pi. Well, let's go to our calculator and see what we have for mins and maxes. Hitting y equals, clearing out the old function. We want to do parentheses, the cosine of x, and we want to square it. Delete out the old values for the table. And our first point is pi over 2. We get 0. Add in pi, so we've got pi over 2 plus 1 pi. We get 0 again. And pi over 2 plus 2 pi. We get 0 again and again. So what we see is each of these guys is going to give us 0 for a height. Let's try the other ones. Let's just try pi and plus n pi from our secant, from the sine. So just pi is equal to 1. What if we do pi plus pi? Pi plus 1 pi. Also equal to 1. What about pi plus 2 pi? Also equal to 1. What we see is each of these always equals to 1. So we're going to have not an absolute max or an absolute min because it doesn't peak out, but we do get these relative maximums and relative minimums. So we can say the relative, or not relative, but local minimum at x equals pi, or I would say local minimum of 0 at x equals pi over 2 plus n pi, where n is an element of the integers. And we have a local maximum of 1 at x equals pi plus n pi, where n is an element of the integers again. Just to kind of see what's happening here, if I were to actually graph this, let's adjust our window. Let's go from -6 pi to pi. And I want to label every pi over 2. I'm going to do a minimum of -2 and a maximum of 2. And then when I graph it, you see every pi over 2, there's either a local min or a local max. I didn't do the window I wanted, but it gets the idea here. As we get a local min or a local max every pi over 2 based on what we just found. And we know the height's 1 and the heights are 0. So that's the big idea for today, is the extreme value theorem. That if f is continuous, all we need to do is find the critical points and check the edges. And one of those is going to be the local min, or the absolute min. And one of those is going to be the absolute max. Take a look at it on the homework today. And we will see you in class to talk about the extreme value theorem a little bit more. Today we're going to take a look at what's called the mean value theorem. The mean value theorem takes a look at answering the question, when is the instantaneous rate of change, or the rate of change at any specific moment, equal to the average rate of change. So for example, if you go on an hour-long trip and you average 40 miles an hour on that trip, when were you actually driving 40 miles an hour? Sometimes you were driving faster, sometimes you were driving slower, but when were you actually equal to the 40 miles an hour, or your average for the entire trip? And this is what the mean value theorem finds for us. The mean value theorem, or sometimes called MVT. First, before we can use the mean value theorem, there are two requirements that must be met. And if either of these are not true, the mean value theorem does not apply. First, the function must be continuous on the range we're talking about, from a to b. And second, it must be differential on that same range from a to b. If the function is continuous between two numbers and differentiable on those two numbers, or between those two numbers, then we can say that there exists at least one point C that is between A and B, such that the derivative at that point is equal to the rate of change, or the slope, the f of b minus f of a over b minus a. Maybe to help us see this, it might help to see it graphically, what we're talking about. Graphically, what we're saying is, if I take a curve that goes from one point around up into another point, from A to B, where we've got f of A and f of b on the y-axis. If I was to connect the point directly from A to B with a straight line, that slope is going to be my average rate of change between the 2 points. And what the mean value theorem states is that there is at least one point then in between them, called C, where the tangent line is parallel. In other words, the instantaneous rate of change at that point is the same as the average between A and B. In fact, you might notice that there's 2 points on this graph that give us a parallel slope. So maybe we could call them C1 and C2. This graph actually has 2 points where the slope is equal to the average slope between the 2 points. That's what the mean value theorem states, is that there's a point in the middle that has the same tangent slope as the secant from A to B. So first, I mentioned the requirements of the mean value theorem. It's always important to check the requirements. Is it differentiable? Is it continuous? So we could ask the question, does the mean value theorem apply? Or maybe it'd be better to say, when does the mean value theorem apply? Let's change it to that. When does the mean value theorem apply to y equals the square root of x squared minus x minus 2. Well, we could take the derivative of just about any point, and it's continuous at just about every point, except for one important point, or one important thing. What's under the square root must always be greater than or equal to 0. So what we're really saying is x squared minus x minus 2 must be greater than or equal to 0 for the mean value theorem to apply, because that's the only time it's actually continuous. Well, if we factor that, we get x minus 2 times x plus 1 is greater than or equal to 0. And so we find out we've got these two potential solutions of 2 and negative 1. And we want to know when those solutions are positive specifically. So if I make a little graph here, you can see we've got a 0 at negative 1 and a 0 at 2. It's an x squared graph, so we should know it's a parabola. And specifically, we want the graph to be positive. We know it's positive on the left and the right, but negative in the center. When it's negative in the center, the graph's not continuous. So the range, when the mean value theorem applies, when it's actually continuous, is from negative infinity to negative 1. And actually, we'll include the negative 1, because it's continuous at 0. Union from 2 to infinity. These are the points on which our graph is positive. The graph of what's under the square root is positive, meaning we can actually take the square root. It's actually continuous on those points. So those are the only ranges when the mean value theorem would apply. We could even ask more directly, does the mean value theorem apply to maybe y equals the natural log of 5x minus 1 over the interval from 0 to 3? Well, we know the domain of the natural log, what's inside the natural log, must be greater than 0. It can't even be equal to 0. So what we need to check is 5x minus 1 greater than 0 going to put us outside of the range of 0 to 3 that this problem's interested in. Add 1. 5x is greater than 1. Divide by 5. X must be greater than 1/5. So we would say, no, the mean value theorem does not apply because it is undefined from 0 to 1/5. If we were just going from 1 to 3, the mean value theorem would work because it's defined on all of those points. It's continuous on all of those points. But because it's discontinuous from 0 to 1/5, the mean value theorem will not apply over the range 0 to 3. Let's try another one. Y equals e to the 3x squared minus 1. With e and with x squared and with multiplication and with subtraction, we know the graph is continuous. There's no jumps, no breaks, no holes, no gaps. It's also differentiable on the entire graph. The derivative, we'd have to use a nice little chain rule. But if we took the derivative, it would be e to the 3x squared minus 1 times the derivative of the top stuff, which is 6x. And the minus 1 goes to 0. But this is also defined on all points. So there's nowhere this is discontinuous. There's nowhere where this is not differentiable. I didn't even give the range, but let's just give it one, because I should have. Let's say over negative 2 to 2. Definitely between negative 2 and 2, this is all defined. So we would say, yes, the mean value theorem is going to apply to this function on this range. which means between -2 and 2, the average rate of change can be found as an instantaneous rate of change. We don't know where, but we definitely know it exists. OK, then. Let's see, now that we've checked the requirements, let's see if we can use the mean value theorem. First, we're going to do it kind of visually. I want to graph this function and connect the a and b, and then show tangent lines. There's at least one. There might be more, so I'll put the s in parentheses, with the same slope. So the graph we're working with is f of x equals x cubed minus 6x squared plus 8x. So let's take an x out to try and graph it. Gives us x squared minus 6x plus 8. Continuing to factor, that's x minus 2 times x minus 4. And so we have zeros at x equals 0, 2, and 4. And so we should be able to graph this. Before we graph this, let's go ahead and figure out what the slope is between the points, between the edges. It didn't even give a range. Let's do the range on -1 to 6. So let's find f of -1 and f of 6. And we'll have our calculator help with that, just to make it a little quicker. We have x cubed minus 6x squared plus 8x. And I'll go to my table. Let's delete out the values we don't want. At -1, it's equal to -15. And at 6, it's equal to 48. So we had -15 and 48. So this graph's not going to be really to scale. But at -1, and then 1, 2, 3, 4, 5, 6, up here is going to be 48. Which means we've got about -15 down here somewhere. We have a 0 at 0, 2, and 4. We know at 6 it's equal to 48. And at -1 it's -15. So this graph's going to come in, go up, go down, and up. But what this problem really wants us to do is connect the endpoints with this line. And then go ahead and just show graphically that we can draw a parallel line that's tangent to the graph, at least at one point. And you notice there's 2 points where those lines are parallel. Probably a little too steep there. Whoop, too far the other direction. Ah, tricky. There we go. Parallel lines, same slope, tangent to the points on the graph between our a and our b, between -1 and -6. But just doing it graphically is a little boring. Let's actually find the points. Let's find the points C where we get that average rate of change is equal to the instantaneous rate of change, or f prime of c. The derivative at c is f of b minus f of a over b minus a. And let's go ahead and do the same function that we did up above. We're going to do f of x equals x cubed minus 6x squared plus 8x on the same range of -1, 6. And we're trying to find these black dots that we just found. Where are those points that we're going to get the same slope as the average slope? Well, first let's find the average slope. That's f of b minus f of a over b minus a. Or f of 6, using the endpoints, minus f of negative 1 over 6 minus negative 1. And we just saw that f of 6 is equal to 48. Minus f of negative 1 is negative 15 over 6 minus negative 1. So we have 63 over 7, which is equal to a nice, pretty 9. So we want to know when the derivative is going to be equal to 9. So we're going to find the derivative, f prime of x, which is 3x squared minus 12x plus 8. We want to know when that's equal to the average slope, or equal to 9. Well, we need to subtract 9 from both sides to make it equal to 0. 3x squared minus 12x minus 1 equals 0. And you might see that that's not going to factor very nicely. So let's see. Our x, then, using the quadratic formula, is equal to 12 plus or minus the square root of 12 squared minus 4 times 3 times negative 1 all over 2 times 3. And when I do that on my calculator, I'll end up with two values. First, if we subtract, you get negative 0.08 and 4.08. So my graph's not really to scale, but we would have hit those slopes at negative 0.08 and 4.08. So I went through and made a graph that was more to scale than the one that we had before. The red curve that you see here is our function that we've been working with. And then what I did is I put a dot at negative 1, comma, negative 15, and 6, comma, 48. And you can see I've connected them with this orange line. Then what I did is I put a purple dot here at the first point that we had, the negative 0.08, and drew a tangent line. I also put a dot at the second point that we found at 4.08 and drew a tangent line. And you see that those blue tangent lines are perfectly parallel to the orange tangent line. And what that means is that the instantaneous rate of change at those 2 points on those blue lines is equal to the average rate of change of the orange line that connects the two endpoints. And that's visually how the mean value theorem works. So our two answers do work. The mean value theorem is right there on your screen. The big thing we're talking about today is that if the function is continuous and differentiable between the two endpoints, there exists at least one point C such that the instantaneous rate of change is equal to the average rate of change, or the slope, between the 2 points. Take a look at the assignment and try a few of these, and we'll take a closer look at them in class. The derivatives can tell us a whole bunch about the shape of a graph of a function. And that's what we're going to look at today. We're going to answer the question, what do derivatives tell us about the shape of a graph? First thing we're going to look at is what is called the first derivative test. And to kind of set up what the first derivative test does, I'm going to draw a little picture here. Actually, 3 pictures, 3 little graphs. And we're going to compare what the derivative is doing. on each. So here is some function f kind of curving upwards. We'll have some function f curving downwards. And then we'll have a function f that comes up to a point. And we're going to be interested particularly at a point C, kind of in the middle of both of the, or all three of these, and what the derivative is doing at each one of those. Now, we know the derivative is the slope of the tangent line at that point. And so if I draw my point and the tangent line, for the one that's increasing, for the one that's curving upwards, you see the slope is also going upwards. In other words, if the function f of x is increasing, the derivative f prime of x is positive. And similarly, at the point C, on the curve that's decreasing or going down, you'll see that the slope of the tangent line is going downhill. It is negative. So we'll say that when f of x is decreasing, the derivative f prime of x is negative. Now, at the peak here on the third graph, you'll notice that it's neither increasing or decreasing. And in fact, the tangent line is completely flat at that point. So if f of x is neither increasing nor decreasing, then f prime of x is 0, which is neither positive nor negative. Now, we recognize that point as a point when the derivative is 0. We call that a critical point. We already know that critical points are where the derivative is 0. It's either a maximum or a minimum value. So let's summarize that conclusion in the actual test, the first derivative test. What we're going to do with the first derivative test to learn about the function is first we're going to find all critical points. And as a reminder, that's when f prime of x is equal to 0 or it's undefined. Once we find those points, we can use those points to divide f prime of x into subregions. And then we can test each subregion. And we'll find out where the derivative is 0. That's going to be where the graph levels out. And then we'll know in between those points, is the graph increasing or decreasing based on what the derivative is doing. So let's see if we can use that test with an example here. The example we're going to play with is f of x equals x cubed minus 12x. We're going to decide where is the derivative 0, where is it increasing, where is it decreasing. Well, first we have to know the derivative. F prime of x is equal to 3x squared minus 12. And to find those critical points, we set it equal to 0. So if I add 12 to both sides, actually, let's just factor it. Let's do 3 times x squared minus 4 equals 0. 3 times x plus 2 times x minus 2 equals 0. So our critical points are x equals negative 2 and positive 2. Those are our critical points. Then what we're going to do is we're going to divide kind of a number line into those sub-regions. we've got -2 and +2. And we know at those points, the derivative is 0. The graph is flat at those points. So what's f prime in those regions? The easiest way to test that is we're going to go to our calculator. On the calculator, we're going to hit the y equals button and type in our derivative function, so we know if the derivative is positive or negative. The derivative function was 3x squared minus 12. And we'll go to our table, second table. Let's delete out the old values. Now, first, we need to test a point in each of these three regions: left of -2, between -2 and +2, and right of 2. So left of -2, we can pick any number. Let's pick -5. And we see it's a +63. So left of -2, the derivative is positive. What that means is that f, the function, left of -2, is actually increasing because the derivative is positive. Between -2 and 2, let's put the number 0 in. It's -12. The derivative is negative between, which means the function itself is decreasing between -2 and 2. Greater than 2, maybe pick the number +5. It's positive. All we care about is the sign. And so that tells us that it is increasing over that range. Now we know where the graph is increasing, decreasing, and then increasing again. It's giving us a general idea of the shape of the graph. But there's more to the graph than just whether it's increasing or decreasing. It helps to know what direction or how it is curving. Is it curving when it goes up on this left part? Is it curving up? Or is it curving up? Those are two very different curves. In red there, we need to know what type of curve it's doing as it's increasing. And that leads us to our next topic, the next thing the derivatives tell us about the graph. And this is what we call concavity. Now, concavity might be a new concept to us, so let's set it up first with a little bit of vocabulary. The first word we need to know is, what is concave up? Concave up means the graph itself appears to be rotating counterclockwise. And if you think about a general parabola, starting from the left, you see it rotates counterclockwise as you draw the parabola. You also could have something approaching an asymptote, kind of giving a counterclockwise rotation. Or even if it was increasing, a counterclockwise rotation. Going from left to right, you're moving around the circle counterclockwise. And that kind of makes sense counterclockwise if we think about our unit circle, which we're very familiar with. We count unit circles counterclockwise. So that's a positive concave up motion going counterclockwise. Another way that I like to think about concave up is if I think about the parabola, it looks like the u of concave up. And that reminds me that u up is concave up. As you might expect, the next word is concave down. And here we are rotating clockwise. Or if you think about the unit circle, in the negative direction. If you start from the left, a negative parabola is concave down. It's going clockwise around. And you could also get things approaching asymptotes in much the similar way. These all are concave down. And as you might expect, with calculus, we're interested in when we switch between a concave up motion and a concave down motion. Just like when we switch from increasing and decreasing, we have critical points. With concavity, when we switch between concave up and concave down, what we end up with are called inflection points. And that is where the concavity changes. For example, the graph could be first concave up, and then it's going to switch to concave down. Right in the center there, you see the rotation direction changes. Starts out going clockwise or counterclockwise, then it changes to clockwise. The classic x cubed also, let's see, this one starts out going counterclockwise and then turning it to clockwise. You start concave up, and then you change to concave down in the middle. Those are inflection points where the concavity changes. And just like a critical point is when the derivative is equal to 0, concavity can also be found. The way we find those inflection points is we look at the second derivative, f prime prime of x, and see when it's 0 or undefined. Now, concavity tells us a whole lot when it's combined with the first derivative test and whether the graph is increasing or decreasing. Let's look at concavity and increasing, decreasing relationships. And to set this up, we're going to do a little tic-tac-toe board here. And we're going to look at what happens if the graph is increasing and it's concave up. If it's increasing and concave up, we have to rotate counterclockwise as we increase. Contrast that with increasing and concave down. Now, as we are increasing, we have to rotate clockwise, which takes us off in the other direction. Similarly, we can compare what happens when we are decreasing. If we are decreasing and we're concave up, as we go down, we have to rotate counterclockwise. Versus if it's decreasing and concave down, as we rotate, it has to rotate downward clockwise. So if we know both of these facts about the graph, we will very quickly know the shape of the graph and what is going on at various points. And we test for concavity very similar to how we test the first derivative test, except instead of finding critical points, first we find inflection points. And once we find those inflection points, we can divide the second derivative, f prime prime of x, into subregions. And again, we will test each subregion. So let's take a look at just doing that test for concavity, and then we'll bring it together here in just a minute. So number 4, going back to that same example we had before, where f of x is equal to x cubed minus 12x. We already said the first derivative was 3x squared minus 12. The second derivative, then, we can quickly calculate to be 6x. And so we're going to divide the number line into subregions based on those inflection points, based on when that second derivative equals 0. We'll divide both sides by 6, and x equals 0 is my inflection point. And so right at 0 is where we are going to split up the f prime prime to see what's happening. Where is the second derivative positive and negative? Going to y equals now. I'm going to clear out the second derivative, or the first derivative. We'll put in the second derivative equation, which is just 6x. And then go to the table, delete out what I don't need. And I might have been able to do this in my head. In fact, I should be able to do this one in my head. But just to show you for the more complex equations, I'm going to test something to the left of 0, maybe negative 5. And I see the second derivative is negative. Then we'll test something to the right of 0, maybe positive 5. And we'll see the second derivative is positive. So we've divided into subregions. We know where the second derivative is positive and negative. Now we know if our function, the original function, x cubed minus 12, is concave up or concave down. We see on the left it's negative, so it is concave down to begin with, up until 0, where it becomes concave up. So we know on the left it's going to have some type of clockwise motion. On the right, it's going to have some type of counterclockwise motion. Kind of running out of space. Whoops. OK. Now that we know how these tests all work, let's bring it all together. With our function f of x equals x cubed minus 12x. The first derivative, which I'm going to always represent in blue here, is 3x squared minus 12. And we know if we make that equal to 0, we found out earlier that gave us critical points at -2 and +2. The second derivative I'm going to represent now in green is going to be 6x, which when we made that equal to 0, that gave us inflection point at 0. I strongly encourage you color code your critical points and your inflection points so you don't get them confused as you're breaking up into subregions here. We know we've got critical points at -2 and 2. So these guys are going to split up my f prime, my first derivative. I've got an inflection point at 0, so that's how I'm going to split up the second derivative of f prime prime. And ultimately, we're interested in what's happening to our function f in each of these regions. There's not actually a lot of space to the left, so I'm going to rewrite that. Give myself a little more space. F, f prime, and f prime prime. OK. First, in green, to the left of 0, we found out the second derivative was negative. So we know it's going to be concave down. To the right of 0, we found out that the second derivative was positive. And so we know there that the graph is concave up. In blue, in the middle, the first derivative to the left of 2, now we're looking at the blue lines, ignoring the green lines. To the left of 2, we found out the second derivative was positive, which meant the graph is increasing. Between -2 and +2, we found out the second derivative was negative. which means the graph is decreasing between those points. To the right of 2, we found out that the first derivative was positive, and so we know the graph is increasing. So now at the very top, in red, we should have an idea what the graph of f is doing. Left of -2, we see that we're concave down and increasing. So concave down and increasing, the graph is going to curve clockwise while increasing. Then, between -2 and 0, we see it's still concave down, but it's decreasing. Decreasing in concave down is going to go clockwise and downward. But after 0, we're still decreasing, but the graph is concave up, which means it's going to rotate its curve to be concave up as it's decreasing. To the right of 2, it is concave up and increasing. So we're rotating counterclockwise as we increase. Now we have a lot better idea of what's happening with this graph. Let's see if we can actually make our graph. And I'm not going to put anything on the y-axis yet because we don't quite have those. What we do know about the graph is, and I'm going to put a little dotted line. It's just to kind of mark right there on -2 is going to be some type of critical point. So I should expect it to level off when it hits the blue line. At 2 is another critical point. So I should expect it to level off when it hits that blue line. And then at 0 is going to be my inflection point where the rotation changes. Okay, we know our graph increases and rotates clockwise up to a critical point. Then it's going to decrease, continuing to rotate clockwise until it hits an inflection point where the rotation should change, but it should still be decreasing until it hits a critical point. And then we keep rotating counterclockwise as we increase. And I want to notice all the elements of our graph. It starts out increasing, then it's decreasing, then it's increasing. It starts out rotating clockwise until the inflection point when it rotates counterclockwise, giving us the concave down on the left and concave up on the right. And this is how the derivatives can help us get a very good idea of the shape of the function. Try a few of these on your own. Come back to class ready to discuss them, and we will see you then. Now that we've taken a look at concavity and increasing and decreasing functions, we've just got a little bit to add to our conversation as we look at how do we graph functions with calculus. And the main missing piece we have right now is what happens with limits at infinity. Basically, what happens is we take the limit as x goes to infinity of our function f of x, or what happens as the limit as x goes to negative infinity of our function f of x. And the big idea we look for here is we consider kind of a who takes over. As x gets large. So for example, if I wanted to do the limit as x goes to infinity of 3x squared minus 7x plus 5 all over 5x cubed plus 2x squared minus 7, who's going to take over in this case? Well, in the numerator, the 3x squared will take over because x squared is bigger than any x or any constant. So when we square really big numbers, it's going to become huge. And in the denominator, the x cubed is going to take over because it's got the highest exponent. In fact, what we could also say is that the x cubed is going to get bigger faster than the numerator. What we're really saying is the numerator is going to be whatever it becomes, but the denominator is going to become the biggest part of this function. That 5x cubed is just going to become huge faster than any other part of this function. Well, if we take any old number and divide it by just a huge number as x gets close to infinity, dividing by a huge number is going to basically leave nothing left. And you can see that this limit, as x goes to infinity, is basically going to equal 0. Similarly, if I wanted to look at the limit as x goes to infinity of 3x cubed minus 5x plus 1 over 1x cubed plus 6x minus 2, similarly, we can see in the numerator the x cubed, the 3x cubed begins to take over the numerator as it becomes huge. And in the denominator, the regular x cubed takes over. But as we can see, neither one of those is going to get bigger faster. So essentially, they are going to get bigger at the same rate. Because whatever we cube in the numerator, we're also cubing in the denominator. And essentially, that part that's cubed will reduce or divide out. The x cubes divide out, leaving behind on the biggest part 3 over 1, or in this case, just the number 3. Because the x cubes, ultimately, as they become huge, divide out, and everything else is too small to worry about, we're just left with 3. Compare that with the limit as x goes to, let's do negative infinity this time, of 6x minus 2 over the square root of 4x squared plus 3x. I'm going to scroll up a bit so we can see better. The numerator, we can see the 6x takes over. That's 6 times some huge negative number, which means that 6x becomes a large negative in the numerator. In the denominator, the 4x squared takes over, but we're taking the square root of that. And so that becomes the square root of 4x squared taking over. But notice that reduces to 2x. And because we square the negative, that's x squared, the negative squared becomes a positive. So 2x is actually a large positive number. And that, again, is because the x squared makes that part positive. Times a positive is positive, and the square root is still positive. So ultimately, what we've ended up with is the x's, 6x over 2x, where the x's can essentially divide out, but not the negative. The negative is still there. As x goes to negative infinity, the numerator is going to go to negative 6, while the denominator goes to 2. giving us a final limit at infinity of -3. And this is kind of the game we keep playing as we look at solving these limits at infinity. We look at who's taking over, what's happening to x as it gets huge, whether positive or negative. And we have to be very careful with what's happening with the signs. Is it positive or negative? So if I want the limit as x goes to infinity of x cubed minus 6x over x squared plus 5, again, in the numerator, the x cubed is going to take over. In the denominator, the x squared is going to take over. But what you see is they're not growing at the same rate. This time, the numerator grows faster, because cubed is going to get huge faster than squared will get huge. And so similar to our first example, we're going to end up with a big number divided by something that's much smaller, that's not growing at the same rate. So if I take a huge number and divide it by something small, I'm still going to be huge. And so in this case, this one's actually going to keep getting bigger up to infinity. We need this concept of the limit as x goes to infinity to see what's happening with the end behavior, or on the far left or the far right of the graph. The first example we took a look at, on the far edge of the graph to the right towards infinity, this graph is approaching an asymptote at 0. The second example at infinity is approaching an asymptote at 3. The third example at negative infinity is approaching an asymptote at -3. Well, the fourth example is not approaching an asymptote at all. It's just going off to infinity, forever getting bigger. We're going to combine this concept of limits at infinity with all the other stuff we've seen about graphing a function. So first, our general strategy. Let's get everything down in one place that we know about how to graph a function. First, it's helpful to find the domain. Where is the graph or the function undefined? Do we have a hole? Do we have a vertical asymptote? What's going on with the domain? The second thing that we found back in pre-calculus days was we found the x and y intercepts. Then we're going to add what we talked about today, which is finding the limit as x goes to infinity of f of x, and the limit as x goes to negative infinity of f of x, because that's going to tell us the end behavior, or what's happening at the edge of the graph. Does it approach an asymptote, or does it go off to infinity? Speaking of asymptotes, we can also find any vertical asymptotes. Those are going to come from the domain, not the holes. The holes and the vertical asymptotes come from the domain. But specifically, the vertical asymptotes we'll want to label, if there are any. Then, using, and I'm going to always do this one in blue, using f prime of x, identify the critical points and increasing, decreasing regions. That's what we talked about in our previous video from section 4.5, the first derivative test. Then, using, and I'll always do this in green, f prime prime of x, or the second derivative, identify inflection points and concavity. Is it concave up or concave down? And when we put all this together, we should have a very good idea of what this graph looks like before ever touching the graph button on our calculator. So let's see if we can work through one example and graph f of x equals x cubed minus 3x plus 2. And I'll work through all the pieces we just talked about. First, the domain. There's cubing, adding, subtracting, multiplying here. No restrictions on those. The domain is all real numbers. So nothing fancy there. To find x-intercepts, we set the whole thing equal to 0. I should do a different color here. Let's say 0 equals x cubed minus 3x plus 2. And I'm going to use the rational root theorem and synthetic division to find these zeros. The options are plus or minus 1 and plus or minus 2. So let's try first x equals 1, 1, 0, negative 3, and 2. Don't forget the 0 for the x squared. Bring down the 1, bring down the 1. 1 times 1 is 1, negative 2. Oops. Getting ahead of myself. Negative 2 and 0. So that did work. So x equals 1 is a 0. And now I have 1x squared plus 1x minus 2 equals 0, which is x plus 2 times x minus 1. Bring down the other factor that we got of x plus 1. Oops, not x plus 1. We've got to subtract 1 from both sides. So that's x minus 1. And since we've got two matching guys, we're going to say that x plus 2 times x minus 1 squared equals 0. So x is equal to negative 2 and positive 1. Those are the x-intercepts. For the y-intercepts, we only have to make the x's all equal to 0. So we get 0 cubed minus 3 times 0 plus 2, which is 2. So y equals 2 is our y-intercept. Part C is to look at the limit. And I'm going to scroll up to give us a little more room. As x goes to infinity of our function x cubed minus 3x plus 2. And you see the x cubed takes over. So if we cube infinity, what we end up with is just infinity. But we also need to consider the other limit as x goes to negative infinity off the left of our graph of x cubed minus 3x plus 2. Again, the x cubed takes over because it gets bigger faster than anything else. But this time, we're cubing a negative large number. When we cube a negative large number, we'll get a negative larger number. So this, on the left side, is going to go to negative infinity. So we know from the left, it's towards negative infinity. And it's going to exit on the right towards positive infinity. Vertical asymptotes. Vertical asymptotes come from, let me write down, vertical asymptotes. Vertical asymptotes come from when the denominator equals 0, but we have no fraction here with this function, so there are none. With fractions, you'll have to be careful of those. E is our first derivative test, finding the critical points and where it's increasing or decreasing. So f of x, again, was x cubed minus 3x plus 2. So our derivative is 3x squared minus 3. And we find our critical points by making it equal to 0. Factor out of 3, x squared minus 1, x plus 1, x minus 1. So our critical points are -1 and +1. We're going to combine that with the information from part F, which is the second derivative. The first derivative we already have, so taking the second derivative there is 6x. Set that equal to 0, and so x is equal to 0 becomes an inflection point. Now, for the sake of our graph, it's going to be helpful to know, well, actually, let's over here to the right first. Let's make our number line. We're going to break it up with an inflection point at 0 and a critical point at -1 and +1. So the critical point split it up into 3 regions. The inflection point splits it into 2 regions. So we can consider what's happening with f prime prime, f prime, and ultimately learn about f. OK, on my calculator here, I'm going to hit y equals. In y1, I'm going to type in the original function, because it's going to give me some key points that I'm going to want to actually know their exact coordinates. So in y1, the function is x cubed minus 3x plus 2. My y2, this is the first derivative, 3x squared minus 3. y3 is my second derivative of 6x. And now I'm going to go second table and delete out this information I don't want. First thing I'm going to do is figure out the exact coordinates of the critical points and the inflection points. My critical points were at -1 and 1, and the inflection point is at 0. What's nice is that gives me the coordinates of -4, 1 and 1, 0 as my critical points. So we have -1, 4 and 1, 0 as my critical points. We're going to need those in a minute. And the other thing we pulled off the calculator was that the inflection point 0 is at 0, 2. We're going to need that inflection point here in just a minute. Now let's see if we can learn what's happening in each of the regions that we've mapped out here for our graph. Actually, what I'm going to do is I'm going to go to y equals. And I'm going to highlight the equals on y1, because I don't care about f right now. I just care about what's happening with the first derivative and the second derivative. So if I highlight the equals and hit enter, you'll see it's no longer highlighted. Now when I go to second table, it's just going to tell me y2 and y3. So first, for the second derivative, that's in the third column there. The second derivative, we need something to the left of 0. How about -5? To the left of 0, you see y3, the second derivative, is negative. So my second derivative is negative. It is concave down to begin with. It's rotating clockwise to begin with. To the right, maybe at +5, you see the second derivative is y3. It's positive. So it's positive on the right, which means it's concave up. Now let's go to the blue, the first derivative. We want to know if it's positive or negative, so we know if it's increasing or decreasing. y2 has my first derivative in it, so I'm looking at this column. First, we need something to the left of -1. We already have -5. And notice it's a positive number. So it starts out positive, which means it is increasing initially. Something between -1 and 1 would be 0. Notice the derivative is negative. So it's negative, which means it's decreasing until the next critical point. Something to the right of 1, we could use the number 5 that we already have, which is positive. So we know it's increasing after that point. Then we're going to put this all together to decide with increasing, decreasing, concave up, and concave down, what's the general shape in each of these 4 regions. Starting out concave down, counterclockwise rotation, but increasing, we know our graph starts going up with a clockwise rotation. Still concave down after the critical point, but now decreasing, it's going to go down with that concave down motion. From the bottom of that, though, after 0, after that inflection point, it needs to be concave up, but still decreasing. So you'll start to see the rotation go counterclockwise after 0, but then start increasing after the critical point at 1, still concave up. And so we can kind of see the shape, the direction. It's going to go kind of like an upside down parabola. It's going to turn to an upside up parabola. Notice it exits at -infinity on the left like we expect. It goes off to positive infinity on the right like we'd expect. We're going to put all this information together to make our final big graph. All right, first, let's go through our list of things we discovered. The domain's all real numbers, but we have x-intercepts at -2 and 1. I did those in purple. We had x-intercepts at -2 and +1. We also have a y-intercept at 2. So at 2, there's a y-intercept. We know on the left, it's going off at -infinity. On the right, it's going off at positive infinity. We also know that there is a critical point, and I'm going to do this in blue so I don't miss my colors, critical points at -1, 4, and a critical point at 1, 0, which is also one of our intercepts. We also know there's an inflection point at 0, 2, which is also one of our intercepts. But that is an inflection point where it's going to switch rotation from positive, it starts negative, from a negative rotation to a positive rotation. So we should see it comes in from the negative, starts out increasing with a negative rotation, hits the critical point, and now it's decreasing. But once it hits that inflection point, the rotation is going to change direction. Hits the critical point, and now it's increasing. And now we've got our graph of our function. Notice, just like we expected, the first derivative told us it starts increasing, then decreasing, then increasing. The second derivative says it's concave down or a negative rotation, then concave up or a positive rotation, switching at that inflection point. And that is how we can graph our functions using calculus. There's a lot of pieces, so you do need to practice this. So take a look at the book, the assignment, and we'll see you in class to discuss this further. All this conversation around graphs, the shapes of graphs, when the derivative equals 0 to find key points, has a very important application, and that is in what we call the applied optimization problems. So our question that we're going to attempt to answer is, how do we optimize or find the most efficient, the fastest, the biggest, the smallest? How do we optimize a value of interest? And ultimately, what we're really asking is, when does the derivative equal 0? Because that's the peak or the valley. That's the optimal point for the most efficient or most profit or least expense or shortest distance or shortest time that we're trying to get after. So let's take a look at a few of these classic optimization problems. And then from there, you should be able to solve lots of different types of optimization problems. The first classic problem is what we call the rectangle problem, where we're generally trying to either minimize the perimeter, maximize the area, something related to that effect. So let's say a farmer has 80 feet of fencing to enclose a pasture along a rock wall. What that means is he only has to actually fence 3 sides of the wall, not all 4 sides of the wall. So what dimensions would maximize the area? So let's draw a picture to kind of see what's going on. We've got this rock wall already. And what this farmer's going to do is he's going to make a fence that goes alongside that rock wall. So he's really only fencing 3 sides. And we need to give variables to the sides as we calculate the area, because that's what we want to maximize. So we'll say it's an x by y fence, which means the other side's also x, if we're thinking about perimeter. And we know that the area of any rectangle is equal to the length times the width, or in this case, x times the y. But that gives us 2 variables. So we need to constrain one of those variables so that we can reduce it down to 1 variable. And that's going to come from the limit we're given, is that we have 80 feet of fencing available to us. Well, if there's 80 feet available to us, that means the total distance, x plus y plus x, or 2x plus y, that total distance has to equal the 80 feet of fencing. Well, the easiest variable to solve for here would probably be y. So we'll subtract 2x, and we'll say that y is equal to 80 minus 2x. And we'll replace the y in our area formula to be 80 minus the 2x. To make life easier, we'll go ahead and distribute. So area is equal to 80x minus 2x squared. And we want to maximize this area. So if we think about maybe the graph of the area is going to increase to a certain point and then come down after that point. We're looking to find that maximum point, and we know at that point the slope of the derivative is equal to 0. So let's find the derivative of the area in terms of x. The derivative of the area is equal to 80 minus 4x. And we just need to make that equal to 0 to find the critical point where this fence area is optimized. Add the 4x to both sides, and 80 equals 4x. Divide both sides by 4, and x is equal to 20. Now that we know where that maximum occurs, we plug that in for x in the y equals equation. Y equals 80 minus 2 times 20, or 80 minus 40, which is 40. So for the farmer to maximize the area of his 3-sided fence along the rock wall, he should do a 20-foot by 40-foot fence. And I think fence actually has a C in it. 20-foot by 40-foot fence. And that's the idea of the rectangle problem. Let's try another problem. This is probably one of the most classic problems of all calculus. What I'm going to call the run and swim problem. And rather than write this all out, I'm just going to kind of draw a picture and narrate what I'm talking about. We've got this river. That's water. Does that look like a river? We've got this river, and a person is on one side of the river. And he wants maybe a pot of gold that's on the other side of the river. It is going to be 9 miles down the river is where that pot of gold is. But the river is also 2 miles wide. What this person can do is he's going to run along the river a ways. Then he's going to jump in the water and swim diagonally across a ways. What we want to know is how far should he run, so we'll call the running x, before he starts swimming, in order to get to that pot of gold in the most efficient, quickest way possible. Well, we need to know a few things about this person. Let's say the person runs 6 miles per hour and swims 3 miles per hour. So how far should the person run? So let's write out the question. How far should the person run before swimming? Well, let's see if we can get a little more information on this. The swim distance, let's call that swim distance y. So we've got it labeled. And then we're going to have this gap here on this right triangle. We already know the height of the triangle is 2, but that gap, if the total distance from the person to the pot of gold is 9, and he runs or she runs x, it's going to be 9 minus x is what's going to be left horizontally. Let's give ourselves a little bit more workspace. Well, we should remember that the formula for distance is equal to rate times time. And we're trying to minimize the time. So let's go ahead and solve this for time. And we'll say time is equal to the total distance divided by the rate. And we know that the person is going to be running at a rate of 6 miles per hour. So the run time is going to be the distance, we don't know x, divided by the rate, or 6 miles per hour. While the swim time is going to be the distance divided by the rate. The swim time, the y, the diagonal, we don't know. Or the swim distance, the y, the diagonal, we don't know. But we do know the rate at which the person swims is 3 miles per hour. So the total time is equal to the sum of these things, x over 6 plus y over 3. The other thing we're going to use to our advantage is we have a right triangle formed on the edge of the river. Pythagorean theorem tells us that 9 minus x squared plus the height, which is 2 squared, is equal to the swim distance, which is y squared. Doing a little simplifying, squaring the 2 gives us 4, but we want to get rid of the y squared, so taking the square root of both sides, we'll have 9 minus x squared plus 4 under the square root is equal to y. So let's replace the y in our time equation with that information. Time is equal to x over 6 plus the square root of 9 minus x squared plus 4 over 3. This time is what we want to minimize. In other words, the graph here is going to come down to some point, and we need to find out what point has a slope of 0 on its tangent line. And the way we do that is we take the derivative and set the derivative equal to 0. Square roots are a little bit more work to take the derivative of, so let's actually rewrite this with a 1/2 power. So we have x over 6 plus the 9 minus x squared plus 4 to the 1/2 power over 3, because that's going to be easier to take a derivative of. So the derivative of the time, the derivative of x over 6 is just 1 over 6, plus, let's make a big fraction, and we'll do this piece by piece. First, the 1/3's a constant, so that's going to be out front. We can bring the exponent of 1/2 out front as we take the derivative, which means we've got a 2 in the denominator and a 1 in the numerator. Then we reduce the exponent by 1, which makes it to the negative 1/2 power. The negative 1/2 power, the negative exponent moves it down to the denominator. So now we've got 9 minus x squared plus 4 to the 1/2, but in the denominator because of the negative exponent. Then we have to multiply by the derivative of the inside using our chain rule. So we've got this little piece, the 9 minus x squared, that we can take the derivative of, brings the 2 out front, times the 9 minus x. Reduce the exponent by 1, just leaves 9 minus x. And then we have to multiply by the derivative of inside that. And the derivative of negative x is negative 1. Let's see if we can clean that up a little bit. What I notice is we've got 2's that divide out, which is nice. So, let's take this negative and do a positive times a negative is a negative. So we've got 1/6 minus, we're left with the 9 minus x in the numerator. Let's do this in brown, actually. It's a better color. We've got 1/6 minus 9 minus x is left in the numerator, and that's it, so I don't really need the parentheses, over 3, and let's go ahead and take that 1/2 and make it back into a square root, times 9 minus x squared plus 4. And we know when this derivative equals 0, we've got our minimum time. Switch over to purple. We're going to add that first fraction to the other, that second fraction to the other side, giving us 1/6 equals 9 minus x over 3 square roots of 9 minus x squared plus 4. We now have 2 equal fractions. We can solve 2 equal fractions by multiplying the diagonals. 1 times 3 times the square root is 3 square roots of 9 minus x squared plus 4 equals 6 times 9 minus x. So I'll go back to blue here as we solve. Square root's going to be annoying, so let's square both sides. Actually, blue's a bad color. Let's do green to get a little more contrast. Square both sides. And we know when we square both sides, because it's all multiplying, we square the pieces. 3 squared is 9. Squaring the square root gets rid of it. So it's 9 times 9 minus x squared plus 4 equals 6 squared is 36 times 9 minus x squared. Let's distribute the 9 onto both parts here. Will give us 9 times the 9 minus x squared, plus 9 times 4 is 36, equals 36 times 9 minus x squared. And if we keep the 9 minus x squareds as a group, we see we've got 36 of them on the right and 9 of them on the left. To make life easier, let's subtract 9 of these 9 minus x squareds from both sides. And that tells us that 36 equals 27 of these 9 minus x squareds. Divide both sides by 27. 36 over 27 reduces to 4/3 equals 9 minus x squared. Get rid of the squared with the square root of both sides, and we get 2 over the square root of 3 equals 9 minus x. And I'm going to add x to both sides and subtract. Oops, it's plus or minus 2 root 3. Sorry, that's important. If we add x to both sides and add and subtract the 2 root 3 from both sides, we get x is equal to 9 plus or minus 2 divided by the square root of 3. Pulling up our calculator to take a look at this, we've got 9 plus 2 divided by the square root of 3 is one answer. But what you notice is that gives us 10.15. Going back to the original, the whole distance was only 9. If I go 10.15, I'm actually going past my pot of gold and having to go backwards. That's not the best strategy to go about. So we probably don't want that solution. So let's try again, and we're going to do 9 minus 2 divided by the square root of 3. And we find out x, the distance we should run, is about 7.85. So this person's a really good runner. He's going to run 7.85 miles before the person jumps into the water, and either she or he will swim the rest of the way. So now we know she or he's going to run 7.85 miles, jump in the water, and swim the rest of the way to the pot of gold. That'll be the quickest way to get to the pot of gold. That's the run and swim problem. Another classic problem is what I like to call the hallway problem. The hallway problem is best illustrated with a picture. The idea is you've got a hallway that goes around a corner, but the width of the hallway is not the same on both sides. Maybe on one side the hallway is 10 feet long, and on the other side the hallway is 8 feet long. And the question becomes, how long of a piece of furniture, or maybe some long picture, can you get around that corner in this hallway as you move into the apartment around the corner? Let's go ahead and write that out. What is the longest piece of furniture to fit around the corner? Well, to set this up, we need a little bit more information on here. One thing we're going to be interested in is what is the angle theta that we're going to be at in order to maximize our distance. Now we know from geometry, if I extend the wall from the top side across, this vertical angle across from it is going to have the exact same measurement. So we get a triangle to the left, and if I drop a line down, we have a triangle to the right. We actually have two similar triangles, but one has a height of 8 feet, and the other one has a base of 10 feet. Also, we're interested in the pieces of this furniture length. So we're going to label the left side x and the top right side y. And we know that the total length of my furniture is equal to x plus y. But we don't like having two variables. So we have to try and use our relationships to reduce it down to one variable. And actually, that one variable is going to be neither x or y. It's going to be theta, the angle that connects them both. With the 10-foot triangle, from the theta, we have the adjacent side and the hypotenuse that we're working with. That means we're going to use the cosine over there. We know that the cosine of theta is 10 over x. And with the other theta on the y, we've got the opposite side and the hypotenuse. That tells us that the sine of theta is equal to 8 over y. Solving both these equations for x and y, we multiply by x and divide by the cosine. X is equal to 10 over the cosine of theta. And y is equal to 8 over the sine of theta. But rather than dealing with the reciprocals of cosine and sine, let's just use the reciprocal trig functions. And we'll say that x is equal to 10 secant of theta. And y is equal to 8 cosecant of theta. Now we can replace x and y with these pieces. And we've been reduced down to one variable. The length is equal to 10 secant theta plus the y, which is 8 cosecant of theta. Now we've got our function. We're just looking for the spot that maximizes our distance, or our size of our furniture, where the slope is equal to 0. So we'll take the derivative. L prime is equal to, let's do this in a different color. Let's go to brown. L prime is equal to 10. The derivative of secant is secant tangent. Secant theta tangent theta plus 8. The derivative of cosecant is negative cosecant cotangent. So instead of plus 8, let's say minus 8 cosecant cotangent theta. And all we need to know is when this equation equals 0. Well, let's start by moving the negative part over to the right side. So we've got 10 secant theta tangent theta equals 8 cosecant theta cotangent theta. And probably the easiest way to solve this would be to change this all into sines and cosines, since we're more familiar with sines and cosines, and seeing if we can establish what's happening here. So we'll make a fraction. 10's in the numerator. Secant is 1 over cosine, so it's 10 over, we've got a cosine theta. Tangent is sine over cosine. So we've got a sine theta over cosine. Cosine times cosine is cosine squared. Equals, a fraction for the right side, 8 cosecant is 1 over sine. So that puts a sine theta in the denominator. And cotangent is cosine over sine. So cosine theta over sine theta. But we already have a sine theta, so now it's sine theta, or sine squared theta. Let's clear out the fractions by doing the cross multiply trick we've done before. So we've got 10 sine times sine squared is sine cubed theta equals 8 cosine cubed theta. Let's move the numbers to one side and the variables to the other side. We're more comfortable with tangent, which is sine over cosine. So let's move the cosines to the right. Or to the left. We're going to divide both sides by cosine cubed theta. And we'll move the numbers to the right by dividing both sides by 10. Sine cubed over cosine cubed is tangent cubed. The cosine cubes are gone. 8 over 10 reduces to 4/5. Get rid of the cube with the cube root of both sides. And then tangent of theta, our angle, is the cubed root of 4/5. So theta is equal to the tangent inverse of the cubed root of 4/5. Or to make it easier on our, well, yeah, let's just type that in our calculator. Let's find out what theta, our angle, is equal to. We want to do the tangent inverse of the cubed root, which is conveniently under math. Option number 4 is a cubed root of 4/5. And the tangent inverse of the cubed root of 4/5 is 0.7482. 0.7482. But if you remember our picture wasn't interested in the angle, 0.7482 radians. That's what we just found, is that angle. We're interested in how long is the x and how long is the y. Which means we have to come back to our x equals and our y equals equations in order to find those pieces. So we have x is equal to 10 over the cosine of our angle, which is 0.7482. And y is equal to 8 over the sine of our angle, which is 0.7482. Fortunately, our calculator can do that for us quite nicely. So we've got 10 divided by the cosine of 0.7482. And so that x distance is going to be 13.64. For our y distance, 8 divided by the sine of 0.7482. That y distance is 11.76. So for our final answer, the total length of my furniture that can fit around the corner, the 13.64 plus 11.76 is going to be 25.4 feet. I can fit anything that's 25.4 feet long around this corner. If it's any longer, it won't fit. I can't take it into my new apartment. And that's how we solve the hallway problem. So these applied optimization problems can come in many different forms, but the philosophy is always the same. find out some relationship between the variables, take the derivative, and set that derivative equal to 0, and we can optimize, either maximize or minimize, depending on the context, almost any situation. Take a look at a few and try a few, and we will discuss it more in class. Another application of the derivative is something that can help us solve limits that before were unsolvable. The question we're going to answer is, how do we take a limit of an indeterminate form? And the way we're going to do that is with what is called L'Hopital's rule. Now, L'Hopital was a French mathematician who published this idea in a French calculus text. However, he's probably not the one who came up with it. It was probably one of the Bernoulli mathematicians. The Bernoullis was a Swiss family that were some of the most amazing mathematicians ever, and they all were from the same family. And there's some evidence that one of the Bernoullis were the first to come up with it, while L'Hopital was the first to publish this rule, or this trick, to take the limit of an indeterminate form. But first, before we can get into what the rule is, let's make sure we understand what the heck is an indeterminate form. There's lots of indeterminate forms. These are things that are technically undefined, but we know that limits often exist at points that are undefined. And one of these, there's actually two really common ones that we're going to use, is when the limit as x goes to some number, we'll call it a, it could also go to infinity, of f of x over g of x, where we've got some fraction. But when we normally do a fraction with a limit, we take the limit of the numerator and the limit of a denominator and simplify what that comes out to. But when that reduces to 0 divided by 0, we say that is an indeterminate form. We don't determine anything. It doesn't necessarily mean it doesn't exist. 0 divided by 0 is indeterminate, so we need to do another strategy in order to solve. The second indeterminate form, a really similar idea, is the limit as x goes to a of f of x divided by g of x. Sometimes will equal infinity over infinity. And it could be either positive or negative over a positive or a negative infinity. But this is also indeterminate because it turns out there are different sizes of infinity, and we don't know if we're dividing by the same size or different size. Is it 0? Is it infinity? Is it 1? It could be lots of different things. So if our limit is one of these indeterminate forms, L'Hopital suggests the way we solve it using his rule. If our limit is an indeterminate form, it can be shown that the limit as x goes to a of that fraction, f of x over g of x, is equal to the same limit as x goes to a, but this time of f prime of x over g prime of x. And often, this second limit is much easier to take. In other words, if we do a division or a fraction with an indeterminate form, we'll just take the derivative of the numerator and the derivative of the denominator and calculate that limit. So let's do some examples where we do just that. First example, we're going to take the limit as x goes to 0 of sine x over x. Now, normally, we'd plug 0 into the numerator, and the sine of 0 is 0. And we plug 0 into the denominator, and that becomes 0. So what we're really saying is 0 over 0. which is an indeterminate form. So what we will do is we will take the limit as x goes to 0 of the derivatives of the top and bottom, the numerator and denominator. The derivative of sine is cosine, and the derivative of x is 1. So we're really saying, let's plug 0 into the cosine of x. So we'd have the cosine of 0 over, the 1 is still 1, and the cosine at 0 is 1. So this limit, as x approaches 0, is actually approaching 1. And that's L'Hopital's rule. Take the derivative of the numerator and the denominator, and take the limit. Let's try another one. Let's do the limit as x goes to 1 of the sine of pi x over the natural log of x. Well, if we plug 1 into both of these, we get 1 times pi, or the sine of pi. And the sine of pi, the y-coordinate there is 0. And the natural log of 1 means e to the 0 power is 1. So we've got 0 over 0. We have an indeterminate form. Because we have the indeterminate form, we can take the derivative of the top and bottom and find that same limit. The derivative of sine pi x is cosine pi x times the derivative of the inside, which is pi, over the derivative of the natural log of x is 1 over x. Well, 1 over x, that is dividing by a fraction. It's the same as multiplying by the reciprocal. So I'm going to simplify this one step further and flip that fraction over. And we have x pi cosine pi x. And now if we plug 1 in, we get 1 times pi times the cosine of pi times 1, or 1 pi. So we have 1 times pi. Cosine of pi, the x-coordinate at pi is -1. So we have 1 times pi times -1, which is negative pi. Our limit as x goes to 1 is negative pi. This even works on problems with infinity that we've seen before. Let's say, remember when we were doing limits at infinity, the limit as x goes to infinity of 3x squared plus 2x minus 1 over 5x squared minus x plus 1. And if you remember before when we were doing limits with infinity, we said, OK, the x squared is going to take over. And so the x squared part gets huge. And then we end up dividing out the x squareds, and we're left with 3/5. But let's solve this using another method, using L'Hopital's rule. Because as x goes to infinity, the numerator becomes infinity squared times 3 plus 2 times infinity. It's going to infinity. Same thing with the denominator. It's going to infinity. We have infinity over infinity, which means we have an indeterminate form. And we can take the derivatives of the numerator and denominator. That gives us 6x plus 2 over 5x minus 1. Nope, 10x minus 1, sorry. But now, if we plug infinity in, we have 6 times infinity, which goes to infinity. And then the denominator, we've got 10 times infinity, which goes to infinity, which means we still have an indeterminate form. But there's no reason we can't use L'Hopital's rule twice. So again, we'll take the derivative. The limit as x goes to infinity. The derivative of the numerator is 6 over the derivative of the denominator is 10. And that's just a constant. It doesn't matter what x is approaching. It's a constant, 6/10, which reduces to 3/5. We can even use L'Hopital's rule with a one-sided limit. Let's say the limit as x goes to 0 from the right of the natural log of x over the cotangent of x. We might need a little bit more room here. Now, as x goes to 0 from the right, the natural log goes to negative infinity. And as cotangent goes to 0, remember cotangent is cosine over sine. Cosine over sine is actually going to be an asymptote. That guy's going to infinity. We have negative infinity over infinity. We have another indeterminate form, so we'll take the derivative of the numerator and the denominator. The derivative of the natural log is 1 over x. The derivative of cotangent is negative cosecant squared x. And let's actually simplify that. It's negative. 1 over x sticks an x in the denominator. And cosecant is the reciprocal of sine, so let's put the sine squared in the numerator. Whoops, I forgot the limit. That's important. The limit as x goes to 0 from the right of sine squared x negative over x. And now if we plug 0 in, the sine of 0 is 0. Squared is 0. And if we plug 0 in, the denominator now goes to 0. So all we've done is we've gone from indeterminate form infinity over infinity to another indeterminate form, 0 over 0. So L'Hopital says we do it again. The limit as x goes to 0 from the right of the derivative of negative sine, well, the negative stays there. The derivative of sine squared is 2 sine x times the derivative of the inside, which is cosine x, over the derivative of x is 1. Now we can plug 0 in, and we'll actually get a solution. Now we have negative 2 sine of 0 cosine of 0, which is negative 2 times the sine of 0 is 0, the cosine of 0 is 1, and it simplifies down to a limit of 0. So this is the big idea of L'Hopital's rule. If we have infinity over infinity, or 0 over 0, we'll take the derivative of both the numerator and denominator so that we can take the limit and plug it in. We might have to do it several times, but eventually we can get down to a limit. Those are the indeterminate forms that L'Hopital's rule allows us to work with. But there are still other indeterminate forms that you could end up with. The general strategy we're going to imply for these other indeterminate forms is that we need to make them either 0 over 0 or plus or minus infinity over plus or minus infinity. We're going to massage them a little bit to try and make them into an indeterminate form. One classic indeterminate form is 0 times infinity form. What's nice is the reciprocal of 0 is infinity. So we're going to move that 0 to the denominator, and then we'll be in an indeterminate form. Or the reciprocal of infinity is 0. So we could do the reciprocal and move it to the denominator, because dividing by a reciprocal is the same as multiplying. And we'll end up with a form we can work with. Here's what this looks like. The limit as x goes to 0 of x squared of the natural log of x. Now x squared, that's going to 0. But the natural log of 0, natural log is approaching negative infinity. So we've really got 0 times negative infinity. So we're going to rewrite this problem, moving one piece down to the denominator as a reciprocal. So let's move the x squared down here. So we'll have the limit as x goes to 0 of the natural log of x over x to the negative 2, or the reciprocal. X to the negative 2 would move that exponent up. So you can see these are equivalent expressions. But now what we have is the natural log of x still approaching negative infinity. And x to the negative 2, or 1 over x squared, is approaching infinity. And the reason that's going to 0 is we have 1 divided by a teeny tiny number. And when we divide by a teeny tiny number, we get a huge number as a result. So now we have the correct indeterminate form. We're ready to use L'Hopital's rule. And we have the limit as x goes to 0 of the derivative of the numerator, which is 1 over x, over the derivative of the denominator, which is negative 2, x to the negative 3. Cleaning that up a little bit, the negative 2 is going to stay in the denominator. We still have the limit as x goes to 0. Leave the negative 2 in the denominator. But the x to the negative 3 moves up. And the 1 over x means it needs to move down. And actually, that can clean up a little bit. We have the limit as x goes to 0 of x squared over negative 2. And now we're ready to plug 0 in for the x. And when we plug 0 in for the x, we get 0 squared divided by negative 2, which is just 0. So how we handle that 0 times infinity form is we move one piece to the denominator using its reciprocal. It's still equivalent that way, and then we're in that indeterminate form that we can use L'Hopital's rule on. Another indeterminate form is when we have infinity minus infinity. If we have infinity minus infinity, we need to find a way to combine these to get a single fraction. An example of this would be the limit as x goes to 0 from the right of 1 over x squared minus 1 over sine of x. If we were to plug 0 in, we would have 1 over 0, which is infinity. And the sine of 0 is 0, so we have 1 over 0, which is infinity. And so we end up with infinity minus infinity, which is not necessarily 0 because they might be different sizes of infinity. So this is indeterminate form. So we need to combine them into a single fraction so that we can try and use L'Hopital's rule if we do, in fact, have an indeterminate form. Common denominator would mean we multiply the first fraction by sine x over x, and the second fraction by x squared over x squared. And that's going to give us sine x minus x squared. Whoops, forgot the limit part. That's important. The limit, as x approaches 0 from the right, of sine x minus x squared over x squared times sine x. Now you'll see if we plug 0 into the numerator, the sine of 0 is 0. Minus 0 squared is 0. And in the denominator, we multiply 0 times 0 to get 0. We have an indeterminate form which we can use. So now we have the limit as x goes to 0 from the right of the derivative of sine is cosine x minus 2x over 2x times sine x using our product rule plus x squared times negative cosine x. So I'll make it, oops, sorry, not negative cosine x. Derivative of sine is positive cosine. So we have x squared times cosine x. Now we have something that we can take the limit as x goes to 0 on. Let's break this down piece by piece so we can really see what's happening. When we plug 0 into the cosine of 0 is 1, minus, actually let's just hit equals. The cosine of 0 is 1, minus 2 times 0 over 2 times 0 sine of 0 minus 0 squared times the cosine of 0. Well, we still are ending up with 0 in the denominator, or we're getting closer and closer to 0 from the right, because we end up with 0 minus 0 in the denominator. But as we get closer and closer to 0 from the right, what that really means we're doing is we have left in the numerator is 1 minus 0, divided by something that is almost 0, because we're getting closer to 0 from the right. 1 divided by almost 0, or 1 divided by something really, really small. When we divide by tiny, 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 tiny things, we end up with huge answers. And so this limit, as x goes to 0 from the right, is going to be a positive infinity. Let's try another one. Another indeterminate form is when we have infinity to the 0 power. It's not necessarily 1. Might be 1. But not necessarily. For these, we're going to use logarithmic substitution to help us out to solve these problems. If we have the limit as x goes to infinity of x to the 1 over x, you'll notice the exponent, 1 over infinity, is going to 0, and the base, infinity, is going to infinity. We have infinity to the 0 power. So we're going to rewrite it. Using logarithmic substitution, we're going to let y equal the stuff we're taking the limit of, 1 over the x. Natural log of both sides moves the exponent out front. And we're going to take the limit of what we ended up with, and know we can undo that natural log by taking e to whatever power we end up with as our limit or our solution. So we're going to take the limit as x goes to infinity of, and we're going to write it as a fraction, natural log of x over x. Because we know that natural log, as x goes to infinity, also goes to infinity. And so we now have infinity over infinity. We can now use L'Hopital's rule. The limit as x goes to infinity of 1 over x over 1, which, if we clean it up, is the limit as x goes to infinity, moving that x to the denominator of 1 over x. Which we know we're doing 1 divided by infinity, or 1 divided by a huge number. And when we divide by a huge number, you're just left with 0. But that is the limit of our natural log. We have to undo the unnatural log by taking e to that power. E to the natural log of y is y, so e to the 0, and I'll make a note here to undo the natural log that we did. The opposite of taking a natural log is e to the exponent. We take that solution we had as our exponent, and e to the 0 is 1. So our limit as x goes to infinity of x to the 1 over x is equal to 1. Let's try another one where we use that strategy again, where we take the natural log of y in order to help us solve. This one turns out to be in the 0 to the 0 form, which is also indeterminate because a base of 0 should have a 0 for a solution, but an exponent of 0 should have 1 for a solution. So what is the solution? Well, it depends. Let's take the limit as x goes to 0 from the right of x to the sine of x power. Again, you'll notice if we plug 0 into the sine of x, the sine of 0 is 0. And then we have a base of 0, so 0 to the 0 power is indeterminate. So we let y equal x sine of x. And then we take the natural log of y, which moves the exponent out front. So we have sine of x times the natural log of x. Now again, we're going to get rid of that natural log by taking e to our exponent. So we're going to actually calculate the limit as x goes to 0 from the right of sine x times the natural log of x. The problem is, as sine goes to 0, as x goes to 0, sine goes to 0. And as natural log goes to 0, it goes to negative infinity. We've got 0 times negative infinity. We've done this form before. This was number 1, where we said we're going to move a reciprocal down into the denominator. Let's use that exact same strategy here. We could move either one. There is one that actually turns out to be easier and better. I'm going to come down on the next line to give me some space. Let's move the sine of x into the denominator. So the limit as x goes to 0 from the right of the natural log of x over the sine 1 over the sine of x. It has to be the reciprocal when we move it down. And actually, what's nice is we know the reciprocal of the sine function is the cosecant. So we're really doing the natural log of x over the cosecant of x, which means now we've got the natural log as x goes to 0, the natural log goes to negative infinity. And for the cosecant, as x goes to 0, cosecant goes to positive infinity. We have an indeterminate form that we can finally use L'Hopital's rule on. So now we have the limit as x goes to 0 from the right of the derivatives. 1 over x over the derivative of cosecant is negative cosecant cotangent. And let's clean that up. The limit as x goes to 0 from the right. The 1 over x moves the x down. Cosecant and cotangent are both very familiar reciprocal functions, which will move them up, which will be very nice. Cosecant is the reciprocal of sine, so negative sine x. And cotangent is the reciprocal of tangent, so negative sine x over x, tangent of x. Let's keep cleaning this up. I want to break this up into 2 pieces. Let's break this up into the limit as x goes to 0 from the right of the negative sine x over x times the tangent of x. Because what's interesting there is we know we can use our limit properties to break that up into the product. The limit as x goes to 0 from the right of negative sine x over x times the limit as x goes to 0 from the right of the tangent of x. And why would that be better? Well, if you remember at the very start of our discussion, we solved the limit as x goes to 0 of sine x over x. We know that's equal to 1. So coming down to our problem, we have that same limit. We just have a negative sign, which can come out front. So if sine x over x is 1, negative sine x over x is negative 1. Times, plugging 0 into tangent x. Tangent is sine over cosine. Sine of 0 is 0, so we have 0 over 1, which is 0, which means negative 1 times 0. We've got our limit at 0. But let's not get too excited, because remember, we did that natural log substitution. So we have to undo that natural log substitution by just taking e raised to our solution. Our solution was 0. E to the 0 is 1. And so we ended up with 1 for our solution. So that's L'Hopital's rule. L'Hopital's rule says we can take the derivative of the numerator and denominator if we have an indeterminate form, like 0 over 0 or infinity over infinity at the limit. However, if it's not in one of those indeterminate forms, we're going to have to massage the problem a little bit to put it into a useful indeterminate form. We might do that by moving a piece to the denominator. We might do that by combining fractions into 1. Or we might do that with logarithmic substitution. Take a look at these, give them a good practice, and we will discuss them more in class. Today we're going to address another question in applied calculus with derivatives, and that is, how do I find the solution? Actually, it might be better to say a solution, because sometimes there's more than one, to f of x equals 0. This question is going to give rise to what we call Newton's method. And this is very similar, actually, to what your calculator is going to do to find solutions to various equations. Now, we already know that if ax plus b equals 0, all we have to do to solve for x is subtract b and divide by a, and we get our solution. We also know that if it's a quadratic, ax squared plus bx plus c equals 0, we also know we can solve for x using this simple quadratic equation of the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And we also actually have a similar formula for cubic functions. The cubic's a lot more involved, but one certainly does exist. But outside of that, we don't necessarily have a general solution method to solve for equations that become more complex and more complicated. And so what we do is we use Newton's method to kind of estimate the solution to any function. To get an idea of what we're doing, we're first going to look graphically at what's happening. Graphically, what we are doing looks like this. Say there's some function here that comes down, up, and around. And we want to know what is the 0, what is the solution to that function. And it's not a real pretty number, so we're going to have to estimate it. So what we will do then is we will guess as close as we can get, and we will call that our first guess. We'll use x sub 0. And then we'll take that to the line. And yes, it's pretty close to our 0. So to figure out what's happening around there is we will use the tangent line. And the tangent line is going to give us our x1, which is our next guess. And if we go to the line, that's closer. So what we will do is we will find the tangent line, which gets us even closer. And we call that x2. And then we go to the line and do another tangent line. And you see those tangent lines are going to keep getting closer and closer to our actual 0 until we can actually estimate its exact point. So graphically, what we're doing is we're making a guess at x1. Then we go to f of x1 and find the tangent line. And then this gives a better guess. And then we'll call it x2. So we find f of x2 and find the tangent line. And you can see how we begin to repeat the process until we get close enough for our purposes. So if that's graphically the process, let's look at the equation of the tangent line at x sub 0, or our starting guess. Well, we know that y equals f of x naught, the y-coordinate, plus the slope, f prime, at x naught, times x minus the x naught, is the equation of the tangent line. But then we can find the point x1 on this line that hits 0. Basically, what we're saying is 0 equals the f of x naught plus f prime of x naught times x1, our new guess, the new x-coordinate, minus x naught. And then we will solve this equation for the x1. As we solve the equation for the x1, you'll see that we'll first subtract off the f of x naught. Then we'll divide out the f prime of x naught. And then we'll add the x sub 0, which leaves the x sub 1. All that to say, this formula tells us how to find the next point. Or maybe we can say it more generally, x sub n is equal to the previous guess, x sub n minus 1, minus f of the point, x sub n minus 1, divided by the derivative, x sub n minus 1. This is going to be the important equation we're going to use to make it all work. Let's do an example. And we're going to do all the ugly work on our calculator, which is going to be really nice. So our first example, f of x is equal to x cubed minus 5x plus 2. And we want to know when that equals 0. To help us, we'll do f prime of x, the derivative, which is 3x squared minus 5. And to get an idea of the shape of the graph, let's go ahead and hit y equals And I'm going to graph it. We've got, what, x cubed minus 5x plus 2. And when I graph it, you'll see the graph comes up, down, and back up. And we're going to be interested in seeing if we can figure out what is that value just to the right of the origin. It looks like it's between 0 and 1. Just to the right there, what is that value? So just to kind of sketch a graph. The graph comes up, down, and up. And we're trying to find this guy just to the right of the origin that is between 0 and 1. I'm going to give you some calculator instructions that are going to save you a lot of work. What you're going to start by doing is we're going to put f of x into y2, the second row. And then we're going to put the derivative, f prime of x, into y3. And then in y1, we're going to put our formula, which is the x minus the y2 equation at x divided by the y3 equation at x into y1. And you'll notice that is exactly the Newton's formula that we just found, where x is the n minus 1. y2 is the function. y3 is the derivative of the function. And the way we grab the function is we type in vars, go over to yvars, and then we go over to function. So let's take a look at what that means. Y equals, clear. First, I'm going to put f of x into y2. So y2 is x cubed minus 5x plus 2. Then I put the derivative into y3, 3x squared minus 5. Enter. And then I'll go up to y1. And for y1, we'll type in x minus. We need to grab the y2 equation. Right next to the arrows is the vars button. Scroll over to yvars and select function. And we want the y2 function, which is the second one. And then we'll open up a parentheses and say we want to plug the x value into the y2. And we're going to divide by the y3 function at x. So vars over to yvars, function. y3 is the third option. And we want to plug x into there. Now, when I hit second table, let's delete out the points I don't want. In x, I can put my first guess for the 0. We said our 0 was between, our solution was between 0 and 1. So let's just guess maybe 1 for our first guess. When we put 1 in for our first guess, Newton's method says the tangent line is going to take us over to 0. So that 0 becomes my next guess. Put 0 in for the next guess, and Newton's method says the tangent line pulls us over to 0.4. That's a little closer. So we'll type in 0.4 for our next guess. Now we've got 0.41416 for our next guess. And that gets us a little closer. So I'll type in 0.41421. And you notice when I type that in, I get the exact same thing for my solution. That tells me I'm as close as I can get for my guess. So I'm going to come back to my whiteboard here, and I'm going to summarize those results from the calculator. Just to summarize, we started with x1, or x0. Our first guess was at 1. That gave us our next guess, which was at 0. Our next guess the calculator gave us was 0.4. Our next guess the calculator gave us was 0.41416. Our next guess the calculator gave us, which was 0.41421. And then when we plugged that in, we again got 0.41421. And when we get the same thing on it, then we say that our solution is exactly that. X equals 0.41421 is the solution that exists between 0 and 1. L'Hopital's rule is really nice, though, because it even works with non-polynomial functions, some transcendental functions that are a lot harder to work with. So let's try the second example here, where we say the secant of x minus x squared. We want to know when that equals 5. Well, Newton's method tells us when things are equal to 0. So what can we do about the 5? Exactly right. We're going to subtract 5 from both sides to get the actual function we're going to use Newton's method with. So we have the secant of x minus x squared minus 5 equals 0. And we also need the derivative, which is secant x tangent x minus 2x. And the derivative of the negative 5 is 0. So we're ready to go to our calculator. First, let's clear out all the old functions. Probably could have kept y1, but it's good to practice typing it in over and over again so you know that formula. But just to get an idea of where it's going, in y2, we're going to type in the function, the original function, which is secant x. Now, the calculator can't do secant x, but it can do 1 divided by the cosine of x, because secant is the reciprocal of cosine, minus x squared minus 5. And when I graph this, we end up with this fancy graph. And it's going to curve across the top to come down and curve across the top to come down. But let's see if we can find the 0 just to the right of the axis again. It looks like it's between 1 and 2. So kind of our rough sketch so that we know what we're working with. It came down, wiggled up, and went up. And then it came back down somehow. We're going to be specifically interested in the first one that is between 1 and 2. So in our y equals, y2 is the derivative. The derivative is secant x, which is 1 over the cosine of x, times the tangent of x, minus 2x. Then again in y1, we're going to type in x minus the second function, y vars function 2, at our x point, divided by our derivative function, which is in the third function, vars, y vars function 3. Second table. Delete out all this other stuff. And we said our first guess was between 1 and 2. So I might try 1. You see, 1 shoots us way out to 5.7. That doesn't feel like it's getting closer. In fact, if I do 5.7018, that's going to shoot me back to 2.7. So 2.7228 shoots me down to a negative number. So I'm actually on the other side. And if I do negative 0.0015, now we're at 26,000. Boy, 1's not getting me closer. What that means is either I'm not close enough to my point, or the slope at my guess is too steep that it's throwing me way out of whack and I'm not getting anywhere. So we said it's between 1 and 2. Let's try 2. 2 shoots me all the way up to 11. And you can already see kind of the same thing beginning to happen. We type in the next point, which shoots me over to 9.7. 9.7617 shoots me over to 4.66. 7.3 shoots me to 4.5. 6.96 shoots me over to 4.0024. Now I'm back at 1.69. I'm all over the map. So let's try a better strategy. I'm not close enough to the point I want. But we know the point is between 1 and 2. So let's try right in the middle of 1 and 2, 1.5. Ah, look at that. It keeps me close to 1.5. We're at 1.46. I feel better for that. So let's try 1.4649. And that gives me 1.43. Notice we're staying very close. That's what we want. 1.429. 1.4283. And notice that tangent line is going to be exactly the same. We finally got close enough that we found our 0. I do want to make sure I'm showing my work. So I'm going to list out my guesses. My first guess, we started at 1.5. My next guess shot us down to 1.4649. My x2 gave me 1.438. x3 gave me 1.429. x4 gave me 1.4283. And x5 gave me 1.4283 again, which was the same. So my solution that's between 1 and 2 is actually at 1.4283. And that is how we do Newton's method. Newton's method just is taking us graphically from a guess to getting closer with the tangent line. Then we use the tangent line to get closer and the tangent line to get closer until we finally find the 0 that we're looking for. We have the advantage of using a calculator to make that process easier, but go ahead and practice a few. Make sure you're comfortable with it. We'll take a look at it in class, and we will see you then. One last thing that I want to do before we wrap up derivatives and begins to take a preview of what is coming in our second quarter of calculus is looking at what is called the antiderivative, or really how we answer the question, how do we find derivatives in reverse? And that derivative in reverse is what we call the antiderivative. And we say that the antiderivative of f of x, lowercase f of x, is the function f of x, but notice it's capital F of x, whose derivative is the lowercase f of x. In other words, if capital F of x, the derivative of that is lowercase f of x, then the capital F of x is the antiderivative of the f of x. Maybe it's better with an example. How about we consider f of x equals 3x squared. Now, based on our power rule, which we know, but we're going to do it in reverse, we can conclude that capital F of x, the antiderivative, must be equal to x cubed. Because notice the derivative of x cubed is 3x squared. So the antiderivative of 3x squared is x cubed. It's the process in reverse. However, there's something we need to note. What if capital F of x equaled not just x cubed, but x cubed minus 1? Or if capital F of x equaled maybe x cubed plus 7. If we took the derivative of both of these, the derivative of the x cubed is the 3x squared we want, and the derivative of the negative 1 is 0. Similarly, with the other equation, with the plus 7, the derivative of x cubed is 3x squared, and the derivative of the 7 goes to 0. So we actually ended up with 3 potential antiderivatives of 3x squared. We've got just x cubed minus 1, or x cubed plus 7. And actually, you can see that we could extend that concept to basically say we could add any constant number to the x cubed, and we would still have an antiderivative. Let's note that we can add any constant, and we'll call that constant c, to any antiderivative. That means we're going to have to note that in our final solution. So when we say the antiderivative, actually, let's write this down. Different color. So the antiderivative of 3x squared is x cubed plus any constant. So let's see if we can kind of use what we know about derivatives and apply those rules in reverse. Let's see if we can do a few examples. Let's say f of x equals 5x to the 4th. Capital F of x, the antiderivative, then, we know that with the power rule, the exponent moves out front and reduces by 1. So we can see the power of 5 moved out front, and then it shrunk 1 from 5 down to 4. So capital F of x, the antiderivative, must be x to the 5th plus any constant. Let's try another one. Let's say f of x is equal to 1 over x. Well, we recognize 1 over x as the derivative of one of our special functions. 1 over x is the derivative of the natural log of x. So the antiderivative must be the natural log of x plus any constant. What about trig? Let's do f of x equals sine of x. What is the antiderivative? We're really asking whose derivative is the sine of x? Well, we know the sine of x is the derivative of cosine of x, but there's that extra negative. The derivative of cosine is negative sine, so we might assume the derivative of negative cosine then must be the positive sign. And of course, it's going to be plus any constant. What about f of x equals e to the x? Well, this is our favorite function because the derivative is itself, and so likewise the antiderivative will be itself plus any constant. So we've been kind of playing with this idea of an antiderivative, of just kind of thinking the derivative of what should equal this. What do we know about derivatives? What patterns can we notice to kind of come up with the solution? But let's formalize what we're doing here with the formal notation for these antiderivatives. The formal notation is we'll use this little squiggly sign. That squiggly sign we call the integral. The integral of f of x, and then we'll put a dx, so we know the variable we're taking the integral of with respect to x. The integral of f of x dx is going to be equal to that capital F of x plus a constant. That integral sign tells us find the antiderivative. And just like we have a bunch of derivative rules, like the derivative off to the side here, like if we want the derivative of x squared, that's equal to 2x. We've got those derivative rules. We also have integral rules as well. And we have one for powers, the power rule. The power rule says the integral of x to any exponent, dx, is equal to, well, let's see if we can piece this together. The derivative makes the exponent shrink by 1. So we need the exponent to go up by 1. Of course, the derivative says the exponent is multiplied out front. So we're going to divide by that new exponent. And with integrals, there's always a plus c. This is the power rule, a useful formula to be able to use quite quickly. And just like we use the power rule with derivatives a lot, we're going to use the power rule with integrals a lot. There's actually a whole lot of integral rules. Just to give you a taste here, this table is copied out of your textbook. So I'll put a number 2 here, maybe. See textbook for more integral rules. And this table is in 4.10. And you can see this table. And it kind of takes the differentiation formula, which we're familiar with, and does it backwards with an integration formula. The second one is the power rule that we just solved. So there's lots of formulas in there. But we're going to focus mainly on the power rule. Let's see if we can find the integral of 7x cubed minus 5x squared plus 2x minus 7 dx. We'll take this one term at a time. With the 7x cubed, we keep the 7, the constant out front. The x cubed goes up to 4. And then we divide by that new exponent. Then we have minus 5x squared. Now it goes up, because we're doing the antiderivative, goes up to 3. And we divide by that exponent. Plus 2x, we increase the exponent by 1, so now it's squared. And we divide by the exponent. minus 7. Increase the exponent by 1. Right now it was x to the 0. That's why it's not there. Increase it by 1. We have x to the first. And we divide by 1. We don't really need to say the divide by 1. But the 2 over 2 does reduce. And so our final integral is 7x to the fourth over 4 minus 5x to the third over 3 plus x squared minus 7x. And don't forget, we always need, with integrals and antiderivatives, a plus c. We can use the power rule to even integrate some more interesting looking things. Like, for instance, the integral of x cubed minus 2 times the fourth root of x over x squared dx. Now, to help us out here, we're going to massage the function a little bit to make it something we can use in our power rule. One thing we can do, because of the minus in there, is we can distribute the divide by x squared onto both parts. So we actually have the integral of x cubed over x squared minus 2. And let's change that fourth root to an exponent, x to the 1/4 over x squared dx. Well, we can continue to simplify by subtracting exponents. X cubed over x squared is just x minus 2x to the 1/4 minus 2. Well, 2 is 8/4, so 1/4 minus 8/4 is negative 7/4 power dx. Moving up to give us a little more room, let's take the derivative now, or the integral. For the x, we raise the exponent by 1 to get x squared, and divide by 2, minus 2x, and then we raise the exponent by 1, or 4/4, to get negative 3/4, and divide by the new exponent of negative 3/4. Of course, there's going to be a plus c at the end. Never forget the plus c. Cleaning up a little bit, we've got a negative negative. That makes it positive. Dividing by a fraction means multiplying by the reciprocal. So let's multiply by 4/3 instead. So we have x squared over 2 plus 2 times 4 is 8. Negative exponent moves it down, x to the 3/4 plus a constant. And so we have x squared over 2 plus 8 over 3x to the 3/4 plus our constant. Let's try one more. Let's see if we can do a trig one. The integral of cosine of 3x dx. Now, I know the antiderivative of cosine, or what's going to give me cosine when I take the derivative. That's going to be the sine. So I might think maybe sine 3x plus c is my integral. And you'd be very close if you said that. But remember, the chain rule says if we take the derivative of sine of x, the derivative of sine of 3x would be cosine of 3x times the derivative of the inside, which would be times 3. So we have to undo that times 3. And the best way to undo times 3 is to divide by 3. So the integral, or antiderivative, of cosine 3x is the sine of 3x divided by 3 plus a constant. Take a look at some of these in the assignment as you practice a few of these. These antiderivatives or integrals are really about pattern recognition, trying something out and seeing, that's close. How can I adjust to get closer until you get something that is correct? In Calc 2, we'll talk about a lot of strategies to make some of this easier. But for now, we want to kind of get some exposure and some experience with integrals and antiderivatives. So take a few of these, and we will see you in class to discuss them further.